Du. Raz, dva, tři. Raz, dva, tři.
No. Good morning. My name is Karol Kampf, and this is Jaroslav Trnka. We are really happy and thrilled. We can open Amplitudes 2022 and welcome you in Prague in person. So after 3 long years, we can finally meet in person. So let us see if we didn't forget how to organize conference alive. So please, Jaroslav.
Okay, so let me do just a quick intro, and then we will have a welcome speech, and then we will start the conference program. So yeah, welcome everybody to Prague. So this is the first in-person Amplitudes conference after 3 years, or after 2 virtual conferences. Prague, or Praha, means doorstep. So hopefully this is a doorstep to the new era, and we are back. In in-person conferences. Let me say a little bit about the history of Charles University. We are at the Philosophy Faculty of Charles University, one of the historic buildings. Charles University in Prague was established in 1348, so it's one of the oldest universities in Europe, or definitely in Middle Europe, modeled by University of Paris. There is still an old part, or the original part of the building near Carrillo, which is a center of the university in the downtown, you can see. There are many interesting milestones in the history, but one interesting for us was that Albert Einstein was a professor here in 1911 to 1912, and the Faculty of Mathematics and Physics was established in 1952 after the separation of the Natural Sciences faculty. Now, let me now turn to the history of Amplitudes conferences. Some people remember most of them or all of them, but the Amplitudes conferences already have a long tradition, starting in 2009 in Durham. And as you can see here from the table, the number of participants gradually went up. And this year we have 216 or 218, now updated number, participants. But we feel that the field is even bigger, because that which was showed by the virtual conferences in last 2 years, when up to 700 people actually registered. So I thought it would be nice to kind of show the posters or the web pages from these conferences. So it started in 2009 in Durham. It was still not called Amplitudes. It was International Workshop on Gauge and String Amplitudes. But then was Amplitudes 2010 in Queen Mary, 2011 in Michigan, 2012 in Hamburg, Germany. Then 2013, we had a nice conference in Ringberg Castle, owned by Max Planck Institute in Germany. Then 2014, Sakle. Then ETH Zurich, Stockholm in Sweden, Edinburgh, and that was the first one which was organized also with the summer school. Then SLAC in 2018 with the summer school at UC Davis. 2019, unfortunately, was the last in-person conference in Dublin. And then after 2 virtual conferences hosted by Michigan and Brown University, and last year by Niels Bohr Institute in Copenhagen, we are here back to 2022. Now, this is not the first week of our activities. Last week we had Amplitudes Summer School held at the Faculty of Mathematics and Physics. And we had 8 lecture series on various topics in scattering amplitudes, and we had more than 100 students participated, which was great, and many of them are also now taking part in this conference. The recordings from that school are on the YouTube channel for Amplitudes 2022, and we will also upload all the talks from this week. Okay, some practical information. We will have, there will be lunch breaks during the talk in the middle of the day. Lunch is not provided here, but there are many restaurants nearby. And if you go to a lunch break, I suggest you go towards the city center, towards the Old Town Square, and there are many cafes and restaurants that you can find. Important thing about bathrooms, it's kind of non-trivial to find them in this building. So in order to find a bathroom, you have to go half floor up and go around the building on the opposite side. And then on the left side, there are male, and right side, there are female bathrooms. Now the conference talks, it will be combination of in-person and Zoom talks. So unfortunately, some of the speakers couldn't come in person, so they will join by Zoom. The research talk will be 30 minutes divided into 25 and 5. And the review talks, we will have 3 of them. External review talks in the morning will be 45 minutes. All the talks will be streamed and later uploaded to the YouTube channel. Now, the welcome reception as well as the coffee breaks are in the floors above. So at the first floor and the second floor, it would be 2 floors. And yeah, so you just have to go up. And just a reminder that the welcome reception today, after the talks, is also combined with the poster session. Okay, we recommend that if you can, to wear a mask in this room to stay safe. And yeah, welcome to Prague again and have a great conference. Thank you.
I will invite now the representative of the Dean office, Zdeněk Doležal. It's not only Vice Dean, but he is also our colleague from the particle department, so it's my great pleasure to ask him to say a few words.
Thank you very much. I'm very honored to open this event and to see so many people, so many young people. I thank to my colleagues who dared to organize an event, which is not a trivial thing nowadays. Although I am working in the same department, I'm an experimentalist, so I will not pretend that I have any clue of what you will be talking about. There are other experts, of course. I would rather say a few words inspired by the venue and the place where we are now. We are in the historical center, or at the site of the historical center. This building was opened in 1929, and it witnessed several important events in our modern history. 1939, I would like to quote a few dates. 1939, it was in November, where we were already half a year under the German occupation. There was a peaceful rally commemorating our Independence Day in October, which was suppressed by Nazi police, and 2 people were shot and died. And one of them was a student of medicine of Charles University, Jan Opletal, and his funeral turned out to another rally which was brutally suppressed, and Czech universities were closed for 6 years. So there is a large gap in the history of our academia. 1948, again, a few hundred meters from here, the communist prime minister announced a successful coup which turned our country to a totalitarian regime for 40 years. It was interrupted by a breeze of freedom in 1968, so-called Prague Spring, but it also was interrupted and by the Russian army coming in, and there is a very bitter event in January 1969, where a student of this Faculty of Arts, Jan Palach, burned himself in an attempt to alert public awareness that the raising passivity is deathful. So this was unfortunately not successful, because then we fell back to the totalitarian regime for another 20 years. And It was a commemoration of 39 event. 50 years later, there was a student demonstration, 17th of November, which initiated so-called the Velvet Revolution, and since then we live in a free society. So these are things which happened very nearby and of course shaped our lives. And you will definitely have opportunities to see and to meet with these things. Anyway, I think you are here for the conference. You have a busy schedule, and I will not delay you further on. So I wish you a successful conference and good luck.
Thank you. And it's my pleasure to welcome first speaker. Let me introduce him, Nima Arkani-Hamed, from Institute in Princeton, please.
Thank you. Can I use this one?
Yeah,
or I have to use that one?
It's up to you.
All right. Well, it's really fantastic to be here. I'm going to be, this is I think the third Amplitudes meeting in a row that I've been speaking about the same broad topic. This time I'll be talking about it from a rather different point of view. This has been a sort of a project over the course of the pandemic together with Hadley Frost, Pierre Plamondon, Julia Salvatore, and Hugh Thomas. And I think after all this time, we more or less understand what's going on, so I can finally say that a paper will actually be appearing at some point this year. We're sort of contemplating writing. Now, I want to begin with the obligatory slide. That's been, some version of this slide has been the first slide of every talk I've given at every Amplitudes meeting ever. And I'm putting it up here for the epsilon fraction of you who have not seen it yet and aren't sick of it yet. So by next year, you can be like, there it goes again. I'm sick of it already, right? So I'm doing you a favor. The kind of moving question that those of us thinking along this particular line I've been pursuing for over a decade now, is thinking about scattering amplitudes from the perspective of finding a new question to which the amplitudes are the answer. So the sort of conventional question to which amplitudes are the answer, the amplitudes are measured by some experimentalists out at infinity, and we sort of integrate in, this is not, what happened? Okay, sorry, I reversed the order there. We sort of integrate in a kind of a standard picture of particles moving and crashing into each other as local interactions in space-time, and summing over all the possible ways these pictures could happen to be compatible with the picture of a unitary evolution of a wave function in Hilbert space. And we have, that picture is completely correct, but we have lots and lots of reasons to expect that there should be maybe a radically different way of thinking about what the amplitudes are. In this question, the actual observable is anchored at infinity and is labeled by on-shell kinematic data, one way or the other. Many ways of thinking about the on-shell kinematic data, but it's a function of things that we measure at infinity. And so this picture of stuff that we're putting on the inside of this black box, which does involve particles moving in and hitting each other and so on, that's like integrating in some auxiliary space that's not really there in the problem. It's there in our mind's eye as theorists to give us a rational accounting for the answer. And what we're looking for is a different thing to put in, which does not involve this auxiliary space. And somehow, if at all possible, to find a new question that's formulated directly in the kinematic space where the amplitudes live. A new kind of mathematical question, new physical ideas perhaps, that also give us the amplitudes as a result. And one of the motivations is that if we can get a better idea of what can do this trick, we'll begin to see how this something else can actually give rise to the properties of amplitudes that we ordinarily ascribe to the rules of space-time and quantum mechanics in the interior. And over the past 10, 12 years or so, there's an emerging picture that even though when you go to this sort of kinematic space at infinity, it seems like a dry, boring, arid space with not much going on, this kinematic space is, for example, just labeled by n on-shell momenta. That's it. What can you do in the space of n on-shell momenta? What kind of question can you ask in the space of n on-shell momenta whose answer is all the richness and complexity of amplitudes? Well, we're starting to see some set of ideas that begin with fundamentally combinatorial notions, geometric ones, analytic ones, and so on, which have this character. So some questions that we can ask in kinematic space whose answer gives us amplitudes in a totally different way. And the words are associated with ideas like amplituhedra, sosahedra, in the context of cosmological correlators, a very baby first step in this direction in the language of things called cosmological polytopes. And of course, the story is continuing, but what I find most exciting about this general set of ideas is that it's clearly related to the real world. It's clearly related to the real world we see when we look outside our windows, not toy models that we invent in order to have something to do with theorists. It's clearly have something to do with the world that's happening out there. And in some reasonable approximation, and exposes some hidden symmetries and fascinating new mathematical structures, many of which are even new to the mathematicians. I just love that it shows that there's some pure magic in physics that's really right under our noses. All right, so now let's get into the theory we're going to be talking about. We're going to be talking about the kind of simplest, totally non-supersymmetric theory of colored particles. So just colored scalars. So it's a trace phi cube theory. So phi is an n by n matrix. The basic interaction is this cubic interaction that we draw with the usual double line notation diagrams. And so here is some representative diagrams that contribute to the 4-particle amplitude. Tree level, 1 loop, 2 loop planar, the leading 2 loop non-planar corrections, and so on. Okay? So there's no supersymmetry in this story, there's no planarity in this story. Okay? So the only thing we have is color. Okay, and before I tell you anything about the formalism, so I've been speaking about this, as I said, for the past 3 amplitudes meetings. In the first meeting, we were just getting our feet wet and understanding of the kind of structure we should expect to see at loop level. Last year, we sort of more or less understood what the amplituhedron is for this theory, and we called those things surfacehedra. And so last year, it was all about these polytopes and their very interesting properties and all of that stuff. And one of the big motivations, I'll come back to this at the very end, one of the big motivations for undertaking this whole adventure for this theory was that we know that something important should be associated with the duals of these spaces, the duals of the amplituhedron. But we don't know what the dual of the amplituhedron is for literally n equals 4 super Yang-Mills. However, we should be able to know what the duals of polytopes are. So since we figured out the duals of these what these surfacehedra were, it made sense to try to figure out what the correct notion of dual should be for them. And that's essentially what we figured out how to do over the past year. And this now is associated with new formulas for the amplitudes. So really new formulas not for integrands like what we've normally been talking about in this business for a long time, but actually for amplitudes. And so before getting into any formulas or anything like that, I'm just going to flash this slide, and we'll come back and I'll tell you where these things come from. Here is just so we see on one slide is an expression for the actual amplitudes, all the tree amplitudes and all the one-loop amplitudes in this theory. And you see all the tree amplitudes are written as a single integral of one object. Clearly, there's nothing here that looks like Feynman diagrams or anything like that. There's a single object, and it's an integral over the unit n-4 sphere. Okay, n is the number of particles. The one-loop amplitude is some very similar-looking expression. It was an integral of the unit n-1 sphere. And the notable thing, you'll see it in more detail later. You might not recognize this structure here so much. Here, you see something that looks a little bit like the Schwinger or Feynman parametric representation of one-loop amplitudes. Maybe these alphas look a little bit familiar, like Schwinger parameters that you would see in one-loop calculations, except there's also parameters for all the sort of tree-level propagators that are there in the problem. This is the whole one-loop amplitude. This is the whole tree amplitude. But the sort of notable, so these are concrete integrals. You could put it on a computer, evaluate it numerically, and get an answer. Make a plot. Okay? So in whatever the region the integral converges, there's some region of Mandelstam invariance where the integral converges. It's a concrete integral, you can get a number out. And it depends on the external data, the momentum, and so on. But the really key thing is what is the dependence on these variables that we're integrating? See, these expressions that occur here are just linear. They look linear. They're just involved these things like tj plus tj minus 1, et cetera. But there's this interesting max in front of the whole thing. So the integrand here kind of looks like an integral over Schwinger parameters, except these things that are Schwinger parameters are actually almost linear functions of the variables that we're integrating over. And you see they're piecewise linear functions. Okay, so we'll come back to talk about where all this stuff comes from. We have the sort of concrete version of these formulas through to the two-loop non-planar, the one-loop double trace amplitudes beyond the planar limit, and the two-loop single-trace amplitudes also planar and the leading non-planar corrections. Okay, so, but in fact, that's just a matter of doing it. I'm going to tell you what the algorithm is for doing it at any order in the loop expansion. Okay, so now. So we're going to spend some time, remember the whole point here is to find a question in kinematic space whose answer is the amplitude. And so we're going to spend quite a bit of time thinking exactly precisely about what the kinematic space is. Okay, so that's going to be essentially the entire subject is going to flow from thinking quite precisely about how you should consider the kinematic space. So to begin with, the most basic connection is that if you draw even just the sort of color structure of the diagram, that the color structure of the diagram is associated with the triangulation of a surface. So this is the sort of most basic Tuftian connection for the genus expansion, except I want to stress an aspect of it. So first let's start with a simple example at tree level. So if I draw this double line notation diagram, I'm going to call them fat graphs from now on. Okay, so this fat graph for 5-point tree amplitude. Well, that you can think of dually as giving me a triangulation of the disk with 5 points on the outside. Okay, and why is it a triangulation of a disk? It's because you can just back up and say, what is a surface, period? What is the definition of an oriented surface? How, if you were blind and you couldn't see, how would someone tell you what surface they're talking about? Well, they would tell you how to triangulate the surface. And what is a triangulation? A triangle is a sequence of 3 edges. Okay, so every triangle is a sequence of 3 edges, and it's oriented. So you call them A, B, C, and they have to be read in a particular orientation. Now, a surface is someone hands you a zillion triangles, but there has to be a rule that every edge that occurs can occur in one of 2 orientations, first of all. And secondly, every edge either occurs once, ever, or it can occur at most twice, but if it occurs twice, it has to occur with opposite orientation. And that tells you how the triangles are glued to each other in the interior to produce a triangulation. That's just the very definition of an oriented surface. And those rules are 100% the same as the rules for building a Feynman diagram out of gluing together 3-point vertices. And the 3-point vertices really tell you the 3 edges of the triangle, and the ones that are glued together on the inside with opposite orientation are the propagators. Okay? So, I want to stress again, a single color diagram, normally when we talk about this, we use the language of drawing the diagrams on a surface, sort of imagining the surface is sitting there and we draw the diagrams on the surface. This is a very slightly nuanced distinction I'm trying to make. One diagram, and it's not a Feynman diagram, it's just a color diagram. It's a diagram that's sort of telling you the order in the 1 over n expansion that you're in. One diagram defines a surface, okay, by giving a triangulation. Okay, so we're going to now make a first attempt at talking about the kinematic space. This is the zeroth attempt at talking about the kinematic space. The most obvious way of talking about the kinematic space is to say I draw a surface, and the sort of propagators that I see in the Feynman diagrams are going to be associated with chords on the surface. So things that just might go between points on the outside. There might be sort of holes or punctures in the middle. We would see that, for example, at one loop. Okay, so the propagator is associated with chords on the surface. What are Feynman diagrams are just a maximal set of non-intersecting chords. So I should have called that chords on the surface. And a maximal set of non-intersecting chords gives me a triangulation. So here's an example of something that's there at 2 loops. Oops. The second loop is dropped on this side for some reason. Sorry about that. Where's my button going here? Oh, there it is. Okay. Oh, this thing ran out. Okay. So if I take this picture, it corresponds to this particular fact graph. Okay. Now, we can go on from here to talk about the momentum that we would associate with any propagator. Okay? And the momentum, or we're really going to have momentum squared, but the momentum associated with any propagator, I have to associate something with a curve, and the momenta are associated with homology. So you imagine that the boundary components are given momenta, P1, P2, P3, let's say in the case of the disk, and if you draw any other chord like x, we assign x, I mean, we're familiar with this from the sort of Wilson loop picture, but this is very slightly different. I'm saying that we're gonna, no matter how I draw this x, the momentum I associate with x is P1 plus P2 plus P3. Why? Because x is homologous as a curve to that boundary, okay? What about, here's an example of the annulus at one loop. This would be a contribution to double trace amplitudes at one loop. In this case, I have the momenta on the outside, but that doesn't completely specify the homology of the surface. Okay, there is this kind of line, for instance, from here to there, whose momentum is not determined by that of the boundary, simply because I can't deform this guy to the boundary. So there's another element in the basis for the homology of the surface, which I have to pick one of those lines. I can choose any one of them that I like, but let's say I choose this one and I call it L. That'll be a loop momentum in the diagram. And then all the other loop momenta I can unambiguously label now by homology. For example, this next one over would be L plus P2, because this curve is homologous to this one plus that one, and so on. This one down here would be L plus P2 plus P3 plus Q1 plus Q2, because they have to move along down there as well. Okay? So this is the first sort of informal way of talking about the, momenta. Now, immediately, there's an issue here, which was one of the first things that we had to deal with, and I talked about at some length in the first time I spoke about this, is there's something slightly funny that it looks like we have infinitely many curves. The moment we, the first non-planar case, when we have the annulus, let's say I look at this triangulation of the annulus, right? So that's a nice triangulation of the annulus. Now, take this picture and imagine just rotating the inside circle by 360 degrees, okay? Then all of these guys get wound up a little bit more, okay? So this is a more windy looking picture, but of course, if you look at it, they're still not intersecting each other. That's another triangulation of exactly the same surface. And in fact, those things correspond to exactly the same Feynman diagram, okay? Just as far as the color diagram goes, they're exactly the same. They both just correspond to this kind of diagram. But how are they different from each other? They're different in the momenta that are assigned to them. Because if in this diagram, let's say I assign this guy to have momentum L, okay, so this would give me some picture of that's L plus, and so on. Okay, I keep reading it off here. Then I told you that we can now assign momenta to everyone else consistently, so I can figure out who are the momenta that I would associate to this graph. And the graph that I get here is, in fact, the graph is exactly the same, but the labeling of the momenta is different. Okay? And the momenta in the new graph are just shifted compared to the old graph and translated by the sum of the momenta of the inside, which is equal to negative the sum of the momenta on the outside. Okay? Now, this is actually a good thing, because there's a sort of famous problem that people trying to think about loop integrands beyond the planar limit have dealt with, which is how do you label loop momenta consistently, graph to graph to graph? And this is the solution of that problem. Okay? However, the point is that what the challenge is, you want to label loop momentum in such a way, for example, that all the cuts work automatically. And if you try to do it in any finite way, to choose some sort of finite set of graphs and label the momenta, and even find a consistent way of routing them from diagram to diagram, for any finite set of graphs, there's always some sort of cut near the boundaries of the diagrams that you keep that don't match. So this picture tells you don't make any artificial choices. You have to look at all of them at the same time, okay? And we're going to do that. We're going to look at all of them at the same time. This infinity is related. Again, the fancy words, or this is the action of the mapping class group on the surface. The fact that I can take the inside and rotate it any number of times, of course, generalizes to any surface. And I'll talk at the end about how this issue is dealt with, okay? But for the moment, the natural thing to do is to just let it go and consider everyone together. We're not going to make any choices at the moment. Okay, so now we're going to talk about the kinematic space a little bit better, right? So this is going to be our proper picture of what the kinematic space is, so I'm going to do it slowly. In fact, in all the previous pictures, I was still drawing a picture of the surface, right, and drawing the curves. You have to imagine about homology, what the curves look like. Again, the idea is, how would you do it if you couldn't see? Okay, how would you do it absolutely algorithmically if you couldn't see? And so everything we're doing from now on is going to be done at the level of the single fact graph that defines the triangulation of the surface. Okay, so I'm never going to look, I'll draw it for some intuition now and then, but everything is going to be done at the level of that single fact graph that defines the surface. So, the first point. So you draw this fact graph. Remember we said that the variables should be the chords on the graph. Well, if you only have the fact graph, how could you possibly draw that? Well, obviously, it should just be some kind of trip through the fact graph. Okay, so you just imagine taking a walk through the fact graph. There's only one rule: there should be no U-turns in this walk. Okay? So as you walk around, if you walk down some road, you're not allowed to turn around and walk back. You have to walk to the next intersection, and then you can either take a left or a right at the next intersection, but you can't double back on yourself. Okay? So they are trips through the fact graph with no U-turns. Now, if you think about what this looks like sort of back on the surface, this is not exactly what I was calling before a chord. So here, let's say I look at this path. This path is what I would call very close to what I would call before a 2-5. So 2-5 before I would draw a chord that joins 2 and 5. But see, this is not really going from the point 2 to the point 5. I don't really have the point 2 and the point 5 in this picture. It's going from somewhere to the right of 2 to somewhere to the right of 5. Okay, so it's starting somewhere here on the road between 2 and 3 and ending somewhere there on the road between 5 and 1. Now, if you want to think about it intuitively in the language of the surface, this is called a lamination, and we'll call it a curve from now on, so I don't use that big word, okay? But you imagine starting with a chord, but you want to push the endpoints away from the sort of marked points on the boundary, and you can push the endpoints away in a consistent way because the surface is oriented. So, okay, I'm just all going to push the endpoints in the direction on the boundaries that's defined by the orientation of the surface. So in this case, I push them a little bit to the right of 2 and a little bit to the right of 5. Okay, so this lamination on the surface is something very natural from the perspective of the fact graph. It's just this sort of trip without any U-turns in the fact graph. So let's do a couple of other examples. Okay, so here's something a little interesting that we see at one loop in the planar one loop case. Okay? In the planar one loop case, let's say I want to talk about what you would think of as a kind of a loop variable. That would be something that goes from, let's say, 2 to this sort of marked puncture point in the middle. That made sense when I was drawing a chord that could go from sort of marked point to marked point. But now I'm not allowed to go from marked point to marked point. So if I start here, there's nowhere for it to go there. So the only thing that makes sense to do is to sort of head there, but just kind of spiral around forever. Okay, so that's maybe slightly funny. But it also sort of makes sense on the fact graph. You know, I want to go around, and it sort of, here I can sort of go around and around. It doesn't make sense to stop anywhere. There's no place to stop. So I just have to spiral around forever in that direction. I can also talk about spiraling around the other way. It will turn out we only ever need to talk about spiraling one way. Okay, so by convention, we talk about spiraling counterclockwise. If it's at the end of your path, and if you're spiraling at the beginning of your path, you spiral clockwise. Okay? And okay, here's another example of something that would be there for the annuals. Again, a double trace diagram where it would look like this nice blue curve on the surface here, lamination, and it's this particular sort of trip through the graph. See, now in this case here, there was no place to stop. Here, there's an off-ramp, so I could go around once, I could go around 10 times, and then exit at A if I like. Here, I'm not forced to spiral around forever. Okay? But in these cases where on the surface it just looks like a puncture, there's this spiraling. All right, so that's now what the variables are. Now, how do I assign momenta? So I said on the surface it's a question of homology, blah, blah, blah. But again, we're going to do everything purely in terms of the fact graph. Okay, so here's the rule. It's kind of obvious what you want to do. If you imagine what the momentum, even at tree level, what was the momentum before? We draw this loop, and it's the sum of the momenta on the left, or negative the sum of the momenta on the right. So you have to sort of put in an asymmetry of the guys on the left or the guys on the right. And you can do it consistently purely in terms of this trip by saying that the momentum that you would assign to any curve is you take the momentum where it starts, and then you follow the curve, and everywhere you make a right turn, you're going right. That means there's a road coming into you from the left, so you add the momentum that was coming into you from the left. If you're making a left turn, you do nothing. Okay? So that's the rule, and it assigns a momentum to the curve. And okay, let's see how it works in sort of obvious examples. For example, here, the momentum, there's P2 when you start. At this first turn here, it's a left turn, so you do nothing. But at the next turn here, it's a right turn, so I add P3. Okay, so and indeed, the momentum associated with this guy is P2 plus P3. Okay? And here, in the loop case, it's a little more interesting. Let's say I want to talk about the momentum I'm supposed to assign to this sort of spiraling curve. Remember, this is supposed to correspond to the loop variable. So what would it be in this case? Here at P, I start with P3 at the start. I'd immediately make a right turn, and incoming here is the momentum L plus P4, so I add L plus P4. But then forevermore, I make left turns after that as I spiral around. And so I add nothing. Right? So the fact that I'm spiraling around more and more and more doesn't make any difference to this momentum that I would assign. And indeed, that's exactly the momentum that you would associate with that curve. All right, so now we're done. We've defined our kinematic space. We've defined the labels for the kinematic space. There are trips on this fact graph, and we've given a rule for assigning momenta, or momentas, which we can square to give us sort of propagators associated with the fact graph. So now we have our arena, and so we have now our challenge. In this arena, we want to find a question whose answer is going to give us the amplitude, blah, blah, blah. Okay? And to begin with, the most basic version of this question is, why should we, it has to do with the most basic features of local space-time processes and quantum mechanics. Why should we look at Feynman diagrams? Why do we care about Feynman diagrams at all? Right? Remember, the one diagram that we're beginning with doesn't even have momenta in it. It's just a color diagram that tells us how the color indices are all connected. Why do we care about all the other diagrams? Who cares about all these other diagrams? That's one question. Second question, why should we add them all up together, sort of coherently? So why do space-time processes matter is question one. Question, why should we add them all up together? So why does quantum mechanics matter? And really, very beautifully, the answer to this question is just lying in plain sight when we think even slightly more concretely than we have so far about what the labels of these variables are in our kinematic space. So I've still described it not precisely enough. When we describe it precisely, the answer to this question is essentially going to fall into our laps. And it's going to give us a new, of course, much more efficient way of computing amplitudes. I showed you examples of some of them, but with no reference to the diagrams at all, that exposes some of the hidden symmetries that we've talked about in previous meetings. This picture, which is fundamentally about particles, and the sort of 2D surface is just there about the combinatorics of a single Feynman diagram labeling the surface, also hands us the generalization from particles to strings in a very, very simple and interesting way. So we're going to go from this picture and just thinking about labeling the kinematics of particles to a way of representing string amplitudes that we've checked, actually matches string amplitudes through one loop for the bosonic string. I'll say more precisely what I mean by that and why there's quotation marks around those strings, but with no reference to a worldsheet CFT, vertex operators, anything like that. And as we'll see, there's a fundamentally combinatorial description of particles and strings from this point of view. And there are many interrelated views of these ideas, many of which I've spoken about in the previous talks. So the words are tropical, fans, tropical geometry, surfacedra, what we call binary geometries, relations to hyperbolic geometry. These things are all interconnected to each other. But I think what at least I've become increasingly convinced of, I mean, we've known about this connection for a while, but we've been making it simpler and simpler as things have been going on so that I can finally talk about it. I've sort of threatened to talk about it, but I've never talked about it before. So I'm going to try to go to the end of the story now and talk about it. What seems to lie underneath all of this is a certain counting problem in kinematic space. Okay, so there's a very simple sort of counting problem associated with the way we'll characterize. Now, where this counting problem comes from has to do with some sort of somewhat more abstract things that involve thinking about quivers and representations of quivers and the categories of representations of quivers. But you're going to have to know nothing about those subjects. Okay? So everything that I'm going to be talking about from here on in, you would have been able to understand in grade 10. Okay? So there's really nothing fancy going on. However, at one point, I'm going to introduce an object. I'm going to introduce a counting problem, and you're not going to know why that counting. It's a very nice counting problem, but I'm not going to be able to explain to you why you care about that counting problem. If you want to know where that counting problem comes from, that's what's related to thinking about categories of quiver representations and so on. And of course, this more abstract point of view is more powerful because it actually tells you how to do exactly the same things for a much wider setting of objects that have nothing to do with surfaces. Okay, so what I'm telling you about today will have something directly to do with surfaces directly for the structure that we care about. Okay? But this is the last time I'm going to say the word category here. Everything from here on in is going to be very elementary. Okay, but let's begin with the first part of this subject, which is just labeling the variables even more explicitly. So remember, we say that the curves are just some trips in the surface. So how would I specify a trip on the surface? Okay, let's just keep on going. How would I tell someone how to take some particular trip? Well, I would turn on Google Navigate and ask Google Navigate to tell me what the trip is. So let's say, how would I describe this trip? So what I've done here is take our old friend that we talked about before, and I've just labeled every road here in some reasonable way according to the guys that surround it. That's just for convenience. I could label them any way I want, obviously A, B, C, D, E, F, G, but I've labeled them so that this here is a road 1, 2. It's between regions 1 and 2. Road 2, 3. Road 3, 4, 4, 5, 5, 1. This intermediate road is road 1, 3. This intermediate road is road 1, 4. Obviously, the road names are exactly the sort of chords of the triangulation. Okay, so that's not surprising. All right, but now if I want to tell you that you took this trip, then what would Google Navigate tell you? Say you started the road 2, 3, and then when you hit the first intersection, you make a left onto the road 1, 3. And when you hit the next intersection, you make a right on the road 1, 4, and at the next intersection, you make a right on the road 5, 1. Right? Now, instead of saying left and right, I'm going to draw those as up and down. Okay, so left is up and right is down. Right? So this trip corresponds to this picture. So it's a word. 2, 3 left, 1, 3 right, 1, 4 right, 5, 1. Every trip is a word. The fact that you can't double back just means that, well, that you don't have a left, you don't have a left follow. You don't have a left right. Okay, so that's why it's all consistent. Everywhere you either go left or you go right. There's no U-turns. Okay, and I'm recording here the words for every possible trip here. Okay, so there are some trips that correspond to just going from boundary to boundary. So here's a trip 1, 2, is I start from 1, 2, and I just immediately make a left turn to 2, 3. There's a trip 2, 3, I start from 2, 3, I make a left onto 1, 3, left onto 3, 4, and so on. See, all the boundary guys just go in one direction. I'm just sort of going left, all right? The interior guys are a little more interesting. So here's the road 1, 3, is I start at 1, 2, I make a right on 1, 3, I make a left on 3, 4, okay? And I've denoted all the rest of them as well. Okay, so just pause here and I'll just take a second. Everything we're doing from now on is going to be something to do with these words. Nothing else, okay? Everything is going to be an operation we do on this word, curve by curve. Okay, we're never going to talk about many curves together. Everything we're doing from now on will be about one curve at a time, one word at a time. Okay, so now, even before thinking about all the information in that word, there's a slightly coarser way you can think about this word, which is something called the geometric vector associated with the curve. What is a geometric vector? It just records which one of the roads that you hit along your trip and how many times did you hit it. Okay, so it's literally, you know, if I go to 2, 4, I would have a space. Here I have sort of 7 roads in my problem, the 5 boundary roads and 1, 3 and 1, 4. So I have a sort of 7-dimensional space. And so the geometric vector associated with 2, 4 would just be 1 in the entries 2, 3, 1, 3, 1, 4, and 4, 5, and 0 in the other entries. If I had a more complicated curve that visited some road many times and so on, it would have bigger integers. But every curve is associated with a geometric vector like this, okay? It seems like super boring. And if I look at the collection of all the curves, well, I just have a whole bunch of vectors, right? I have a whole bunch of vectors, and they're all pointed, they all have positive coefficients, so they're all on the same side of some plane, they're all positive, they're all in the positive orthant, okay? All right, so nothing exciting is happening yet. One thing that we can do, so this is a 7-dimensional space. I can characterize all the words. For example, I can choose a nice basis for the 7-dimensional space. I will choose the basis associated with the words for the obvious guys, like 1, 3, 2, 4. Sorry, 1, 3, and 1, 4, I should have done. That should be 1, 4, as well as the 1, 2, 2, 3, 4, 4, 5, 5, 1. So that's my 7-dimensional basis, and I can express all the other words as a linear combination of these ones, and I'll spare you the algebra, the trivial algebra. This is what the answer ends up being, okay? So every geometric vector is a linear combination of this in the 7-dimensional basis. But now we're gonna do something a little interesting. We're gonna go on shell. What do I mean by going on shell? You see, in this picture, we've treated all of the curves on an equal footing, the boundary guys as well as the internal guys. But the boundary guys are not actually kinematic variables that are free to move. The boundary guys are exactly nailed by the on-shell condition, p squared equals m squared. So we shouldn't treat them on the same footing, right? They can't actually vary. The ones that vary are the internal curves. So how can we go on shell from this viewpoint? What we do is we simply project this 7-dimensional picture in the direction of every one of the geometric vectors associated with the boundaries. So you literally imagine you take this picture and you just look at it in the direction of every one of the 5 curves that correspond to the boundaries. When you do that, of course, by definition, all of those guys get projected to the origin. So that's how I get rid of them. I get rid of them simply by projecting through them. I'm now left with a 2-dimensional space, right? I had a 7-dimensional space to begin with. I projected through the 5 boundary guys to quote-unquote go on shell, and I'm left with a 2-dimensional space. And now this 2-dimensional space does look interesting. Okay? The 7-dimensional space looked boring, the 2-dimensional space looks interesting. And what I'm going to do is simply look at, so let's say I take 1, 3 and 1, 4 after I do this projection, then the remaining 3 vectors are going to be a linear combination of 1, 3 and 1, 4. And I can read off the linear combination just from this formula upstairs. Remember, 2, 4 was 1, 4 minus 1, 3 plus this thing in the direction of the boundary. Well, after I project, the thing that's in the boundary has gone to 0. So all those things in red that are the boundaries are gone to 0. And so I have a new formula that says G24 is now just 1, 4 minus 1, 3. I just lop off the red guy. 2, 5 is minus 1, 3. 3, 5 is minus 1, 4. Okay, now I gave you the sort of rationale for what we did, starting from this very naive natural notion of the geometric vector and then going on shell. But already from this example, you can see the pattern of how you can read off what this final vector is purely from the word. You don't have to do any of this work. How do you read it off purely from the word? Well, you look at the word. Everywhere there's a valley in the word, you pick that road with a plus sign. Everywhere there's a peak, you pick it with a minus sign. Okay, so for instance, if we look at the road 1, 3, it was 1, 2, down 1, 3, up 1, 4. And so it has a valley at 1, 3, so and these guys are called G vectors, not geometric vectors. its G vector is just 1, 3. Good, that was one of, this guy is only a value is 1, 4, but 2, 3 went up and down, and so this guy is minus 1, 3 plus 1, 4. This guy's minus 1, 3, that guy's minus 1, 4. And I've now saved you the work. For any word, you can immediately write down what these G vectors are just by looking at the peaks and valleys of the word. Okay? But what's the point of doing this? Because now something remarkable happens. Let's look at this picture. So here was the G vector. I've drawn it for 1, 3 and 1, 4. This was a G vector for 2, 4 was minus 1, 3 plus 1, 4. For 2, 5 was minus 1, 3. For 3, 5 is minus 1, 4. So I've just drawn the 5 G vectors. The first thing that you see is that these 5 vectors actually cover the whole plane. That was not true before, right? The geometric vectors were all pointed. They lived in this positive orthant. After the projection, they cover the whole plane. But a little more interestingly, how do they cover the plane? They break the plane up into little cones, right? Who is this little cone? This little cone is bounded by 1, 3 and 1, 4. Well, who is 1, 3 and 1, 4? Well, that's a triangulation. Okay? This is a Feynman diagram. This is 2, 4 and 1, 4. That's also a Feynman diagram. That's a Feynman diagram. That's a Feynman diagram. That's a Feynman diagram. Okay? We didn't ask for Feynman diagrams. We didn't ask to have maximal set of chords that are non-intersecting. We didn't ask for any of that. We were just labeling the curves and then going on shell. But amazingly, after you do this, you find that the set of vectors that are left have the property that they tile all of space, and the cones that tile all of space are precisely the things that come together as Feynman diagrams. Okay? Mutually compatible, mutually non-intersecting chords that give you curves that give you Feynman diagrams. So this is quite remarkable. The cones are triangulations or Feynman diagrams. They completely cover the entire space. So that's why you say you have to consider all of them together. You can't take any of them apart. Only when you consider all of them together do they tile the entire space. So we see why we care about space-time processes and why we care about all space-time processes are generated just from this simple picture. Here is just another example, so you see how it works. So I'm going to now look at this bubble diagram with this triangulation. I'm just drawing the top pictures just so you have just a picture of what it looks like on the surface, but again, we can do everything just from the fact graph. So this diagram that corresponds to a sort of a tadpole propagator is this word, is this trip, and is this word. Okay? This one, which is a loop, which have spiraling counterclockwise, looks like that guy. This is a loop spiraling the other way. Okay, it looks the other way. You notice when you have spirals, this goes down and up, down and then up, but then it just keeps going up forever. So despite the fact that it's, again, going on forever, it doesn't change the fact that its geometric vector is just A, because there's still just one valley. Okay? And here there's just one peak. So there's nothing infinite going on with the actual G vectors. Okay, so I drew these ones. If I do the other ones starting from 2, I just reverse B and A in this picture. And so once again, I can draw all of them. And once again, all of them now give me 6 vectors. And these 6 vectors break up the plane into 6 pieces. And let's look at the guys on this side. So this was 1 plus, 2 plus, 2, 2. And I didn't label the other one 1, 1. And these are exactly these 3 diagrams. The ones on the other side are exactly the same diagrams. They just involve the opposite spiraling. But the picture is simply reflected across this symmetry plane. So in fact, all you need is one side of this picture. Okay, but if you didn't do it, if you just take every curve in sight, you do get something that tiles the entire plane. Once again, I didn't ask for it to sum all the one-loop Feynman diagrams for this little problem. It just does it. It just breaks the space up into pieces, and it just does it. Okay. Now let me tell you some generalities about these about fans. In general, these fans are infinite because we have infinitely many variables. Okay, so here's an example for the annulus, the simplest case with 2 marked points. And if you just draw the G vectors, you see as you go around more and more and more, they get longer and longer and longer. Each one of these triangles is a Feynman diagram. In fact, in this case, there's just one Feynman diagram. So they're all exactly the same looking Feynman diagram, just with their momenta shifted, as I explained before. Okay, so every diagram is the same one as before, just with the definition of loop momentum shifted from one diagram to the next. But it's also the case that they don't quite cover the entire space. because they asymptote to this guy in the direction, in this direction, minus 1, 1. And that's, in general, the case. They cover almost the entire space, except for some lower dimensional regions that are not covered. And those lower dimensional regions have a purpose in life. Those lower dimensional regions are associated with closed curves on the surface. Okay, so if you add, we didn't talk about closed curves on the surface because we didn't need them, apparently, for the trace phi cube theory that we're talking about. But the closed curves are there on the surface. I talked about it at a previous Amplitudes meeting, so that won't be the focus today. But this is gravity. This is the sort of geometric combinatorial avatar of the inevitability of closed strings in open string theory. Is that even if you didn't want it, the fan tells you it's missing something. And the things that are missing are associated with curves on the surface that you do not associate it with colored particles, but with uncolored ones. Okay? Anyway, that's all I'll say about it here. Another qualitative thing is that this picture tells you that you shouldn't think of all the diagrams as just individual things, that you add this and you add that and you add that. There are some diagrams that are close to each other, far from each other, they touch each other, they're tiling the space in some way. And the fact that they're tiling the space is associated with a hidden symmetry that what we called in previous years the scattering form has. Okay, so I won't say more about this in detail other than for those of you who might remember that there is a claim that these scattering forms have something called a projective invariance, which is a loose analog for this dumb trace phi cube theory of dual conformal symmetry for n equals 4 super Yang-Mills. But this picture now tells you precisely how to weight each one of these d logs with signs in order to make it projectively invariant. Okay, anyway, there's a few more things I'll say, but I'll skip that. Okay, so we have our first 5 minutes. I have 5 minutes? Okay. All right, okay, very good. I had no idea I had 5 minutes. Okay, fine. Okay, so let me say something that we can, that this picture of the fan tells us that we will be able to do. And to do that, I'm going to motivate something. I'm going to give you a reminder on Schwinger parametrization. So let's say we have a single graph. We know that we can Schwinger parametrize this single graph. That allows us to do the loop integration as a Gaussian integral. And the result is given as a sort of famous integral involving the semantic polynomials of the graph. Okay, so that's fine, but you might wonder, can I put all the diagrams together, add them all up together? Each one of them is just an integral of the same dimensionality, but can I add them all up together? And clearly there's no reasonable way to add them all up together. There's no way to line up what you mean by the variables in one integral and the other. Okay, so it's sort of stupid to just manually add them all up together under one giant integrand. But the fact that there's a fan actually motivates a way to give a unified picture of Schwinger parameterization. Okay? And the idea is just the following. So imagine, and actually I can even motivate thinking about this by going back for a second. In the simplest 5-point tree case, we could sort of see manually that the space was divided into these cones, that each cone was a diagram. Already, if we imagine going to 3 dimensions, this picture of the g-vectors just gives me a bunch of rays. And I told you that it's true that if you group these rays together into cones corresponding to the diagrams, that they don't overlap and they tile the whole space. But they don't come out that way. I mean, you would have to then still want to look and see that you want to group them together in a cone because they correspond to a Feynman diagram. It's still not telling you that you have to make them as diagrams. It's sort of your desire to, you notice that if you make them as diagrams, then you get cones that don't overlap and tile the whole space. What you really want is something that would tell you, let's say you pick up some ray in this space, which diagram is it in? That would be great to know, right? You just pick some random ray in the space. Which diagram is it in? What you want is sort of some function such that, or some set of functions, a function associated with every ray, such that if you're in some place in the space, the function would be non-zero if you're in a cone that has that ray and is 0 otherwise. Or if I say it the most extremely, what I want to have is some function I'll call u sub x t. The t upstairs is meant to signify tropical, but we'll come back to that in a little bit. What I would like to have is some function u sub t such that this function is piecewise linear on all of these cones. Okay, so it's going to be linear in each cone separately, but not globally linear. But it needs to have the property that if you evaluate this ux on the g vector in the direction y, it's equal to 1 if x equals y and 0 otherwise. If such a function existed, then it would do exactly what you want, right? Then you just evaluate it. If you like pick a random point, you would just evaluate these u's on every variable, and it would tell you which cone you're in, right? Because it would be 0 for every one other than the variables that come together in a cone. So that's just a nice motivation for thinking about these guys, period. But also, if you have these guys, they would give you a unified Schwinger parameterization for the entire amplitude. And what is it? You would just take the product, there's a propagator piece of x squared associated with every x. I just take the product of all these e to the x ux. Well, the x has units, so I'd put some alpha prime there to make up the units, but the alpha prime is going to drop out here entirely. So there's an alpha prime squared out in front that makes the units work out. Okay? That's it. Okay, so then I would just put all these guys together, now integrate over the whole T space, all of T space. But the whole point is that these u's are such that even though there's a u for every single variable, in this region, the only ones that are non-zero are for 1, 3, and 1, 4. In this region, the only ones that are non-zero for 1, 4, and 2, 4. In every region, they're linear, and the linearity means that in each region, this integral is exactly giving you the Schwinger parameterization for that cone. Okay? So that's the sort of point. If you can find this function that piecewise linear and lights up one ray at a time, then that thing gives you a unified Schwinger parameters for the whole space. All right. And in fact, even if we don't know how to do that ahead of time, if we just pretend that such a function exists, we can give a formula for any surface. Essentially, what I'm doing here is just the Gaussian integral that's associated with this unified Schwinger formula. Okay, so if I just plonk down every single variable raised to the power of its propagator, I can still do the Gaussian integral. And now I get a formula for the amplitude as an integral over all these t parameters, and it's exactly the same form as I had before. I can now, as usual in Schwinger parameterization, I can do the integral over the overall scale here and go from an n-dimensional integral to an n-1 dimensional integral that's been projectivized. In this case, to just live on the n-1 sphere. And I have these polynomials, u and f, these, which are now not associated with the graph, but associated with the surface. And there's another little thing that I've put here, which is modded by mapping class group, because we had that funny thing that we counted the diagrams infinitely many times, but that's simply the fact that there's now a symmetry that this integral has. There's a transformation, which is again piecewise linear on T space, that just leaves the whole thing invariant, and that gives me a spurious infinity. Okay, so I should just divide out by that symmetry group. I should mod out by the mapping class group. And when I do that, I'm done. Now I have a finite integral. So that's why it was a good idea not to worry about labeling the integrals and stuff like that until the end. Okay, we're just going to do this modding out at the very end. Now these u and f's we call surface semantic polynomials. There's a concrete formula for them. Given that I'm going to be killed momentarily, I won't talk about it. But essentially associated with any surface, for every homology equivalence class of curves x, you assign a Schwinger parameter alpha x. And I won't describe this in any detail, but there's a polynomial that looks very much like the ordinary u and f polynomials, semantic polynomials, except now not just for one graph, but associated with the entire surface. Okay? All right, so if we could find these variables that light up one ray at a time, we're done. The problem is that naively finding these variables is just as hard as enumerating all the Feynman diagrams. Okay? After all, you want to figure out, if you're given an array, which cone you're in. Well, let's say I just gave you a random picture of a fan with a bunch of cones. I can draw any random picture like that as I want. If you want to figure out which cone you're in, presumably you've got to figure out what all the cones are. And then look around to see where you are and which one you landed in. So if we had a random fan, this problem is just as complicated as enumerating all the Feynman diagrams. So even though you can find a unified presentation of the whole thing, doesn't matter. It's no easier than actually finding all of the diagrams. However, we don't have a generic fan. We have a very, very special one. And I'm now going to give you a formula for these u of x's directly associated with a counting problem for that word. So I'm never, again, for given a word, I'm going to just give you a formula for this magic variable. Can I have another 5 minutes? All right, good. All right, I will, it won't be, okay. We'll fight again in 5 minutes. So, so here is the new beef here, okay? So what I'm going to do with any word, there's the following counting problem. And this has nothing to do with surfaces or anything. Any word, pick a random mountainscape of word, up, down, well, pick a random mountainscape. I just draw a random one, A, B, C, D, F, G, all right? I'm going to make a generating function associated with this word that I like to call the relationships with baggage generating function. It's like, you know, when you first meet someone or you start dating them or something, you're not just dating them, but you're dating everyone that they've ever dated, right? So the idea here is that I'm going to pick any of these guys that I want, and I just write them down as I pick them. But the rule is that if I pick anybody, I also have to pick everyone that's in their past light cone. So you imagine this is a picture where the up and down is just giving me a light cone. You have to take everyone in their past light cone. Right, so let's just do some examples. So if you just have one guy, you can pick nobody, that's 1, or you can pick A. So this F polynomial associated with just this tiniest word is 1 plus A. What about this one? A up B. Well, I can pick nobody, that's 1. I can pick A, that's A. I can pick B, but if I pick B, I also have to pick A. So this guy's F polynomial is 1 plus A plus BA. This guy is, I can pick A, nothing, A, or D. I can pick A and D. I can pick B, but if I pick B, I also have to pick A. There it is. I can pick B, and also A and D. There's that. Or I can pick C, but if I pick C, I've got to pick everybody in its past light cone, including A, B, and D. All right? So that's the relationships with baggage generating function. And it's called the F polynomial of the word. Now, very nicely, very trivially, this is sort of a problem that, math nerds solve in their sleep in grade 10. There is a generating function for these. There's a very simple way to build a recursion formula that gives an explicit formula for this F polynomial. The reason is, imagine your word, whatever it is, if you start at the left somewhere, it's either going to go up or down. So you either will or won't include this variable in your choices. So I'm going to write this sort of F as either I do include it or I don't include it. But then there's a very simple recursion for if I do include it or I don't include it. For example, if y goes up, if I do include it and y is down here, then I'm including it, so I multiply by y, and I'm free to either include or not include the next one, because the next ones are above it. So it's y times little f yes for this blob plus y times little f no. On the other hand, if I don't include this guy, then I certainly can't include that one, because if I include that one, I'd be forced to include this one. So f no is just little f no. So this is a little 2x2 matrix multiplied by f yes and f no. And I'll call this the going left matrix that depends on y. And there's similarly a going down matrix that depends on y. And so the whole F polynomial, I just make a matrix for the whole word, just multiplying by left or right, up or down for everything. There's an up for the very last word. You just multiply all these guys out. That's a certain 2x2 matrix. That gives me f yes, f no. Then I have to add them together. And the final answer is just the b plus d components of this 2x2 matrix. So this is totally concrete. You give me a word. I multiply these 2x2 matrices, and I find the corresponding F polynomial. All right. But now these F polynomials satisfy some interesting and sort of obvious identities. You see, that's great, but I have to multiply 2x2 matrices as I go. You might want an even more sort of practical way to recursively determine the actual polynomial, right, instead of multiplying these matrices out. And there's an obvious sort of identity that you expect that they satisfy. So let's say I have a sort of a big word that looks like that. Then I can have, imagine that I group this word into a piece X, an overlapping piece Y. So there's X union Y, X intersect Y, and X and Y separately. And a little bit of thought makes it obvious from the counting problem that there's a relation that looks like the F polynomial for X multiplied by the F polynomial for Y would actually equal the F polynomial for X union Y times the F polynomial for X intersect Y if any one of the Y's in this intersection was set to 0. Okay? So that's really a simple thing that you can see just from the counting problem. So that there's a relationship of this sort, that the difference between these two things is the product of all the y's and the overlap multiplied by some polynomial in y. But in general, this polynomial is not a simple polynomial to write down. However, there's a case where it is simple. I mean, why is it not simple? Because, you know, it would depend on what's going on here to the left in some complicated way, or the right in some complicated way. But you can clearly make some simple prediction if what's going on to the left and the right is just going all the way up or all the way down. Right? And so in these particular cases, if you have a word that looks like this, then in this case we can make a prediction like this. And they differ now just by a very simple factor, which is the product of all the y's in this overlap. Right? So the product of these two guys is equal to the product of these two guys plus something very simple. And you see it's always bigger. If it looks like this instead, the product of these two things is the product of these two things minus the product of all the y's in that piece, so it's always smaller. And why do I focus on these kind of words? Because in fact, every word looks like this. See, it's really nice. Every word starts at one end and ends at the other and either goes up or down. So every word either goes up or down and it comes down to something and it goes up for the first time, and then from the other end it comes up or down and it goes the other way for the first time. Every word actually looks like this, except for just two exceptional cases, which are the really trivial ones, where the word either goes all the way down and then up, or all the way up and then down. Okay, so every word either looks like one of this or that, or it's upside down and left-right inversions, or it either comes, or it looks like this, or it looks like that. So for every word, there is a natural identity associated with every word that actually involves 4 friend words of it, okay, in exactly the way we've seen in this picture. And that means that with every word, we can naturally associate a variable that's less than 1, okay? Because every one of these is giving me an identity where one product is equal to the other product, either plus something or minus something. And so there's a variable that sort of measures how close the word is to being split, okay? And so that's a natural object to write down. And I just take the ratio here of whichever side is bigger goes downstairs. And that defines what we call the u variables associated with the word. And here's the complete list for what all the variables are for every conceivable word that you can make, including the 2 exceptional cases. I stress here this is something you do with every word individually. You can just build this interesting variable. And now we're done. Okay? From now on, everything is exposition, which I'm not going to make. But let me tell you some features of these words. Firstly, these words satisfy the following, these u variables satisfy the following remarkable relation that I've talked about at other meetings before. If I take the u variable for x and I add plus the product of every other curve of the u variable for y to the power of the number of times the curves x and y intersect on the surface, that's equal to 1. And this is what we've been calling for a number of years binary geometries. What's important about this, so it's highly non-obvious that these equations have a consistent set of solutions. If you just begin with these equations, it's not at all obvious that they have a consistent set of solutions. But this picture of thinking about the F polynomials associated with the words gives us these u's, and you can discover that they satisfy these relations. And what's wonderful about these relations, if we ask that all the u's are positive, that it also tells us that if the u variable for any curve goes to 0, by this equation, they all have to be between 0 and 1, by this equation, the u variable for all the incompatible curves must go to 1. Okay? So that's the magical thing about this binary geometry. And you can try to solve these u. In fact, in a sense, the whole story can start from these equations. This is the sort of maybe most invariant way of talking about things, but it's not at all obvious these equations have solutions. You can try to solve them directly. There's various ways of solving them directly in terms of infinite products. There's a solution for these that involves ideas from hyperbolic geometry. And this is what connects to string theory in the world sheet, although I won't have time to talk about it. But what I've also shown here is that it's also even more primitively associated with this particular counting problem. And so for instance, if we, okay, and how is this thing related to the object that we wanted that lights up one ray at a time? Well, all of these are functions of the variables that I associate with all the nodes of this word. I'm just calling them y. So these u's are ratios of polynomials in y. The y's we want to be imagine are positive, so I can always, since they're positive, I can write them as e to the minus t, and the t now goes from minus infinity to infinity. And now there's a natural question to ask what happens as we go to infinity in the t-plane. As we go to infinity in the t-plane, this thing is made out of lots of monomials upstairs and downstairs, but only some of them will dominate as we go to infinity. And this sort of nonlinear ratio of polynomials turns into something that's piecewise linear, the exponential of something that's piecewise linear that's defined to be the tropicalization of the corresponding ratio of polynomials. Okay, so given these words, I can also take this limit and find their tropicalization, and the variables are exactly what we wanted before. These are exactly the variables that light up one ray at a time. So for instance, if we go back to our 5.3 example, I won't go through it in detail, but I'm just using the rules that I defined. So I'm not thinking anymore, I'm just using the rules that I defined. And for every single word here, I have its corresponding u variable. There they are. And I can now check that they satisfy those equations that I told you. Very nice. And I can take this tropical limit. So for instance, if I take this polynomial, I write y as e to the minus t, and I go to t goes to infinity, then as you go to infinity, either one will dominate, this will dominate, or that will dominate. And so it's the exponential of the max of 0, which would be if 1 dominates, minus t14, which would be if y14 dominates, or minus t14 minus t13, which would be if this term dominates. Okay, and so from here I can just read off what these ux's are. So if I take this polynomial, for example, if I look at the second factor, what does it turn into as I go to infinity? Well, from this factor I would get minus t14. From this factor I get the max of 0 and minus t13. This guy's downstairs, so it's minus the max of 0, minus t14, and minus t14 minus t13. Okay, so from every word I get this sort of piecewise linear expression. And then you can just go and marvel at the fact that if you now look at what these things look like back in that fan, those u's are precisely, they satisfy exactly what we wanted, that the ux on gy is delta xy. So for instance, in this little cone, only 1, 3, and 1, 4 are non-zero, the rest of them are 0, and so on. Okay? So that's what gives us our picture of the unified Schwinger parameterization. And in general, at tree level, at trees for general n, the point is these words are incredibly simple, right? So this is what all the words look like at tree level. If I start with this very simple triangulation, they're all things that either that go in just in one direction. The only f polynomials that we ever see are of this form, of simply just a staircase that goes up. And so the corresponding function is just a max of 0, minus tj plus 1, and so on. Those are exactly the kind of expressions that you saw in that one-loop formula, in the tree and one-loop formulas that I showed you a while ago. But what's the point? The number of these polynomials is of order n squared at large n, just the number of variables. But this n squared number of variables is producing all the Feynman diagrams. It's sort of breaking the space up into all the exponentially many diagrams at large n, which gives you something of order 4 to the n. Okay. So okay, I think that's all I will have time to explain. Let me, yeah, I think I will have to end there. Maybe I'll just say in 30 seconds that if you take those formulas and instead of taking the tropical version of the u's, you just take the full u's, you get string amplitudes. Okay, so that's the relationship between particle and string amplitudes. Except string amplitudes, there's lots of questions you can ask. What about d equals 26? What about all that kind of stuff? I could say a little bit more about that, but maybe the most basic and important point is that when you write this formula down, you really have to take the product of really all the curves. And what we talked about in the field theory limit, we also take the product of all the curves, but the only ones that matter are the curves that don't intersect themselves on the surface. Even if you included the curves that intersect themselves on the surface, because they intersect themselves, they can never go to 0. So they don't ever show up in the field theory limit. And also the closed curves on the surface don't show up in the field theory limit. We don't need them. We could add them, but they wouldn't appear in the field theory limit. But you really need to add every curve on the surface. And it's really nice because you don't have to think whether a curve intersects itself or not. You just write every word you can. You don't even have to check whether the word corresponds to a trip that somewhere intersected itself or not. You just write down every word you can, including the words for all of the closed self-intersecting loops. And you'll get string amplitudes out of this. In order to see that they look like string amplitudes and compare to what you get from Green, Schwartz, and Witten directly, it's not useful to use these y variables. It will give you the same answer, but to see that it's explicitly the same, you want to see the solution for these u variables in terms of hyperbolic geometry, which makes the connection manifest. And for instance, I don't have time to explain it. I can just say that if we look at the product of all these self-intersecting curves, there are these infinite products. And it's these infinite products that take this very simple formula that I start with and gives me Jacobi theta functions and Dedekind eta functions of the sort that we're used to seeing at one loop in string theory. All right, so that's it. There's a number of immediate questions and generalizations. So as I hope you've seen, the amplitude is clearly counting something. We don't know what it's counting. We'd like to understand what, this is just for the trace phi cube theory. We'd like to understand what to do for totally general theories where there's, the question is where we have numerator factors, polarization vectors, momenta, is there some kind of analog of this tropical fan magic in the numerator? And there's another point that's sort of obvious from what I told you. In the limit, as the number of particles goes to infinity, the amplitudes simplify. There's a kind of a one-dimensional path integral formula for the amplitudes, and this limit as the number of particles goes to infinity, where 1 over the number of particles is the coupling constant. Okay, so there is some interesting limit that we can think of and characterize in this way. All right, so I think that's all I'll say since I've gone on a lot. Thank you very much.
Thank you. Thank you, Nima. I think we have time for -5 questions. So is there very, very urgent question? Or I would suggest to postpone it to break, so you can ask Nima whatever you want. Thank you very much.
nahrává.
Yeah, why don't you just take your, why don't you just sit here?
Oh, you want me to sit here?
No. But I mean, then the speaker, it will be difficult for him to walk past you. Or, I see.
No, now it's on.
Yeah. It's on. Yeah.
No, I will come
use
here
this one
to introduce you, and then I'll go and sit somewhere. I thought I could sit there.
Yeah, like that.
Okay. I see.
Sit down and just talk with him.
No, yeah, of course.
So when I'm going to introduce you, you put this up. Is that right?
Yeah, it's correct. I will just switch it.
Okay. It's already
Okay,
done.
it's already.
Yeah, just say things about coffee break, then I give it.
Tak bude pro speakery, my jim budeme průběžně
Jo,
doplňovat.
dobrý.
Ještě si můžu poprosit.
Okay, welcome back. Before we start the session, just a few announcements about the coffee breaks. Just as a reminder, the coffee breaks are on both floors, because most of the people went to the first floor this time, so both floors, so equally spread between the floors. The second thing about allergies, many people indicated allergies, and we have a special table with food which agrees with these restrictions. Then there is a person in the back responsible, so please, it's on the first floor, always during the coffee breaks on the right. So if you have allergies and you indicated that, please go to that table. And the last thing about cups here in the seminar room, you can take the coffee cup, you can take the plastic cup, but please don't bring any glass, because already some of it got broken here. So no any glass cups here in the seminar or in the lecture room. Okay? And then, and I give it to the session chair, which is Ricardo Monteiro.
Okay, thank you. Okay, we'll have 3 talks in the rest of the morning, and the first one will be given by Song He, who is joining us from Beijing. Go ahead, Song.
Can I start? Okay. Thank you, and I'd like to thank the organizers for this opportunity, and really wish I could be in Prague. But anyway, let me try to share with you briefly some recent works or recent fun we had playing with geometries in twistor space. So 2 stories with 6 really brilliant students. The first one on this paper with Jiakai, Zhenjie, and Yaoqi on some ABGM amplitude hedron, and then the second one with Jiahao, Yichao, and Qinglin Yang on symbology of finite integrals. And you can also see this single author paper of Qingling and also our collaborations with Yang Zhang's group, these other papers. So for this audience, I guess we don't have to emphasize that how many times we have been amazed by the surprises brought us from amplitudes in QFT, especially after Wheaton discovered the twistor string. And a lot of these surprises, these amazing structures have came when we rethink amplitudes in twistor space, including momentum twistor space, such as the original BCFW, CSW has been inspired by twistor string, but also more recently for the positive Grassmannian and the amplitude hedron for n equals 4 superior mules and the certain generalizations. So I want to share with you in this talk about two recent adventures that we want to study in twistor space, especially about the geometries in twistor space. So the first one is that we found there's a very surprising, to me, a very surprising relation between the amplitude hedron in n equals 4 and that one in ABGM, which also lead to a huge reduction. So it turns out the ABGM one provides a great great toy model for the amplitude hedron in n equals 4. And the second one, I'll show you some method by considering so-called Schubert problems or intersecting lines in twistor space that we can study the so-called symbology of finite integrals. Okay, so to be a little bit more specific, I think we'll hear more in this talks about a lot of structures reviewed by the amplitude hedron. While they are being studied very extensively, I would say like when you go to higher loops, it's relatively difficult and less studied, even for 4-point. So it'd be very nice to have a simplified model which we can become much simpler to solve the integrands and even perform integrals and so on. And you've heard from Nima's talk about the example beyond n equals 4. Of course, we want other examples where you can study like trace phi cube to all loops in some surface hedron. But what about our more familiar object, familiar theory like ABGM? So far, at higher loops, very little has been known about ABGM. Even beyond 3-loop 4-point, nothing has been essentially no explicit results have been achieved. So it turns out that you can obtain an amplitude hedron in ABGM by basically the simplest guess you would imagine. Just take the amplitude hedron in n equals 4 and do the dimension reduction in twistor space in some sense. Okay, so that's the first part I want to guide you through. And then I'll also talk about the multi-polylog symbology, where we've seen many interesting structures like causal algebras and Bootstrap and so on, but also not only for amplitudes, but move to finite integrals. We already know that twistors, the momentum twistors are very good at parametrizing 4-dimensional kinematics, and there's so-called symbol letters of these multi-polylog functions, even beyond the DCIKs, or you have external masses, you have non-planar integral, they're very good for those. And there are interesting mathematical structures such as tropical Grassmannian and so on discovered for these things. So what about going beyond strictly 4-dimension, going to dim rect? Can you still talk about this symbol letters we found for finite integrals in 4-2 epsilon dimension? So that'll be the second topic. So let me just give you a very quick review of what momentum twistors are. These are just simply light rays living in the dual space-time, inspired by the duality of amplitudes with Wilson loops. So more they're defined like this for each light ray here, and they can manifest the dual the conformal symmetry in this dual space-time. And if you give me an n-gon where every momentum is massless, so this is the we can introduce these dual points where each light-like momentum is given by the difference of the two adjacent x. And then you have a collection of also an n-gon here in twistor space, where each light-like momentum is mapped to a point in twistor space, but each dual point, each space-time point is mapped to a line given by these 2 points two adjacent points in twistor space. Okay, so you can do this more generally if you consider some massive external particle. Then you just put 2 twistors here. Okay, so like if you want to consider a 2 mass easy kinematics with two masses here, you just put 6 particles, which doesn't depend on the dual points here, but only these 4 dual points. So for example, the square of this momentum is given by this expression involving the infinite twistor. Also, you see here that the dual points representing the loop momentum is given by another line with usually called AB in Twister. So these are all you need to know about Twister space that I'm going to use in the rest of the talk. So let me move to the first part, which is for dimension reduction of amplitude hedron down to ABGM. So we know that the L loop endpoint amplitude hedron depends on an external momentum twister Z that I just showed you, and also L lines AB. In AB, each AB is a line for the loop momentum. So for 4-point, this definition is given purely as a geometry in this 4L dimensional space of AB, because you can gauge fix the external Z. And they are given by this very, very clean definition here that the for each loop AB with this external 1, 2, 2, 3, 3, 4, 1, 4, and so on has certain sign. Yeah, these are all positive and these are negative. And as well as this important mutual positivity that for any of the two loops, you have this ABI, ABJ positive. Okay. So what about 3-dimension? When we go down to 3-dimension, all you need to do is to take every line in twister space, which is a point in space-time, and dimension reduce it to 3D, which is done in this paper by using this so-called symplectic condition that every line AA plus 1 is projected, satisfy omega ZA plus 1 equals 0, but also for the internal line AB, you need to satisfy this so-called symplectic condition. This is just the literally dimension reducing 4D to 3D, but in twister space. And for 4-point, which will be the focus of this talk, we just see there's again no external AB, just no external Z, just all this 3L dimensional geometry living in this constrained ABI space. Okay, so I give you some parameterization. This is a familiar parameterization of A and B in terms of external momentum twisters. Then you see the familiar definition that X, Y, Z, W are positive, and this so-called mutual positivity condition is this. This guy is negative, except now you have the symplectic condition that says X, I, Z, I plus Y, W I equals 1. This is the dimension reduction to 3. So let's even look at just the one loop. Okay, the one loop case, there's no mutual positivity. So the usual four-dimensional one loop 4-point amplitude hedron is just given by X, Y, Z, W positive, and the canonical form, which gives you the one loop integrand, is nothing but the dual conformal invariant box here. Okay, you have 4 propagator. This is just the 4-dimensional box. Now dimension reducing to 3D is just adding a delta function here, which actually, if you rewrite in AB space, you see there's a 3-dimensional form with this interesting numerator. This numerator is nothing but the famous epsilon numerator for the 3-dimensional box. So this is the answer for 3-dimensional ABGM integrand. This is the first hint that when you dimension reducing a 4-dimensional DCI box to 3-dimension, you pick up an epsilon numerator in the for the 3D box, and that is the correct answer for ABGM 4-point one loop. So how about going to higher loops? The amplitude hedron going to higher loops even for 4-point is very complicated, but there's some nice trick last year by decomposing the 4-point amplitude hedron into negative geometries, where if you consider all the positive mutual positivity conditions for any two loops and write it as no condition minus the negative condition, then you minus this negative condition, then you end up with a bunch of negative geometry where each line represents a mutual negativity condition. So this also gives you a nice representation for the log of the amplitude, where for 2 loop, you just have this single connected graph. For 3 loop, you have this 2 graph, which is a chain or a triangle, and you don't need to worry about the disconnected graph. They just give you the product of lower loop in the definition of log of amplitude. You need to subtract the product of lower loops, right? And then this is the representation of negative geometry for the 4 loop log, where you have this 6 topology of negative geometries. I want to emphasize that there's a huge simplification when you now just do dimension reduction, because most of these graphs, these negative geometry graphs, are gone. So actually only a very small, tiny fraction called bipartite graphs, they will remain. For example, for 3 loop, this triangle is gone. Only this chain, which can be made bipartite, remain. And for 4 loop, out of all this graph, only this 2 trees and this box, only the trees and this box will remain. They can be made bipartite. And I won't go into any detail, but I just want to say this has something to do with a special feature of mutual negativity in 3 dimensions. Actually, once you write down the mutual activity in 3 dimensions, they give you natural time ordering of this loop variables. So as if you are living in some ADS3 with time ordering for each edge, you have some arrow that you have earlier guys and later guys. And of course, because it's time ordering, there's no closed loop. So already you can write the sum over all graphs and sum over some directed acyclic graph where you don't have any closed loops. And then by a theorem, we proved all this combination of negative geometry undergoes a huge cancellation. This is example for 3 loop that most of this arrowed directed acyclic graph cancel and only bipartite ones remain. For example, here triangle cannot be made bipartite, so they all cancel. And the chain guys, you can only left with either the middle guy is the source or middle guy is the sink, which you can write it as black or white node. So actually, this is a huge reduction. You see the guys remain compared to the original guys, just it goes to 0. The fraction goes to 0 as L goes to infinity. And then also it has a very nice pole structure that each black or white spot represents a certain possible pole in 3 dimensions. This is not seen in 4 dimensions. So 3 dimensions is really much simpler. And I'll show you a bunch of examples. First, I introduce some, so I'll show you the results up to 5 loops. Actually, beyond 3 loops, these are all new results. The 1 loop results has been written in this shorthand notation here. I put, because this pole always comes together, like the loop AB with 1, 2, or AB with 3, 4. I call it an SI pole. It has Y, and W. Actually, it's a double pole. It has 2 poles. And AB 2, 3, AB 1, 4, I call it T pole. And then the mutual guy, I call it Dij. Okay, for any 2 loops. C is just this constant, and the epsilon is the epsilon numerator I introduced. So for bipartite graphs, first thing we know is that the pole structure is always very simple. The black guy has a S pole, the white guy has a T pole, and any edge has a Dij pole. So for 2 loop, already 2 loop is well known, but it's interesting to look at its log. It only has this 2 bipartite graph, which you have this results, or if you can write it out completely. This is nothing but just 2 double triangle with some non-planar external points. And for 3 loop, this is actually a new result that log of the 3 loop actually has only 1 topology. Again, it's a chain diagram. There's no triangle. And it's again a ladder diagram. So the log of 3 loop in ABGM has only ladder diagram. This is a very interesting result, which confirms some conjecture in earlier paper. And now starting 4 loop, everything is new because nobody has computed this before. From our geometry, we can see that there are tree, bipartite graph, and the box. And the trees are very simple. They have always only 1 term. And the box you need to compute. So given the denominator, you need to find the correct numerator for the canonical form. But it also has a very compact result. And then 5 loop, you can keep going. You have this tree guys and the box with another edge and this genuinely new topology. And there's actually a general formula for tree. You always can do this so-called inverse soft construction to build any tree diagram in negative geometry. But for these others, they're a little bit more complicated. So in this way, you see huge simplification compared to Super-Amuse case. And very nicely, they give you the loop integrands for ABGM amplitudes at higher loops. And you can actually also have evidence that they give you all loop cases because you can check some all loop cuts. For example, in ABGM, you cut this, for any loop, you cut this 3 propagator, it should reduce to L-1 loop. And this is derived from geometry, very trivially, because the geometry just reduced, the residue just reduced to a 1 loop less. And you also, any cut that isolate an odd point amplitude, like 3 point or 5 points, you can see that the geometric makes it manifest that it will vanish. So this is also an important class of all loop cuts for ABGM. Finally, we checked our 5 loop results agree by checking the unitarity cut. So you do this double cut, it's given by product of lower loops. But it'd be very nice to see if we can really prove it. Okay, so let me turn to the second part, which is a totally different story. But you can see that in spirit, they still resemble the theme that we're really we're really employing this power of twistor variables a lot. But now we are not considering some integrands. We're really considering integrated results. Okay, so these are some symbology of integrated amplitudes, and simpler cases there are finite integrals. What kind of symbol letters you can have? And the basic idea is, again, very, very simple. You start with some integral topology. You consider cutting its propagators, like consider some maximal cut or some leading singularity. But now you do one step further. You not only compute the maximal cut, you want to know what this maximal cut look like in twistor space. Okay, so this is a famous Schubert problem, because every loop, every propagator, by cutting every propagator, you are intersecting two lines in twistor space. You're intersecting the internal AB line with the external, say 1, 2, or 3, 4, 5, 6, 7, 8. So this is an example of 4-mass box. You've seen this 4-point case before. This is an 8-point example. I want to make everything DCI at the finite, so I use this 4-mass box as an example. So by cutting this 4 propagator, you really mean that you want to intersect your AB line with the external 4 lines, right? So this is a DCI integral because all the infinity canceled. We know very well that it's very well known that for this quadruple cut, there are 2 solutions, and you can compute this leading singularity is for the scalar integral, it's is proportional to the inverse of this delta here, the famous square root with the 4-mass box. But one step further is that we want to compute cross ratios on this line. So not only just the usual leading singularity, which will be a special case, but we want to really compute what are these intersection points on internal or external lines, and then we want to compute some cross ratios, okay? Because these are the natural geometric invariant associated with these intersecting configurations. So in this case, you have 2 solutions. They intersect these 4 external lines at these 4 positions. You can compute this cross ratio. It's given by the famous Z and 1 minus Z. For the another solution, Z bar and 1 minus Z bar. This is nothing but the 4 symbol letters of your 1 loop integral. So this is a first example that after integration, the symbol letters of your multi-polylog functions are given by cross ratios, geometric invariance of your intersecting lines in twistor space. And you can go a bit further. You can also look at external lines, not only the internal lines. So look at this external line. Originally, it had 1 and 2, these 2 points. Now, after intersecting, it has 2 more intersection points. So you can compute the cross ratio of this 4 points. It gives you some other interesting symbol letter. These are not symbol letter for 4-mass box, but symbol letter for 8-point case, because you are using this twistor 1 and 2 separately, right? So actually, this was the idea by Nima almost 2 years ago by considering some already 6- and 7-point DCI integral and the cross ratios on the Schubert problem. You can easily see those classical algebra alphabets like A3 or E6 for 6 and 7 point. And for 8 point, in this paper by Qinling, you can study similar Schubert problems. You can generate all the interesting 9+9 algebraic letters and also some rational letters and so on. So let me explain a little bit further, like how do you compute the cross ratios? I'll take this 2-mass ZZ box case, which is simpler, that you have line 1, 2, 2, 3, which intersect at 2, and 4, 5, 5, 6. This is a 2-mass ZZ box. And on this line, you have 4 points, intersection points. On this line, there are 2 solutions. On this line, you only have 2 points. If you have 2 points, there's no geometric invariance you can compute. Only for this 4 point you can compute. So you can describe these 4 intersection points by a 2x4 matrix, actually a G24, and then compute this cross ratio. Like this cross ratio, 0.1, 0.4, the minor of 0.14 with 2, 3 divided by 1, 3, 2, 4 give you this cross ratio in kinematic space, which is this cross ratio, and 1 minus it is the 2 letters for the 2-mass ZZ box for the finite part. And in general, if you construct some intersection lines, there are m points on it. You will see that there are m times m3 over 2 cross ratios. You actually heard it from Nima's talk. These are some cross ratios satisfying U equations. They form a class algebra we call AM minus 3. This is the dimension of the configuration. And actually, for all we need, we just need to look at any 4 point on this line, which form a pair of cross ratio in this way, U and V. They add up to 1. So these are the consequence of this U equation, and they form a subalgebra of the general A. And let me give you an interesting interpretation of this U and V on the cross ratio on a line. Okay, so actually, what appear in symbol letter are log of this cross ratio, right? I mean, we should really say log U is the symbol letter, not just U. And log U is really the simplest. You take the log form of line interval like BC integrated along another line interval like AD, you just get this cross ratio U. And similarly, if you do it for another pair, you get V. So what if you replace one of the, I just mentioned this fact here. You can replace the D-log form by some elliptic form on the elliptic curve rather than on a line interval. Then you are producing elliptic simple letters. I won't be able to talk about this at all, but these are some work in progress, and you probably will hear it from Matthias' talk. So all these are about DCI integrals so far, because I'm talking about just nothing involving infinity. But we all know that for general integrals, if you want to write them in twistor space, they start to involve infinity. So this is an example of triangle that you only have 3 propagators, so you have also an ABI infinity in the denominator, not only just this finite guys. And our proposal is that in general, if you want to consider finite integrals in 4 minus 2 epsilon, where the I infinity is always there, you need to consider not only intersections of the usual leading singularity, but also those involving ABI infinity. And their intersection will give you not only on internal, external lines, but especially on the intersections on the I infinity line. Okay, so these are like examples of triangles, which will be building blocks that 1 mass, 2 mass, or 3 mass triangle. They give you some interesting intersecting point, and you use this intersection point to build cross ratios to predict finite integral symbol letters. So let me show you just for boxes. This is very simple cases. Like for 1 mass box, if you consider all the quadruple cut, including this I infinity, if you consider all 5 possible quadruple cut of this box with I infinity, you see 5 intersections. And the cross ratio of them form an A2 class algebra. That's exactly your symbol alphabet. For 2 mass easy, you get an A3 algebra because you have 6 intersection points. And now for these 2 more cases that are more interesting, you have A3 and A4 for 2 mass hard or 3 mass, but you also have some new cross ratios for other internal lines, not only on I infinity. So you union this A3 with this A1. You can consider all of them, but only this A1 is independent. And then in this case, you can consider this A4 with 3 more A1s, and they give you the familiar class algebra result for the 1, 2 boxes. And I'm running out of time, so I'll just quickly mention that you can move to 1 loop integral in general, and all you need are just pentagon integrals, because higher point I can reduce here, and you can do it easily for 0 mass or 1 mass or even 2 mass pentagon integrals, which you correctly, all your Schubert problem correctly predict their symbol alphabet from canonical differential equation, for example. And you can go to higher loops. I won't have time to talk about it, but just this particular example of double triangle or slash box, and you can even put another line here to make it 3 loop integrals. And in addition to the 1 loop case, you have the 6 intersections. This 2 loop leading singularity give you 2 more intersections. If you only compute the minor of these 2 intersections, you see the leading singularity. This is a famous leading singularity for the slash box. But now you can also consider cross ratio involving these new intersection points. They will give you very nicely all the algebraic letters involving this square root. And you can use it for Bootstrap. You can easily bootstrap the 2 loop and even 3 loop case using this A3 plus 3 algebraic letter in this case. And we can do it for actually phenomenologically interesting cases like 2 loop pentagon kinematics with 1 or 2 masses, or box kinematics with many massive corners. They are very, and you can even try to go to 6 point, but that requires a lot of work. So the final thing I want to mention is you can also do it for non-planar cases. Although here you have to be a little bit careful about what do you mean by cutting all propagators in twistor space, because the momentum twister are naturally defined for the planar integral. But here for a non-planar integral, we're inspired by this, what Sylvia and friends did for the dual conformal symmetry beyond the planar limit. The maximal cut can also be written in dual points and then in twistor space. And very nicely, you also correctly predict, for example, the symbol alphabet for this non-planar 2 loop integral. Okay, so finally, just a summary that we've seen in the ADGM story. Really, we want to learn if this is just for 4 points, or we can do it for higher points. What's the relation with the Wilson loop in the theory? And more importantly, we are doing integrals for this integrands. And could we do it similar to the n equals 4 case where you can maybe resum and so on? And for the symbology story, apart from pushing it to more the precision frontier, we're also interested in study the symbology for functions beyond the multi-polynomial, because we've shown you an example that at least for the double box case, the elliptic symbol letters may be predicted from a more sophisticated twistor geometry, not only the lines, but also elliptic curve. Okay, I'll just stop here. Thank you for your attention.
So, can you hear me?
Yeah.
Any questions? Yes, Johannes? Song, can you hear him?
No,
just a moment.
Hi, Song. This is Johannes Henn. Thanks a lot for the great talk. I'd like to ask about the first part. Can you say something more about extension beyond 4 particles, about higher n for the first part of the ABGM construction?
Okay, sure. So the definition, you can still try to dimension reduce, say, higher point amplitude hedron, but now you have 2 possibilities. One is that maybe, so even restrict so it is much more difficult to do it for higher k. So you can try to restrict yourself to MHV, which everything is bosonic here. So you will not expect this higher point, dimensional reduced higher point amplitude hedron will correspond to ABGM amplitude, which will be supersymmetric starting 6 point, and there's no odd point. So maybe this is really related to Wilson loops in ABGM instead. I mean, the MHV sector of the amplitude hedron. At least at one loop, we also see the dimension reduced guy has vanishing. I mean, order 1 is all 0. So it's all order epsilon contribution. So there's a chance that it's actually talking to Wilson loop instead of amplitudes. But you can also consider another possibility, which is at tree level, we successfully reproduce not by dimension reduction, but considering orthogonal Grossmanian in these 2 papers, we can have some momentum amplitude hedron at tree level for ABGM, like 6 point, 8 point, and any higher point. So whether or not we can generalize that to loop level is still an open question. Sorry, does that answer your question?
Yes, thanks a lot.
Sure.
Okay. Hi, Song. This is Julio. Nice talk. I want to ask about the second part. So if I understood correctly, none of the examples that you showed had a double pole anywhere. So does this way of deriving the symbol letters rely on your integral secretly being a D-log form?
Oh yes, yes. Actually, yeah. I think everything we had here are considering like UT integrals, which conjecturally can always be written like D-log, of course. Yeah. We're not considering like double propagator and so on, those cases, because yeah, to be more precise, we're considering integral topology, right? So you're always considering integral topology, and it's someone else's job to find all the master integrals there, and we just want to see that after you find all the master integral, which can be put in the, say, a canonical form for its differential equation, all the symbol letters appearing in that matrix may have an interesting geometric interpretation. So clearly, we're not involving any, when we compute all this leading singularity, we're not involving any higher poles and so on.
Okay, thanks a lot.
Is there one last quick question? Well, if not, we move on to the next speaker. And let's thank you.
No, no, moving to Queen Mary. Yeah, straight.
Okay, so for the second speaker of this session, we have Laurentiu Rodina, who was in Taiwan and who just moved to Queen Mary. Laurentiu.
Hello. It's great to be here, and it's great to see so many people after so many years of not going to conferences. Today I'll talk about some fascinating geometry we've been working on for the past few years. One of them is the EFT hadron, and I guess more people here would be familiar with it. In case you're not sick of hadrons, we'll be introducing a new one in an upcoming paper, hopefully later this year. And this is work with my great collaborators. So let me try to get this working. Okay. So I'll just jump ahead real quick to show you what the results are, and I'll introduce all of these things later. So here on one side is the EFT hadron, which describes the space of consistent effective field theories, or effective field theories that have some consistent UV completion. That's local, unitary, and so on. And this is given by the famous dispersion relations that I'll describe later, but roughly what happens here on the UV side, you have unknown UV states that have some interaction strength, roughly, some mass, some spin, and these give you the low energy effective couplings. And there's been a huge amount of work on describing this geometry and these relations and what they imply. But the focus has usually been on this interaction string being just positive. And what I like to do in this talk is describe some very simple elementary way to show what happens to the geometry when you impose that this P actually has an upper bound, which comes from unitarity. And at the same time, the same sort of tricks allow you to impose the low spin dominance condition, which has been recently investigated. And what happens is, very briefly, this is a space of two couplings, two low energy couplings. Before imposing the upper bound on P, you only get these projective bounds, which are two-sided bounds on ratio of couplings. Once you impose this upper bound, the geometry reduces by a lot to something like this. And you get non-projective bounds on any coupling you want. On this side, the modular hadron that I'll be very briefly introducing, is you can show that the partition function for a 2D CFT is described by virtually the same geometry. So here again, you have some, this is the degeneracy number, usually you just want it positive, you have the scaling dimension and spin. So the two geometries are identical. But what I like to focus on is actually show what happens when you demand that this degeneracy number is an integer, which is a condition that has not been studied too much so far. And again, just to show what briefly happens, this brown region would be what happens if you don't impose that this is an integer. Once you impose that this is an integer, you get these new boundaries, and your allowed space is inside here. So for example, why people are interested in this 2D bootstrap is as you increase the gap, at some point you don't get any consistent CFT. The way we see that here is as you increase the gap, this brown region shrinks, and when it shrinks to 0, that's the upper bound on the gap. But here, once you impose this integrality condition, the space shrinks slightly even faster. Now, let me motivate why it's interesting to consider space of theories in general. There are many things you can learn by looking at the space of theories. Of course, the most obvious one is you can rule out theories as you impose more and more constraints. Some theories are just not consistent with your constraints. But that's just one thing. For example, what often happens is as you're carving out your geometry, you get various special points. And in those points, it happens that for some reason, you can usually find very special theories. Some of them are known, some of them are not known. For example, Simon and Vincent found this 1 over STU theory in a special point of the EFT hadron. Other people found the low spin dominance. As you plot your known theories, you might find they lie in some particular subspace, and then you might wonder, is there some principle? Like, why are these theories all lying on this line? And in this case, it turns out there is some principle, low spin dominance. So that's one other thing you can find. And I guess one other thing you can do is, as you impose more and more constraints, it might happen that your space of theories actually shrinks down to a point. And this is actually the case, for example, for the open string. Take the EFT hadron, and you demand that the amplitude satisfies monodromy relations, you actually end up with just a point, which corresponds to open string theory. And now this geometry is interesting for many perspectives. It's related to all sorts of mathematics that people have been studying for very different reasons, like optimization theory, positive geometries, moment problems, geometric function theory, even sphere packing. And in this talk, I'll present a new approach based on Minkowski sums to describe such geometries. So how do you compute the space of, say, effective field theories? Well, you have your low energy amplitude that corresponds to some effective Lagrangian. You do the low energy expansion in SNT, and you get here some numbers. And now the question is, what relations must these numbers satisfy in order for this amplitude to have a consistent UV completion? So it's a very simple question. Of course, there's no obvious way how to do it. But we have the magic of the dispersion relations, which just relies on a very simple relation of these contours. So if you add these three contours that correspond here to the complex S-plane of your amplitude, you have your contour at infinity. You continue that contour around the UV parts with the cuts or residues or whatever. And then here you have the IR part of the amplitude. And of course, if the amplitude is analytic, there are no other singularities anywhere else. You can shrink those contours so these three add up to 0. So that's your starting point. And now there are very simple ways to express these three different contours. First, in the IR region, this is just your low energy expansion of the amplitude. Here, along the branch cut or residues or whatever you might find, you can use locality and unitarity to express that part of the contour. And it's going to be given by the expansion of the Gegenbauer polynomials. And then finally, if you have the Froissart bound, then this contour at infinity vanishes. So then you just have these two things left, you equate them, and that's your dispersion relation. And this relates the IR amplitude to the UV states, right? Now, of course, if you knew the UV states, like you know your UV theory has 5 particles with this mass and this spin and so on, you can just compute these numbers, and there's nothing that interesting to do. The interesting question is when you don't know anything about these numbers. You just know that this is positive, maybe bounded by above. You know that these are integers, and these are maybe larger than some mass gap. That's all the information you know. So the question is, what does this space look like? And this question has been studied from very many different perspectives by some directions here. I won't describe all of them. And of course, another very important condition is that you have the crossing symmetry, which you also have to impose on this geometry. Now let me jump to the modular bootstrap, which was introduced some years ago and then studied by many, many other people. And the modular bootstrap is about looking at the 2D CFT partition function that has modular invariance. So this is the partition function is just a sum over Virasoro characters with some degeneracy number, and it satisfies modular invariance. Now, in our upcoming paper, we'll show that even this partition function, once you expand around the self-dual point, is described by a relation very similar to the dispersion relation. In fact, it's almost identical. Where this is some degeneracy number, this is the scaling dimension, this is the spin of your operators. And in this geometry, the modular invariance condition actually becomes another set of linear planes that you have to intersect your geometry with. So just to compare the two, so these are the two things combined, and you see the geometries are just identical. These satisfy basically the same sort of conditions. This is some positive number, this is larger than some mass gap, this is integer. The modular bootstrap is the same, this is positive, this is larger than some scaling dimension gap, and this is some spin. And in our previous papers on the EFT hadron, we show how this geometry, you can solve it in terms of Hankel matrices. So these are well-known solutions to this sort of moment problem. Where, for example, a condition like this imposes the fact that this is an integer. Some condition like this imposes the fact that this is positive. Together with a bunch of other similar matrices and the crossing equations, we show that you get some plot like this. So this is the plot in some coupling space. And we get analytic boundaries for here, which match exactly the known numerical results using SDPB or other methods. So this was the old way of doing the geometry in terms of these matrices. Now, when I want to discuss more complicated conditions, for example, the fact that this has an upper bound and this is an integer, then the previous Hankel approach doesn't work, or at least we don't know how to do it using that. So I'll describe a totally new way to solve this problem, and that's using Minkowski sums. So probably everybody knows what the Minkowski sum is, but I'll just describe it very carefully so it's clear what's happening. So say you want to describe this space, which is given by some sum over spins. You know the spins, because this should be a sum over all possible spins, but you don't know these p's. Now say in the simplest case, you have just one state, maybe a spin 2 state, and you look at some 2D space, right? This is what you get with just one state, and this is a segment, right? For various values of p, if it's bounded between 0 and 1, for example, any value of p will put you somewhere on this segment. So the space is this whole segment. Okay, that's very simple. If you have 2 states, maybe a spin 4 particle, these p's are independent, right? So their sum is going to be this rectangle. It's easy to convince yourself that for any value of p1, any value of p2, you must be somewhere inside here. And in 2 dimensions, this is very easy to generalize and is well known. If you give me ordered vectors, like 1, 2, 3, or more, then this is the result. And these are the vertices. It's 1, 1 plus 2, 1 plus 2 plus 3, and so on. So it's this nice cyclic structure, although I should stress this is not a cyclic polytope, but it's very close. Now, oops. In higher dimensions, as far as we know, this problem has not been studied, or maybe I'm pretty sure some mathematician thought about this and solved it, but we couldn't find it. So if you look at the higher dimensional space, you're interested in the Minkowski sum of segments, the solution turns out to be some very nice polytope, where again, if you give me ordered vectors, cyclically ordered vectors, these are the vertices. It's, again, some cyclic or consecutive combinations of your vectors. And if you might think this is a cyclic polytope, it's not. Just the number of faces compared to edges and so on doesn't match what you need for a cyclic polytope. But in fact, the cyclic polytope that's well known from the EFT hadron is just the limit of this geometry. So here, these segments have basically some length L, because P is between 0 and L. If you take L to infinity, that is, you have no upper bound, if you just scale this to infinity, you only have these faces left. That's the cyclic polytope. So the cyclic polytope is just some infinite version of this more general non-projective polytope. And it turns out this is a very powerful thing, in fact. You can use this to prove many, many problems. For example, the L moment problem, which is a well-known problem in mathematics, is written like this. You're interested in what is the space that the AKs might satisfy if they're written in this form. And this is necessary in the dispersion relations, for example. When this rho, this should be M, sorry, is bounded. And you can use the solution we found previously. You can discretize this integral. And then obviously this integral is just a Minkowski sum of segments. And they are cyclically ordered because they're given by just this combination. You can check that these are cyclically ordered vectors. You add them together using the rule I showed you, where you get the consecutive vectors. You take the continuous limit, and you get this, which is the known solution to the L moment problem. And these are some known boundaries that I won't write down, but they're very simple. So this is what you need to do the whole EFT hedron, in fact. Because now the complete EFT hedron is a sum of such objects. So I remind you, this is the dispersion relation, where you also have the sum over spins. So you have such an object, it's multiplied by some spin, and then you have to do the Minkowski sum of objects like this. So the whole question is, how do you compute the Minkowski sum of such objects? And this is also quite easy to do. The first important thing to know is that to compute the Minkowski sum of 2 objects, you just need to compute the Minkowski sum of its boundaries. So for example, if here I want to compute the Minkowski sum of these 2 objects, say I want to do the lower boundary first, I just take the lower boundary here, which is some parametric curve. I take this one here, like A and B here. I add them. And to get boundaries, there are 2 things you can do. One is you just add them together and you extremise. So for example, you keep one coordinate fixed and you extremise in the other. That solution will give you a boundary. So for example, if you do it here, you get some relation between the two parameters, and you get this, which is just a one parameter thing. This is a curve, and it's a boundary of your space. And here is shown in green. But now, because your parameters are actually bounded, extremising is not sufficient, right? So using the Lagrange multiplier method only relies on local variation. So you have to be careful of the boundaries for your parameters. And if, say, your parameters are bounded between 0 and 1, then you have to take each of those choices. So you set here, for example, n you set to 0 here, or you set it to 1, or you set m to 0, or you set m to 1. All of these are possible boundaries, and I drew all of them here. And then it's just a matter of picking the right boundaries, which you can do by asking the boundary to be continuous or so on. So this is everything you need to do to compute the Minkowski sum of any object. And you can do it for the infinite spins. So here is, this is what it looks like for 2 spins. I showed before, it's just this. When you do an infinite number of spins, you get this infinite curve where each of these curves here is just a slightly different function. And for example, this one here, the first one, looks something like this. So it's a very simple polynomial, a parametric in some parameter m from 0 to 1 or some other value. And this f is some number that encapsulates the whole sum over spins. So the whole sum over spins nicely factors out, and it's just a number. And depending on the space you're looking at, it either converges or it doesn't. If it doesn't converge, that simply means there are no non-projective bounds for these couplings. If it does converge, as it does here, so this contains an infinite number of contributions, then you can intersect with your null plane or whatever, and you get your upper bounds, for example, here, right, where the null plane intersects. This is an upper bound in this direction, this is an upper bound in this direction. So this is essentially the non-projective EFT hedron. It looks something like that. It has an infinite number of faces, which are easily describable. So now let me jump again to the modular hedron, and I'll just stick to the spinless modular hedron, where I just ignore all of the spin part. And this modular hedron is actually just a Minkowski sum of identical curves. So that's all you need to compute. So the partition function you can show is basically written like this, where this is some integer degeneracy number. You have this factor coming in from someplace, and the scaling dimension dependence like this. And each of those things is one state, and such a state is just a curve. For example, something like this. And as the scaling dimension goes to infinity, this goes to the origin, because it's exponentially suppressed. And at 0, where it starts at some other point. So each state in the partition function is a curve like this. So then you just need to compute the Minkowski sum of these curves. For example, 2 of them add up to this. And using the previous rule, this is easy to show, you can either get boundaries where here, for example, delta 2 is set to infinity, so this just drops out. You get one boundary. Then you can set delta 2 to 0. You get this boundary. And because this is identical, it doesn't matter which one you take. And finally, the upper boundary is when you do the Lagrange method. You extremise, and you get that the extremal solution is given when the 2 parameters are equal. So these just add up to 2. So this is what the space of 2 states in the modular hedron looks like. And then this is easy to do for arbitrary number of states, in particular because the Minkowski sum is associative, so you can just do it by induction. So here you have what the space for 2 states looks like, for 3 states, and then you just notice the pattern. For infinite number of states, you just have this non-trivial lower boundary that repeats to infinity, and a trivial boundary that just diverges and goes upwards. So to compare with the non-integer condition, it will basically fill up this space. So the fact that you have integer degeneracy number is carving out these small holes in your space. And it gets a lot more fun when you go to higher dimensions, so you can still do this and still draw it very nicely in Mathematica in 3 dimensions. And this is what the space looks like. This is what the boundary looks like. And the important thing is that any strip here is a very simple function, and it is described by a finite number of states. So for example, the first strip here is just this combination of states. It is just 2 states with no degeneracy number. The second strip, you just have to put a 2 here, and so on, for all of these strips. And the vertical ones are just, you can describe them in a similar way. So that's the space. And then, of course, you have the modular planes, right, that come from modular invariants. And in the way I do the geometry here, it's the null planes, these planes that contain all of the information on C, the central charge, and your value for the gap, for the upper bound for the delta gap. For various values here in blue, so C, for example, 1, and no, and some finite gap, you get this blue plane intersecting the geometry. When you have no gap, it's this green plane and so on. And you can, changing the value for C or delta just changes these planes. The geometry is identical. And this is what the intersection looks like for each of those planes. And if you wanted, again, to compare without having this integer condition, basically here the difference would be you would get some smooth curve going like this, or 1 here. So again, this is carving out lots of spaces. And you notice for a non-zero gap, the geometry starts looking very weird. You have these isolated regions and so on. So it's quite interesting what's happening. And you can see why that happens when you compare it to here. It's just hitting these vertical boundaries in some interesting way. So this, I should say, this you can do, these are all analytic functions. It's just a very simple relation you can write down. It's a known function that describes such curves. If you want to do more null planes, and of course you want to do an infinite number of planes, so far we only know how to do it numerically, but with arbitrary precision. So here, if you have no gap, this is what the space looks like. With 2 null planes, you have these holes being cut out of your space. And of course, the problem is very interesting when you have some non-zero gap. When you have non-zero gap, the geometry is finite. Here it's infinite, it just goes to infinity. Once you start imposing some gap, the geometry shrinks, like I said before, and at some point it goes to 0. But here, you notice that this will shrink much faster because the boundary is a lot smaller. And another interesting thing to notice is that if your favorite theory lives on the boundary of this space, once you impose the integrality condition, then it's quite likely your theory is ruled out because these new boundaries only touch the old boundaries in isolated points. In fact, here it's just these 2, maybe 3 points. Here it doesn't touch, here it doesn't touch, it's all inside. So most of the boundary is actually ruled out, and we know that usually it's the boundary that is the interesting part of these geometries. Just to summarize, and some ideas for an outlook, the main conclusion is that the space of EFT couplings and CFT partition functions are described by similar geometries. In fact, they're almost identical geometries. The only difference is how the null planes intersect this geometry. And today I showed the Minkowski sum approach to implement more difficult constraints. Some of them have been studied by various people. Some of them, as far as we know, haven't. For example, this integer degeneracy number, except for special cases. But this is some approach that works in general. For the future, there are many things to do to generalize what we have been doing. For just, there's been this recent paper, well, of course, many others doing the full Bootstrap, where they look at the full nonlinear unitarity condition. So what I did so far is just look at the linear part of the unitarity condition, which just puts a lower bound, it's just positivity, and an upper bound. But the full nonlinear unitarity condition is more complicated from our perspective, but I think there could be a way. For the CFT Bootstrap, we just started scratching the surface. So for example, we haven't looked at spin so far, although it's going to be just the same. When you add spin, the modular hedron is still just a sum of curves, but now each curve will just be scaled by some spin. But it's still just a Minkowski sum of curves. So in principle, it should be easy to compute. Then we might want to look at adding higher null constraints. This is something we don't know how to do yet. It requires some interesting, maybe numerical methods to solve complicated exponential equations. But the point is we know the equations we need to solve. So in principle, it can be done. Something we don't know for certain yet, which is obviously what people will be interested in, does this actually do anything? So of course, there are reasons to believe that as you go to infinite C, which is an interesting limit, the fact that you have integer degeneracy or not shouldn't change the result at all. So it shouldn't change the bootstrap. At finite C, it's less obvious. And at this point, we're not sure if once you do the full bootstrap with a large number of null constraints, if this condition actually changes anything. But regardless, it should be interesting to figure out how to do this geometry. And of course, here I've been doing just this Minkowski sum, but we're still interested if there's a more traditional Hankel type approach that we can use to carve out these geometries. Thank you.
Are there questions for Laurentiu? Yes.
Hi, thanks for a nice talk. So when you derive the bounds from the upper limit from unitarity, so usually in the inferred, the EFT becomes strongly coupled if you're close to unitarity bound. Yes. So I wonder for the coupling constants, like how stable are they under loop corrections?
How stable as you go to a strong coupling?
In the inferred EFT part.
So here in what I've said, I've ignored loops. If you add loops, basically what changes is, first of all, you won't be bounding just these couplings, but they start running, so you get the logs. So then you have to carve out the space for complicated functions of these couplings. So here I'm just focusing on things that are linear in the S matrix. And of course, then besides the fact that here you get logs and so on, the crossing equation, the crossing condition becomes more complicated. But in principle, you can do the same sort of things to derive that, but this doesn't apply to any of that.
Yeah, I guess my worry is whether perturbative expansion is valid if you're close to unitarity.
Yeah, that's of course a big question. So the issue is here, because I'm ignoring loops, that means my coupling constant is very small. So then, of course, it doesn't make sense to put an upper bound. This still works for operators that are just linear in these constants. So some observables might reduce to just this. So for those, it's interesting. But I'm not saying if you take any Wilson coefficient in your Lagrangian, this is an upper bound for that.
Thanks.
Hi, Laurentiu. Thanks for a nice talk also. Just to rephrase Shashan's question a little bit, say I go to the boundary of your region and I just step out, right? What do you expect that it's violated? A weak coupling assumption or some of the other, like unitarity, causality? Like what do you think is the generic?
It's just sort of inconsistent because here, because I'm ignoring loops, I'm assuming that these couplings are small. Now I'm saying something small has an upper bound. That's not directly consistent if you phrase it like that, so you have to be a bit more careful exactly what you're trying to bound. Generally, this doesn't make sense, right? You're assuming these are small, but then you're saying they cannot be bigger than this finite number. Of course, that's nonsense. So this is not what this applies to. Yeah. For the moment, I would prefer to just take it as a mathematical problem phrased like this, and then figure out where it's physically interesting.
Okay, so would you agree then that these are bounds on these arcs?
Yeah,
and
you can add
how
the
do you
arcs.
translate that to a low energy observable, like a Wilson coefficient? It's a different problem?
Sorry?
So this is a bound on an arc, so this integral over the amplitude
yes, exactly.
are close to the cutoff, and then the problem of translating that to a low energy observable, like a Wilson coefficient, is separate.
Yeah, so if you add the arcs, then you can do this thing again, but then it's an arc and it's not just one. Yeah.
Okay, thanks.
Any other questions? Well, if not, let's thank Laurentiu again. Okay, for the final talk this morning, we have Edison from Uppsala.
Thank you. Thank you to the organizers for letting me talk to you about my work. So I'm going to be telling you about pushing the loop frontier in non-planar n=4 super Yang-Mills. And in particular, I'm going to break it up into 2 segments. One is going to be about 6 loops, and one is going to be about 6 points. So the 6-loop work is with John Joseph Krasko and Henrik Johansson, and the 6-point work is with a much larger collaboration, Song, Henrik, Oliver, Fei Tang, and Yong Zhang. The 6-loop work is already out, and the 6-point work should be out hopefully sometime this fall. So, starting with the 6 loops. What are we looking to do? Well, we're looking to calculate the 6-loop full non-planar integrand, and there's various reasons we might want to do that. But most of them are related to the fact that what we really want to do is calculate the 7-loop non-planar integrand, because that's going to be related to questions about counterterms in supergravity. So the big question is whether n=8 supergravity is finite, and whether it has a counterterm in L=7. So at 7 loops, there is a predicted, non-protected supersymmetric counterterm that various groups have various symmetry arguments for constraining or not constraining. And one of the problems is that there's similar counterterms predicted at lower supersymmetry and lower loops. So this is n=4 and 5 at L=3 and 4. And direct calculation of the integrands and then doing UV expansion shows that these counterterms actually have a coefficient 0, which begs the question, what happens at n=8, which is more supersymmetric, should be better protected than these examples. Also, there's some notion of improved UV behavior with special kinematics in 4D. So maybe there is actually something special going on strictly in 4 dimensions. We need to go there and actually find out what's happening. So there's a nice long history of our direct loop calculations, starting all the way back in the 80s with 1 and 2 loops, proceeding through 3, 4, and 5 loops in 2018. So this is all for both super Yang-Mills and supergravity. Each step, as you can see, gets harder and harder, and the gap between the calculations gets longer and longer. We're hoping to slim that down a little bit now that we understand things slightly better. So in general, what the goal is going to be is find some way to recursively construct cuts or contact term corrections that are equivalent to finding the cuts for all of the non-planar diagrams. And to do this recursively, we need to think about what properties do our tree amplitudes that go into the cuts obey. So the very first thing that we'll take a look at is what we call the X identity. And this is a pretty simple observation, that if you take a color-ordered 4-point Yang-Mills tree amplitude, and you try and go on the U-channel pole, the one that's not there in the color ordering, well, there's no pole to sit on. You can't actually go, you don't blow anything up. And so if there's something non-zero there, it has to be finite, it has to be dimensionless, it has to respect all of the symmetries. So the only thing you can get is some insertion of delta functions. Basically, that means that if you go on the right kinematic limit for a 4-point color-ordered tree, you just disconnect the diagram. This is a rather straightforward statement, and it's true for all of the supersymmetric states that run in it. So at tree level, this is super easy, super straightforward. Essentially, all you get is, for an explicit representation, some dot product between the polarizations. That's effectively an insertion of delta functions between the states. Now, this is a nice relation, but we notice that it switches planarity, so that if we're planar here, the crossing, the disconnected into the crossing is a non-planar disconnection. So if we want to maintain planarity, then we need to do a little bit of work, but it's not that much. All we have to do is invoke the BCJ relations. So first we start by noticing that if we multiply the color-ordered amplitude by the pole, and then send the pole to 0, that's just taking a residue. It's taking a residue on a very special limit, but it is just taking a residue, so we're essentially going on the cut of the tree. We can then apply the fundamental BCJ relations, so the S times 1, 2, 3, 4 times equals U times 1, 3, 2, 4. Rearrange things a little bit, and then apply the X identity, the thing that I just talked about, on the side that it makes sense. So what happens is we just disconnect the diagram again, but this time we've aligned things so that we're sitting on the factorization channel. And essentially what that says is something that should be familiar to everybody, is that if we have some 4-point factorized diagram and we sit on the zero flow across the cut, that just turns into some prefactor times disconnected diagram. Most people will know this as an incarnation of the rung rule. But what I want to stress here is that this is not the rung rule. This is the proof of why the rung rule does work where it does, but subsumes it and is a much stronger statement because it is based on direct calculation or direct observation on the 4-point amplitudes, and it will hold regardless of which supersymmetric states are running, and we suspect it extends to supergravity via a soft factorization proof, but we haven't done it yet. So we have some nice properties of tree amplitudes, and we want to turn these into statements about loop amplitudes, and specifically about cuts and how we can extract cuts using these tricks. So the main goal is going to be either we want to calculate the full cut for a diagram, and from that, if we know all of the cuts, it's relatively straightforward to reconstruct the integrand. Or what we're going to be looking to do is calculate the local correction from a contact diagram, and that's equivalent to saying, what is the part of the cut that I don't know about if I know all of the pole terms already? So if I look at the X identity, the very first thing I talked about, where we sit on special momentum flows and that disconnects the diagram, well, if I embed that inside of some loop problem, let's say I have this 6-loop cut on the left-hand side, this very non-planar 6-loop cut that I want to calculate. What I can do is I can take every single place where there's a non-planar crossing and upgrade that into a 4-point amplitude. Now, with a little bit of careful rearrangement, this thing, if we just naively took all the crossings, turned them all into 4-point amplitudes, this would be an L equals 11 cut at next to the 5th maximal, so with 5 contact points in it. But if we're a little bit careful, we can shift the bar up. Now this becomes an L equals 10 only, where we're taking some special kinematic limit between all of these different colored legs. So each of the colored legs, you should think of identifying the momentum flow across them. When you take the special limit, you get the right thing, but there's a couple problems if you want to do this systematically. The first is, if we're starting from the lower loop diagram and trying to find the higher loop diagram we have to evaluate, this is an NP-hard problem. So even starting at just finding the first level, this is some binomial number, and then as you go higher and higher, trying to find all of the different crossings, this gets worse and worse. Also, if you want to start calculating these things, okay, at 6 loops, you can get by with only going to 9 loops, so only 3 loop levels above. At 7 loops, if we want to keep pushing this, you get up to 11, 12, significantly higher loop order, and this is well beyond what anybody has calculated in forms that are manageable to use. Also, this only works in color-ordered cuts. There's potentially some hope of adapting these to direct supergravity calculations. So if we're stuck on color-ordered, that doesn't promote to gravity particularly well. So instead, we're going to look at the H identity. So this is the second identity I talked about, and see how that embeds inside of loops. And the trick here is that what the H identity actually tells us is various limit conditions on the cuts. So our goal is going to be to calculate the local correction. And there's going to be some pole terms for most cuts, but the pole terms that we will know because they have to be things that are descended from closer to maximal cuts. So more legs on shell, we'll know what the pole terms are, and so as we go lower, each of the contact terms, we know everything that contributes on the pole. All we care about is some local polynomial correction to these cuts. And what the H identity tells us is that there's some special limit we can take on the local term that gives us some special limit, that same limit applied on the pole terms that we already know, plus something that is the lower loop cut. And that lower loop cut comes from taking whatever leg we took to 0 and just deleting that from the diagram. So the prefactor then is just the P, the momentum that's flowing through the 2 legs that are identified. And if I say just this, again, this smells quite a lot like the rung rule. But really what we're going to do is we're going to do it on every single possible leg in the diagram. So instead of starting with the lower loop diagram and just saying, okay, I can stick this leg in and I use the rung rule and I get something, we know that this doesn't work most of the time. Instead, we're going to carefully parameterize some ansatz or something similar on the higher loop diagram and demand that we obey this limit as we go down, as we delete each leg one at a time. So why do I mention an ansatz? Well, we need to merge these conditions in some form or another. And we also need to evaluate the lower loop cuts many times. However, this is still very systematic, and it only needs lower loop information, not higher loop information. Now, getting to the merging, this is where some interesting math comes in. If you thought you were going to dodge out on geometry and intersections, I have bad news for you. There's some algebraic geometry involved here. So we could just write down an ansatz, brute force this out, and be done with it. But let's take a more clever approach. So the observation is that on any of these limits, we know that this limit can be phrased as some projection operation on our basis of momentum products that make up the cut. Now, we can calculate this projection, or we can calculate the result of this projection, and we know that the final contact correction has to be this projection plus something that's in the kernel of the projection. And very easily, we can rephrase that as some element of a polynomial ideal. That polynomial ideal is generated by the projector, or the things that are in the kernel of the projector, and then the result of the projection. But if this is true for every loop leg that we can take, we have one ideal for each limit we can take, and we know that the correction, the thing that we're after, has to live in each of those ideals simultaneously, which means it's just the intersection of those ideals. That's some algorithmic calculation you can do, throw it into your favorite algebraic geometry program, and it runs through, and you might say, well, okay, why do you need to do this if you can just write an ansatz and do it? Well, in almost every possible case, it is faster to use the algebraic geometry, it is more efficient to use the algebraic geometry, and it tells us some nice things. So one thing that we can notice is that in essentially every single case that we must use this process in, the resulting ideal in this intersection is itself an ideal. The resulting ideal has one element that has the correct degree. That is the minimal degree of the ideal. And so it is the one element of the ideal. It has the correct degree, which means that up to an overall factor, up to an overall coefficient, it must be the right thing. And in all situations that we can cross-check it, it is always exactly the correct object. So we have a way of bootstrapping our cuts, even fully non-planar, using lower loop data, and not relying on any sort of state sums, any sort of explicit state sums, or anything like that. So then we go and we apply this to every single diagram that you can write down at 6 loops, which we start with some vacuum diagrams, we dress them in all possible ways with 4 legs, we start collapsing all of the possible legs inside of the loop diagrams, and we get some very large collection of diagrams to look through. In the end, it's something like 1.1 million. Of those, 150,000 have non-zero contributions. So they're not trivially, the cuts aren't trivially satisfied already. And so we have dressings for all of these diagrams. This is the integrand, and it exists. It's on, hosted on Zenodo, but it's obviously too large to show on slide. The largest of the terms is one of these maximal cuts that has about 65,000 terms, but the average contribution is sort of 80 terms long. So, where are we going from here? Well, the goal is obviously to get towards supergravity. So we need to improve various things on the Yang-Mills side and develop the technology a little bit more to move to supergravity. So on the Yang-Mills side, right now the diagram power counting is very bad. This has to do with various choices as you go from the cut off shell. You have to make choices about what L-squareds to reintroduce, what cut propagators to reintroduce, and bad choices lead to very bad power counting down the line. There's also a lot of tools that we need to get ready for supergravity. And one of the interesting things is that because of the nature of computational algebraic geometry, various seemingly superficial choices and parameterizations of the intersection of ideals can dramatically affect runtime. So if we want to get things that at 6 loops, these things take about a couple seconds to run, but at 7 loops, they take a couple hours or overnight. We really need to improve various parameterization choices to be able to push on up to 7 loops. There's also some thought that we're putting into applying this to other theories to see exactly how powerful it is. Now, mentioning other theories, well, this is not quite another theory. We're staying in super Yang-Mills, but the other calculation I want to talk about is looking for color kinematics duality at 6 points at 1 loop. So, motivation for this is that essentially the BCJ formula, or BCJ form for 6-point super Yang-Mills has long eluded many approaches. So in 4D, there's some obvious problems, including the fact that the hexagon maximal cut is impossible to properly probe. You're in 4 dimensions, you only have 4 loop momentum you can cut, so you're actually looking at some contact correction. You could try brute forcing it, but brute forcing it is you need some degree 6 polynomial in your dot products. Bad choices of this end up with hundreds of thousands of terms. Good choices are slightly better, but this is still a huge headache to try and do. And you can take some string theoretic approach. These approaches are significantly more prescriptive. You basically just write down the correct answer, except if you try and do it via pure spinners, there's some problems where you break one of the BCJ relations. If you do it during doing forward limits, then you're stuck with linear propagators. And there's been some work trying to fix both of these problems, but in the end, you break something involving automorphism symmetries, or you break what the proper double copy is supposed to be, and so things go wrong very quickly. So let's mix both approaches. We want an ansatz of some form, but we don't want hundreds of thousands of terms. So instead, we'll take the thing that we know from the max cuts, that we know from the forward limit or string approach, and these are phrased in terms of, for the most part, T8 tensors. So T8 times 4 linear field strengths is essentially STA tree, but now we can add in, for instance, commutators of field strengths. And on the maximal cut, so the hexagon maximal cut, we know that we have a very specific structure that shows up. It's composed of these things, but we allow some contact degrees of freedom. And it turns out that if you're very, very clever about the contact degree of freedom choice, you can get it down to 9 degrees of freedom. You have 9 contact choices to make. There's actually 11 written up here, but the plus sic, if you're careful about that on the third term, only 2 of the 4 are independent under cyclicity. So then we walk through the standard BCJ color kinematics relations in which we can define the pentagon with a dangling tree in terms of a difference of hexagons, and then the various boxes in terms of differences of pentagons. And there's also the no triangle Jacobies, which essentially tell you that you should, if you anti-symmetrize the boxes, you should get 0 so that you don't develop triangles as you go, because you're in n equals 4 super Yang-Mills, there should be no triangles. So these defining Jacobies on the left-hand side, you use to define the lower topology numerators in terms of the hexagon. And the no triangle Jacobies on the right-hand side essentially lock the coefficients of these various contact terms into each other. So what do we get? It's actually surprisingly simple. I've written it up here on the board. So these first terms in red are exactly fixed by the hexagon maximal cut. So all you have to do is sit down and very carefully compute the product of 3-point amplitudes. And if you do it in, for instance, 10D, then all you need to do is you need to do 1 computation for the gluons, 1 computation for the fermions, and it just fixes these terms exactly as they are. Then these contact term corrections, as I said, the no triangle Jacobies, relate them all to each other. And finally, there's this nice trick that you don't actually need to do any of the lower cuts. All you need to do is calculate the gauge invariance, you need to enforce gauge invariance of the pentagon maximal cut. So you put all 5 legs of the inside the pentagon and the dangling tree on shell, and that relates That relates the remaining coefficient of the contact term to this first E.L term in red. And in the end, at 6 points, you go through all of this, and there are no free parameters left. This is some unique solution up to your definition of coupling constants. So we'd like to go beyond a little bit. At 7 points, we need some new class of contact terms. So for 6 points, we had E.L, and that was paired with some L squared. But now we have enough powers of loop momentum, need to be floating around, that we can have an E.E, L squared, E.L. These things get a little bit more complicated because, well, at 6 point, the E.L, there was some adjacency condition. But the problem is that if you impose the adjacency condition, so for instance, you might want E3.L3 or E3.L2, it turns out that this is too constraining, and you actually fail to find a numerator that satisfies all the conditions you'd like. And so what you end up needing to do is enlarge the ansatz a little bit. However, if you enlarge the ansatz carefully, then the heptagon max cut plus the color kinematics relations plus gauge invariance leaves 30 free parameters that cannot be fixed by any of the other cuts. No, gauge invariance doesn't touch these things, so you have 30 free parameters left. You can make some various aesthetic choices, but they're totally free and can be set to 0 if you'd like. Where we'd like to go next is towards 8 point. Now 8 point is even more complicated because now you have double contacts. So you have things like Li squared Lj squared or Li to the 4th. And we're interested to see if this sort of gauge invariance plus n-gons plus color kinematics is enough, if you need to start doing more complicated things, or if there are other aesthetic guiding principles to pick out the various combinations. And finally, one of the places we're interested in looking, and how this all ties back together with the 6-loop computations, we'd like to go to 2 loops. And at 2 loops, the maximal cuts, after a little bit of work, can be calculated via just direct sewing methods, so you can sit down and do all the state sums. But it'll also be very interesting to see, because we can probe them directly with state sums, it'd be interesting to see how much the H-identity construction, so the same method that we use for 6 loops, how much that can inform us about going to 2 loops at 5 point, 2 loops at 6 point, 2 loops at 7 point, and to see what sorts of structures show up nicely there. So, today I told you a little bit about some dimension-agnostic cut recursions that we've developed for 6-loop super Yang-Mills that we applied for the full calculation, and this is one of the next big steps towards the 7-loop supergravity calculation, which shows a little bit of hope, although things still look very challenging to come. I also told you about this nice 11-parameter BCJ construction for the 6.1 loop super Yang-Mills. I should say it essentially solves all of the problems of the previous attempts, that it has all of the automorphism symmetries, it squares to the correct objects, it doesn't have any spurious poles, and it's dimensionally agnostic, so we're not worrying about whether we have gram determinants or 4D specific identities at play. And both of these are opening the door to studying non-planar characteristics of higher points and higher loops in dimensionally agnostic ways. Thank you.
Questions for Alex? See.
Yeah, thanks. Thanks for the very nice talk. So at the 6 point, you said, the 6.1 loop, you said that after you impose the constraints, no free parameters. Do you understand why it worked perfectly like that?
I don't think we have a concrete answer for why it works perfectly like that. But I think that we made just the right guess at the ansatz, that we exactly parameterized what freedom we wanted. There's definitely some ability to extend things. So I mentioned at 7 point, you have to enlarge things to E.L where the L is something other than the adjacent one. There's the possibility of doing a similar thing at 6 point to see if that enlarges the space or not. We haven't tried. We got it essentially on the first or second guess, and decided to push on in points rather than figuring out exactly why things were perfectly locked in.
Is there the danger that at 7 points there'll be -1 free parameters?
What?
There'll be -1 free parameters in the sense that you cannot satisfy all the constraints.
No, so at 7 point, so at 7 point, if you use exactly the same type of ansatz as at 6 point, you do get something like -1 free parameters. If you loosen some of the constraints just slightly, so if you allow E dot one of the further away edges, then you can solve the whole system, and you solve it with 30 free parameters. So you actually, you loosen the constraint slightly, and then you get a larger class of solutions. And Lance?
Yeah, you didn't say it very explicitly, but I guess the 6-loop result doesn't obey BCJ, color kinematics duality.
Right,
and
so
the
the
5-loop one also doesn't. Is there a metric for how far away you are? And are there methods to systematically move towards it, or how does that work?
So I will say that the 6-loop one is significantly further away than the 5-loop one, in part because the 6-loop one is written right now purely in terms of contact terms. So everything is, so it's not just cubic diagrams, it's cubic and quartic and quintic and so on. So we don't even have a good way of measuring how far away that is from BCJ because BCJ requires cubic. But the generalized double copy does give a way of measuring how far off of BCJ you are. And so eventually our plan is to start studying what that looks like at 6 loops, but there is an intervening step that we're still working on.
Is there any reason you can't blow up the contacts in one way to make them cubic?
Yeah, so you can make an arbitrary selection. We would like to have a little bit more of a guiding principle to try and get it as close to BCJ as possible. But yeah, just sitting and sort of systematically going through and saying, I want to promote this like this and this like this is possible. You still have to do it 140 some odd thousand times. So it is not a thing we have done yet, but it is a thing we plan to do soon.
Are there other questions? If not, let's thank Alex again.
perspective on ADS amplitudes. Okay, so the next talk is by Agnese BC, and her title is CFT Perspective on ADS Amplitudes. Please.
So thank you very much. Thanks a lot for inviting me to give this talk at the conference. Unfortunately, I cannot be there. It would have been much more fun, so I'm sure you will enjoy the conference a lot. So what I'm going to present today is a way of constructing ADS amplitude, start looking to the CFT holographic counterpart. And mostly what I'm going to discuss is based on a series of papers that I wrote with Giulia Fardelli, a PhD student at Uppsala, and Alessandro Georgiudis, who is a postdoc at Rodina, and Andrea Manenti, who is a postdoc at Uppsala. The three of them are all applying this year, so in case you are interested, put an eye on them. They are all very good. Okay, let me start with the, let me start with the presentation. So what I'm going to discuss is how to use the ADS CFT correspondence together with the conformal bootstrap to be able to construct amplitude in ADS spaces. And what I'm going to present is mainly on the first part. I will review the method to do so. Then I will discuss a bit the structure of whole loop amplitudes, and then I will discuss how to include operators which are higher traces, whereby higher I mean more than double traces, and then I will conclude with some new directions that we are studying and some open problems. So let me start by discussing a bit how to study scattering amplitudes in flat space in string theory. So generically, scattering amplitudes organize in genus expansion. So here I have written a two-loop expansion. So you see here there is a 3-level plus the first correction, which is the genus 1 expansion, and then there are all the higher genus. And so here in particular, I decided to write down a 4-point amplitudes for graviton. So you see that this is generically a function of alpha prime and of the Mandelstam variables, which are S, T, and U, which generically denotes their combination of the momenta of the particles. So in particular, when we have this genus expansion, each of these terms is a full function of alpha prime. And in particular, I wrote here the first term, the leading term, which is called the Virasoro-Shapiro amplitude. And as you see here, there is a full dependence inside this gamma function of both the Mandelstam variables and of alpha prime. And this is, as I said, this is the leading term in flat space. The idea of this talk would be to understand how to do the same kind of computation, but in ADS spacetimes. So when we go from flat space to curved spacetime. In particular, I want to show you something that we can also take another expansion. So in particular, we can take this term here and expanding for small alpha prime, and then you see that we have this kind of structure. So we have the first term, which is the 1 over STU, which is the well-known supergravity limit of the flat space amplitude, and then there are all the alpha prime term. So there is this alpha prime to cube, and then there is this alpha prime to the fifth, and those they correspond to the higher derivative correction. So we see that this kind of expansion is reminiscent to the expansion also of the action when we expand in low energy. And this is something that we are going to see also in ADS. So in general, what we could do if we want to move from flat space to curved space, we can just do what we usually do by using Feynman diagrams. So we can start with the action, which is known, and then we can read off the vertices and compute all the corresponding Witten diagrams. So in principle, this kind of computation can be done, but in practice it is very complicated because there are tons of Witten diagrams to be computed, and there is not really manifest principle to group them. What I mean by that is that generically we need, in order to find, for instance, what I wrote before, what I call the A0 in curved space, we need to compute all the diagrams at once. So we cannot restrict on one sector of them. While in this, in method that I'm discussing today, we will see that there is a kind of principle which allow to group the diagram that we would need in order to compute term by term our expansion. So let me say again, so the idea is to study the dual CFT description, in particular to use the symmetry of the CFT in order to study graviton, and we will see also at the very end of this presentation also gluon amplitudes in a GS, which was denoting the genus expansion also in flat space and an alpha prime expansion. In my talk today, I'm restricting to the leading term in alpha prime, but actually what I'm going to present is valid also in the full alpha prime expansion, and it has been done also in that case. And as I said, the most important point is the fact that I'm going to present the fact a method which relies on the symmetries, and in this particular case, the symmetries are the supersymmetry and conformal symmetry. So let me just start very briefly to recall you how the DSCFT correspondence work, in particular at the level of the parameters, because this is what I'm going to use. So we know that the DSCFT correspondence is a correspondence between two theories. On one hand, we have type 2B superstring theory on ADS5 times S5, and we have two parameters, alpha prime and GS. So we saw already one of them, which is the GS, and then there is also alpha prime, which is related to the string length. On the other hand, on the CFT, we have a four-dimensional n=4 super Yang-Mills with SU gauge group and with SU4 R symmetry. And here the parameters are essentially 2n, which is the rank of the gauge group, and G Yang-Mills, which is the coupling constant of the theory. And in particular, we see that the GS, which already we saw before, which was controlling the genus expansion, is related to n. So if we expand for large n our CFT, we are essentially doing the same expansion in genus that we saw previously. Instead, if we introduce lambda, which is the 't Hooft coupling, which is nothing but g squared times n, this is related to the expansion in alpha prime. So the expansion that I showed you before, where alpha prime is small, is related to the large lambda expansion. And this is actually the setup that I'm going to use. So I'm going to study the CFT in the limit where n is large, and I'm just focusing on the first and the leading order when lambda is extremely large. So you won't see any power of lambda in my presentation from now on. Okay. So in particular, in addition, in the DSCFT correspondence, we have a relation between amplitudes and correlation function. So this was a bit elusive in what I said before, but in particular, we can see that if we have a 4-point correlation function, we can study a 4-particle amplitude in the dual theory. And here I show you how, in principle, one can think about this correlation function and this amplitude, meaning that we have to study a correlator at the boundary to understand, to study the amplitude in the bulk. And in particular, I'm going to focus, as I said, on gravitons. So the dual operator are single trace APPS operators, which have this form here. And so those objects are single trace, as you see from this formula here. And the dimension of this operator is protected and is equal to P in this notation. And I transform under the 0P0 representation of SU4. And in particular, if P is equal to 2, we have this operator, which is the stress tensor, and actually is the superprimary inside the multiplot of the stress tensor, which is this O2, and this corresponds to the graviton on the string side, while for P greater than 2, this corresponds to the Kaluza-Klein modes. And in particular, since I'm interested to amplitudes of gravitons, the 4-point function that I need to study is this object here, where x1, x2, and x3, and x4 are the insertions that I showed you before, so those are the space-time coordinates, while y denotes the polarization of this object, so they are related essentially to this P that you see here. So now what I'm going to use first, so the first few slides that I have is to discuss how supersymmetry enters into the game. So in particular here you see that I just wrote what conformal symmetry is telling us. So we have this prefactor in front of the full function, this function g of u v sigma and tau. This is just conformal symmetry, and in particular we see that I introduce the cross ratios, which are u and v. So those are just combination of points, and we can write them also in these other coordinates z and z bar. So u is nothing but z times z bar, while v is 1 minus c, y minus z bar. We can also introduce some other cross ratios, which are sigma and tau, which are called harmonic cross ratios, and they actually denote again which kind of operator. They are denoting the fact that again we have an operator which transforms non-trivially under the SU4 R symmetry. So in particular, if we use superconformal word identities, we have a few consequences. The first consequence is the fact that this function gu v sigma and tau is a polynomial in sigma and tau, when we define sigma and tau the same way I defined it previously, and also that there is again a superconformal word identities, which is this one that I've written here, and this in particular allow to isolate the contribution to this 4-point function of the protected operator. What that means? It means that essentially we can take the operator product expansion between these two operators here, and inside this operator product expansion, there will be few families of operators. There will be long operators and short operators and also semi-short, but for us they are not very important. But in particular, the short operators which are protected can be isolated from the other operators which belong to long multiplets, which means that they acquire an anomalous dimension, and which are essentially the most important object that we would like to study. So, in particular, using the superconformal word identities that I showed you previously, we can write our G in two pieces. This function G short that I discussed before, so by using the superconformal word identities that I was showing before, it is possible to compute this full function. And then we have this other function, which I denote here by h long, which only depends on u and v because there is only one function, meaning that all the superconformal primaries which belong to long multiplets, they just transform in the singlet of SU4, which means that they don't depend on sigma and tau. Another important point is that we can compute the full function G short because it does not depend on the coupling constant at all. So it can be computed either using the power of the chiral algebra or just going to free theory. So in particular, when I'm going to say that I would like to compute the correlator, I mean that I would like to compute this function h, which intrinsically depends on the coupling constant. And in particular, this h can be decomposed into superconformal blocks in a very straightforward way. In particular, this a is the 3-point function square of two such operators with the superconformal primary transforming under the wrong representation, denoted by a dimension delta and a spin L. And those functions here are called superconformal blocks, and they are nothing but the eigenfunction of the super Casimir operator. Okay, so the idea is to expand now this function h in large N. So again, we would like to mimic the genus expansion. We would like to understand how to build up higher genus correlation function. So we would need to, higher genus amplitude. So we would need to expand for large N our function h. And the idea is to say, okay, imagine I know h0. Can I compute h1, h2, and so on? And the most important point, remember again, that if we would like to study crossing symmetry of this function g, we can write a crossing symmetry relation for h, but this crossing symmetry relation will also take into account the fact that we have this function g short. So this is very important, the fact that we have a g short also on the left-hand side. So in particular, again, the idea is to use crossing symmetry, which includes, again, the knowledge of the G short, and then use the technology of the analytic conformal bootstrap to construct in general HK starting with H0. So if we write them in terms of Witten diagram, maybe for people which are more familiar with Witten diagram, the first part is just corresponds to the disconnected part. So this is pretty simple to compute, while the 1 over n square term corresponds to the exchange and the contact diagram, and the second term is the box, this box here at order h square. And in particular, you can see well from here that the intermediate operators from this diagram is pretty clear, but the intermediate operators are double trace operators, which are built by gluing this O2 that I showed you previously. Now, I would like to very quickly mention how to do that. It would require me a full talk about that, but I would like to be quick on that, just to say that it is possible to reconstruct. There is a full method put forth by Simon Caron-Watt that it is possible to reconstruct the full correlator. I will show in a second what is this C, by knowing the singularity of the correlator, which is encoded inside the double discontinuity of the correlator itself. So you see here the double discontinuity is written as the difference between the Euclidean correlator minus the analytic continuation around z bar equal to 1, and this is just a measure factor that is known. So in particular, if we know how to fix this double discontinuity, we will be able to compute this C delta L, and C delta L encodes all the information that we would like to understand about our correlator, because it has poles at the dimension of the exchange operator inside the OP. Again, remember that those in our example would be the long operators, and it has to have residues which are related to the 3-point function A delta KL, where this delta K here is the dimension of the exchange operator. So now let's try to understand a bit better how to do that in practice. So what we would like to do, we will also expand delta and A at large N and plug everything inside the superconformal block decomposition. We will get this kind of expansion here. And when again we expand for large N, we will have a series of logarithmic terms in U, which will essentially denote the order of N that we have. In particular, at order n to the 0 and n to the minus 2, the only contribution to the double discontinuities comes from the protected part of the correlator. Remember again that we need to use the crossing symmetry, and when we use crossing symmetry, there is a piece which comes from this protected operator, and we will see that actually the double discontinuity of a log V is equal to 0, while this piece that I wrote on the right hand side, which comes from just the disconnected part, is different from 0. So by using this information, it is possible to unambiguously determine H0 and H1. And when we go to order n to the minus 4, there is something a bit more complicated happening, because the protected operators stop contributing. One can compute, as I said before, this function g short exactly, and we see that this stops at order 1 over n square. So we won't have any more the contribution from the protected operator, but there is a term now which is proportional to log square u, then crossed it will be a log square v, which can completely be determined by A0 and gamma 1. That comes from this expansion that I wrote you before, and this can be completely reconstructed from the term n to the 0 and n to the minus 2. So by using now a more complicated machinery, so we need to go back to the formula that I showed you before and compute that integral that I showed you before, but it can be completely reconstructed up to order n to the minus 4. And there are a couple of technical problems. So one needs to solve some mixing problem, because there is more than one operator. So this sum contains an extra index, but this can be done. And there are we did that with Fernando Alda in the past, but there is also a very nice series of paper by this author here, and you can see that it can be interpreted by cutting this square diagram here, and can be written as a sum over all the possible 3-level 4-point function, when the fact that here we have P just is saying that we have to solve this mixing problem. Let me just now try to understand what happens to Eiger loops. So to Eiger loops, we have a few problems. So you can see here, for instance, that in this kind of a diagram, there is only one possible cut, which is the double trace cut. But when we go to Eiger order, there are problems. So the first problem is the fact that there will be Eiger trace operators that start contributing to the double discontinuity, and also that there is a mixing problem to be solved also at Eiger loops. So now let me try to say one very simple term that is contained inside all the Eiger loop amplitudes, which is this term here, which is the highest possible logarithmic term in U. Notice that this is not the full double discontinuity, because indeed, as I said before, the double discontinuity of a single logarithm is 0, but then all the other will be different from 0. And in particular, you see that this term, which is the highest possible log, can be completely reconstructed by knowing the leading term 3-point function and the gamma 1. Now the question that we would like to ask is to which kind of part of the full answer this term corresponds to. And this was what we tried to investigate it. So what we did, we computed this full sum. So you see here there is a complicated sum. We computed this sum. We take the specific limit, which is called bulk point limit, to connect this part of the answer with the full flat space amplitude, and then we compute the amplitude in flat space and compare. This, what told us, it explains to which part of the correlator this function corresponds to in flat space, and we then extrapolated the fact that it has to hold the same way also in curved space-time. And what we found is that this function f of u and v corresponds to these consecutive S-channel cuts to the full ladder diagrams that you see here. So by knowing this function f, we can completely determine these consecutive S-channel cut. So what it means that we are cutting all the propagator. This is pretty obvious because essentially we are doing all the cuts where the double trace operators enter. Okay, so this was part of the result that I want to show. The second part that I will mention in maybe my last 5 minutes, I guess, is how to include also Eiger trace operator. As I said before, the problem is that there are also Eiger trace operators contributing as soon as the n starts, we are probing Eiger n correction, and in order to deal with multi-trace operator, we can follow two routes. One is to study Eiger point function. Some people, for instance, this group of people computed 5-point function, or one should study multi-trace external operators. And this is what we have been doing. So we studied, in order to have the most control setup possible, we studied 4-point correlator of double trace protected operators. So now the simplest possible double trace protected operators are quarter BPS operator, and in particular they are intrinsically multi-trace. We study those kind of operators which have dimension which is related to this SU4 representation. They are scalars and they are multiple trace in this way. In particular, they are double trace. And what we found, so in particular, in order to study this object is very complicated because there is a proliferation of polarization, and also it is complicated to disentangle the contribution of protected operators in the OPE. So we use the chiral algebra to set up this problem. So we studied the protected operators, and actually we saw something very interesting. We saw the fact that as for the half BPS case, through the double discontinuity, it's possible to fix the unprotected part of the correlator, at least the leading order in N. So now we are trying to understand more how to use this information in order to go higher order in N in this setup, in order to use this together with the information that we had for the higher loop to be able to fix maybe a few more orders in the expansion. Let me just end with a paper that is going to appear hopefully soon with Giulia Fardelli, Andrea Manendi, and Chinal Zhu, where we use exactly the same techniques or similar techniques to study spinning correlator in n equal to 2 superconformal field theories. So actually, I said similar because we used mostly superspace approach, but in this case, so those kind of spinning correlators, they are dual to gluon amplitudes, and we study superspace expression for the full supermultiplet. And in particular, we make a connection with the 4-point correlator of the stress tensor supermultiplet in n equal 4, which is the one that I showed you previously. And we found a very nice relationship among many other things. For instance, we saw that the 4-point correlator of currents has this form. This D1 is just a differential operator which acts on X and on the polarization. And also that this was already known, this fact that the 4-point correlator of this can be written in this very nice form. But as you see, maybe all of you already realized that this hints to a double copy relation that we are now currently investigating to find this double copy relation between these two amplitudes. But this is just a trailer of an upcoming paper. Let me just conclude. So what I hope I convince you that we can study amplitudes in curve space by using the CFT counterpart, and in particular, this method relies only on the symmetry of the theory, so it can be applied vastly. It has been applied also, for instance, in ABGM theories and in theories with different amount of supersymmetry. And also the fact that this full program can be, for the case of n equal 4 superior Mills, can be complemented also with integrability result. This is a very promising arena which has just been recently started. There are a few papers, but the idea is to use the full symmetry of the theory in order to study this set of amplitudes. So maybe I'm already over time. Thank you very much for your attention.
Okay, any questions? Well, it looks like everything was admirably clear. All right, so let's thank Agnese again.
Thank you.
And next speaker is Amit Sever.
Should hold this, or you can put it there and then. Okay. So first I want to thank the organizers for letting me present our work here. I'm going to talk about bosonization in three-dimensional Chern-Simons theory. So let me, it's okay. Let me start by introducing my collaborators. This is Barak Gabay from Harvard, and this is Liang Zhong, who is a postdoc at Tel Aviv University. So let me start with some motivation for why we are doing what we are doing. Oh, this is not reacting to the right one. Yeah, this one. Okay, great. So Chern-Simons known to possess a non-perturbative level rank duality. And the statement I want to emphasize that this is really a non-perturbative, and this is why it is very hard to prove. For pure Chern-Simons, this is a well-established duality. But once we couple Chern-Simons to matter in the fundamental representation, this duality is expected to extend to a duality between Chern-Simons coupled to bosons and Chern-Simons coupled to fermions. Now again, because this is a non-perturbative duality, it is a priori very difficult to prove. What I mean by expected means that by now we have a very large evidence for this duality, especially in the 't Hooft-Largen limit. And this comes from the study of correlation function of local operators.
the spectrum of monopoles and baryons operator determine as free energies may be more relevant for this conference, the S matrices. And one of the, I think, interesting open problem would be to connect what I'll tell you about to the conjectured S matrices in these theories, and finally relating some non-supersymmetric dualities to well-established supersymmetric ones. And here I gathered together many people that work on the subject, and sorry if I forgot anyone. So why do we expect such a duality to hold? It turned out that the first evidence for such a duality between fermion and boson in 3 dimensions come from studying pure Chern-Simons theory. We start from the famous paper of Witten from '89. Suppose you study just a simple closed Wilson line in Chern-Simons theory. Pure Chern-Simons theory is a topological theory. And it turned out that in order to define such a Wilson line in the quantum theory and to maintain its topological nature, you have to introduce what is called framing. You have to introduce a small vector along the line that is orthogonal to the line. And in the remaining of the talk, I will consider SUN or UN gauge group and only focus on the planar limit. The planar limit is the limit in which the level of the rank group will take to infinity, while the ratio between the level and the rank of the gauge group, this is what we call the 't Hooft coupling, we'll keep it fixed. This is lambda. Okay? So the weak coupling limit is that lambda is close to 0, and the maximal strong coupling limit is that lambda equal to 1 or minus 1 depend on the sign of k, which is the level of the Chern-Simons theory. So going back to pure Chern-Simons, if you study the expectation value of such, let's say, unframed Wilson loop, you find here some function of the 't Hooft coupling and the level k, but the factor I want to focus on is the phase here, which is e to the I pi lambda times f, which is called the self-linking number. This is the number of times this framing vector wind around the loop as we go around. For example, in this picture, it is equal to 1. So just from focusing on this phase, you see that if f is equal to 1, when I change lambda between the weak coupling limit, which is 0, to the maximal coupling that is 1, I get a phase of e to the I pi. This is why we expect that once we let such a Wilson line end on something in the fundamental representation, it will dynamically interpolate between bosons and fermions, meaning that when I rotate this around, this phase factor would change its statistics. This is something we are going to prove now in the planar limit. So to be more concrete, what we study is Chern-Simons theory in 3 dimensions, coupled to fermions, fundamental fermions, or bosons in the fundamental representation. And these are conformal field theories in 3 dimensions. So to be conformal field theory, you have to tune some coupling near lambda 6 to some critical value. Okay? Talk about these theories, or what we call their double trace deformation with respect to J0, which is the biscalar here, or the bifermion. Okay? This is the relevant deformation of this theory that you can flow to another conformal fixed point. Now, what we'll study is what I think are the most fundamental operators in such a theory. The fundamentals by themselves are not good operators because they are not gauge invariant. The most fundamental operator is some smooth Wilson lining ending between fundamental and anti-fundamental matters, the scalars or the fermions. Let me start with some large N counting. Okay? At large N counting, the matter, only because it's in the fundamental and we have order 1 flavor, only contributed order 1 over n to the expectation value of a closed Wilson loop. However, it contributed order 1 to this, what I call mesonic line operators, these open Wilson lines stretched between a fundamental and anti-fundamental. The double trace deformation that interpolate between these theories and the deformed one only contributed 1 over n squared to the expectation value of a closed Wilson loop, only contributed order 1 over n to the expectation value of these mesonic line operators, but do contributed order 1 to their connected correlation function. Now, since in this talk we will focus on the expectation values of these mesonic line operators, the difference between the theories and their double trace deformation would not matter. It will only enter at the next order in 1 over n. So, because I have a very limited time, Let me start by just enumerating the results, and then I try to explain a bit how we arrived to them and elaborate on them. So the first thing, if you study just, let's say, a Wilson line, a line operators in one of these theories, it will generically experience an RG flow on the line. So the first thing we did is to classify the endpoints of such a flow, what's called the conformal line operators that are a fixed point of the RG flow on the line. The second thing we did is to classify the boundary operator, the operators such lines can end on, as well as the operator that can live on the line. So this is just a classification of all of these type of mesonic line operators. What you want really, in pure Chern-Simons, line operators are topological, but once you couple them to matter, they are no longer topological. What you wanted to understand is what is the dependence of these line operators on the shape of the line. It turned out that in Chern-Simons matter theory, these line operators satisfy a sort of a first-order loop equations. What it tells you is that if you do a small, smooth deformation of the line, what you find is a factorized product of two of these mesonic line operators. You have a smooth deformation, you have a factorized integrated product. I think what we have shown is that just information about the spectrum of the boundary operators and this evolution equation is sufficient to determine the expectation value of these line operators. Okay? This is a sort of a Bootstrap problem on the line. Next, we have shown that the conformal line operators in the theory coupled to bosons or the theory coupled to fermions have the same spectrum under the level rank duality that map the fermionic Tooth coupling to the bosonic Tooth coupling -1, let's say if k is positive, so it's interchanged the weak and the strong coupling. Under this map, they have the same spectrum, and they satisfy also the same evolution equation. Therefore, they have the same expectation values of these mesonic line operators along arbitrary smooth shape. To demonstrate that, we have computed the first, I'd say, non-trivial shape dependence of these mesonic line operators. So suppose you start with some smooth operators and deform it a bit. The operator that deforms a line in a transverse direction is called the displacement operator. And the first non-trivial thing, if you start, let's say, with a straight line, is the two-point function of the displacement operator. Okay? If you do just one deformation, this is 0 by symmetry. If you do two, it's non-zero anymore. So here I draw, it's very hard to see. This is such a straight mesonic line operator adding between two boundaries operators. And to normalize it, I divide by the same thing without the displacement operator insertions. And this expectation value, or this ratio of expectation value, takes the following form. It has some conformal cross ratio associated with these 4 points to the power 2 delta, times 1 over x, which is the distance between two displacement operators. The displacement operator is dimension 2, so this is 1 over x to the power 4. And the only non-trivial factor here is this number here, which is dependent on delta. Delta is the conformal dimension of the boundary operators. These are the boundary operators of minimal conformal dimension. Okay. What we found both from the Bootstrap and from explicit computation, let me mention that this is also the same thing if you do it on a closed Wilson loop. If you insert two displacement operators on a circular Wilson loops, it will control by the same number, same function. We find that it's given by the following expression, where what is delta here, the dimension of the boundary operators, depends on which line operator you are looking at, and if you are looking at the bosonic or fermionic description. But the formula is general, and it only follows from the form of the evolution equation. Mm-hmm. So, playing the remaining of the time, I'll start by describing the line operators in the bosonic theory. Then I quickly describe their dual fermionic line operators. And as time permits, I'll talk a bit about the Bootstrap, even though this was the main part of this work. So let's start with the bosonic theory. And just to simplify notation, I will assume that the level in the bosonic theory is positive, and therefore the bosonic tooth coupling runs between 0 and 1, 0 being the free theory, and 1 being the strongly coupled theory. Well, the dual fermionic theory coupling runs between -1 and 0. The other option is related to this by parity. So line operators in the bosonic theory. The simplest line operator you would imagine is the Wilson line. But it turns out that in the bosonic theory, such a Wilson line has a non-trivial beta function for the scalar bilinear on the line. So it experiences an RG flow. And so this is a scalar. The scalar is in the fundamental. So when I write two of these, think about this as an operator in the fundamental, anti-fundamental representation that you can place on the line. It turns out that the end point of this RG flow on the line is the following operator. Here C is some smooth path, and N is the framing vector that needed to define the Wilson line to start with in Chern-Simons theory. So we see here that we have a condensation of the scalar bilinear in the exponent, and the coefficient up to factor of 2 pi lambda over n have to be plus or minus 1. Both of these are conformal line operators. They are fixed point on the RG flow on the line. Now it turns out that the one with alpha equal to plus 1 is a stable fixed point, while the one that is with alpha equal to minus 1 is an unstable fixed point. And if you change a bit this coupling, it will experience a flow that can go to the alpha equal to 1 or to an almost trivial line operators. So these are the most fundamental line operators in Chern-Simons theory coupled to scalars in the fundamental, conformal line operators. There are also other more complicated conformal line operators that I would not have time to describe. So what are the mesonic line operators? The mesonic line operators are taking such a conformal line operator and letting it end on a fundamental and anti-fundamental at the two ends. Okay? I call them right and left operators. Right is fundamental, left is anti-fundamental. It turns out that in the planar limit, all the operators that can live on the line always factorize into a product of right and left operators. And therefore, once we classify all the operators that can live on the boundary, in the planar limit, we automatically also classify all the operators that can live on the line. The operators that live at the boundaries, they are completely fixed by two quantum numbers. One is the conformal dimensions, and the other is the spin in the space transverse to the line. And for any dimension and spin, there is a unique boundary operators you can place there. So for example, at tree level, if we are in the bosonic theory, this, if you look on the fundamental on the right side, these are just the scalar and its derivative. There can be derivative along the line, this is what's called the fair direction here, and derivative transverse to the line that had to be transverse spin in the plus or minus direction in the plane transverse to the line. Okay? So at tree level, the dimension is just 1/2 for the dimension of the scalar plus the total number of derivatives. But once you go to loop level, this gets loop corrected. Also, it turned out that a straight Wilson line preserves an SL2 conformal symmetry times U1 for rotation in the transverse space. And the operator with the minimal spin here, meaning with no transverse derivative, are SL2 primaries. So what is the spectrum? So it turned out that the spectrum, what is special here is that both the dimension and the spin get loop corrected. Here S, small s, this is the tree-level spin that started its life by an integer. It turns out that the full spin is shifted by plus or minus lambda over 2. Depends if you're talking about the fundamental or anti-fundamental. Meaning that you get a fractional spin. In particular, when lambda equal to 1, you interpolate between if you started with a boson, you end with a fermion, and the other way around. We will talk about the fermionic theory. The dimensions also get anomalous dimension, which is completely correlated with the anomalous part of the spin. Operators with the same anomalous dimension can be related to each other by path derivatives. So what we really care about is the only operator with minimal spin of different anomalous dimensions. The rest can be obtained by them by adding a small piece of the line, basically. So here there are actually 4 towers of operators, 2 on the right and 2 on the left. Here, for example, if I look on the right, there is the operator that started life just being the scalar, have 0 transverse spin, and the operator that has 1 transverse derivative. They have opposite anomalous dimension, and all the rest can build on these 2 by taking path derivatives. So how we arrived for this spectrum, we did it in explicit all-loop computations that I don't have time to describe, you can show that there is a nice recursion relation that the, that the integrals satisfy and solve them explicitly. You see the interesting relation between the dimension and the spin that reminds BPS condition for supersymmetric theories. This is not a coincidence. This relation can be derived by embedding these non-supersymmetric theories into supersymmetric ones. So you see that now, when you consider this line operator ending on the scalar, when we go to lambda equal to 1, its spin become 1/2, and therefore it behave like a fermion. Oh. Wait a second. It doesn't react. Okay. We can ask also what is the operator of minimal dimension that sits on the line. And the operator that of minimal dimension that sits on the line is exactly this biscalar operator, the one that has 0 spin at 3 level. Its dimension is just the sum of the dimension of the right and the left operators. This turns out to be 1 plus lambda, which is bigger than 1. Therefore, this is an irrelevant operator, meaning that the operator we are studying now with alpha equal to 1 is a stable fixed point. Okay? It doesn't have any marginal or irrelevant operators that you can add to the line. Next, we would like to understand what is the dependence of this line operator on the shape of the loop. Okay? So if you consider the expectation value of such a mesonic line operator, we have here a factor that is just fixed by symmetry, 1 over the distance to the power of 2 times the conformal dimension. And this is the framing vector on the right and the left to the power lambda over 2. This is captured the anomalous spin, and this is captured the conformal dimension. And here, standing a function which is a conformal invariant function of the shape of the path that we would like to understand. Okay? To understand it, what we did is try to start with some fixed smooth line and do a small deformation of it. So when you start with some smooth path and do a small deformation, to linear order in the deformation, what you're inserting on the line is what is called the displacement operator. If you look on this equation, the displacement operator by construction is an operator that has dimension 2 to account for the dimension of the deformation and the measure, and spin 1 measuring the transverse direction. We find that the displacement operator, there is a unique operator on the line that has this property. So it is chiral, it is different if you're doing the deformation in the plus or the minus direction, and is given by a product of such right and left operator that in total have spin 1 or minus 1. Now, not something very interesting here. This operator has dimension 2, is fixed by symmetry, but is given by a product of 2 operators. Each one of them has non-zero anomalous dimension, but opposite. And when we multiply them, the anomalous dimensions and the anomalous spins exactly cancel each other. So this equation, now if you plug it into this equation, what you get is what I called before the evolution equation. It's a Schwinger-Dyson type equation. Then when you deform the line, it factorizes into a product of 2 such operators. There is also a boundary equation. We'll tell you what happens when you deform a bit the boundary with a priori unknown coefficient. Given time, I will not expand on it, but we are able to bootstrap it explicitly using the evolution equation and the spectrum. Okay? Basically, it does not get loop corrected. Let me quickly describe the other fixed point, which is the operator with alpha equal to minus 1. Okay? The only difference in the spectrum is that the 2 scalars have now opposite anomalous dimension. And the rest of the spectrum of boundary operators is just the same. So now we are building 4 towers about these 4 operators. The difference is the sign of the spin here that before was minus 1 and 1 here, and now it's opposite. And again, now the operator of minimal dimension is the biscalar, and now it has dimension 1 minus lambda instead of 1 plus lambda, meaning that it's a relevant deformation of the line. And if you start with the operator with alpha equal to minus 1 and turn this operator on, you generate a flow to the operator with alpha equal to 1 or to an almost trivial line operators. So this is done with the bosonic line operators. Let me now quickly go over the fermionic ones. So for fermionic ones, if you now study Chern-Simons coupled to fermions in the fundamental, turns out that just a standard smooth Wilson line is a good conformal line operators. It doesn't have any marginal or relevant operators you can add on the line. So let me jump to the spectrum. The spectrum exactly match the one with alpha equal to 1 in the bosonic theory. For example, what is started in life in the bosonic theory with the fundamental scalar on the right side become one component of the fermion as we take the coupling to be maximal, and the other way around. And the other component of the fermion become the plus derivative of that scalar. Okay. We also constructed the operator dual to the conformal line operator with alpha equal to -1. This was the unstable conformal line operators. But this turned out to be much more tricky and surprising. We jump to the result. It turns out that in the fermionic theory, what you really have to do is to condense the fundamental fermion in the exponent. So you expand the exponent, this line operator is given by segments with a Wilson line between fundamental and anti-fundamental fermions, and almost nothing in between them, and they are integrated. So color-wise, it is like break into pieces, but you can study it, and it turned out to be a good conformal line operator that exactly match all the results of the operator with alpha equal to -1 in the bosonic theory. So here is, again, the map between the operators. For example, just a fundamental scalar becomes just an empty line of this, what you call condensed fermion operator. This looks very strange operator, but it's dual just to a normal Wilson line in the bosonic theory with some scalars in the exponent. We quickly describe the bootstrap and then let's summarize. So the main point of the bootstrap is that the known spectrum of the boundary operators that we have computed explicitly and the evolution equation is sufficient to determine their expectation values. Okay? And the way we've shown that is by sort of a conformal perturbation theory expansion around the straight Wilson line. We add all the possible bulk and boundary operators with arbitrary coefficient, and then we enforce on them conformal symmetry and the evolution equation to linear order around any path. And it turns out that this is sufficient to determine their expectation value in highly non-trivial way. Okay? Well, in particular, this allows us to bootstrap the two-point function of the displacement operator that I presented before, and we also computed it by an explicit all-loop computation. Let me summarize with future directions. So far, we focused on the expectation value of these mesonic line operators. But to really prove the bosonization, the duality between the theory coupled to fermion and bosons in the planar limit, you should also do that for the connected correlation function between them. What we expect to happen, this is something we are working on, is that if you consider, for example, the connected correlation function between two such mesonic line operators, it will be completely determined by the spectrum of boundary operators and the evolution equation as before, and the only new input we have to add is the spectrum of single trace operators in this theory, made of fundamental, anti-fundamental, that is explicitly known, okay? Just an integer. Next thing, we have shown that these properties are sufficient to determine the expectation value of these operators, but we haven't computed them for arbitrary shape. Remember, there is some non-trivial function, conformal function of the path that we would like to find explicitly. And lastly, which was actually our original motivation for this project, we would like to derive the holographic description of these theories. These theories are expected to be holographic to a certain type of parity break-in version of Vasiliev theory in ADS. We have explicit ideas of how to derive that using these operators. Thank you.
Okay, Lance?
Okay. Right. So Lance was asking about the relation to supersymmetry of these line operators. It turns out that any of these line operators, we can, what we call lift, into a locally half supersymmetric line operators in the n equal to 2 Chern-Simons matter theories that couple to both bosons and fermions. But once you put at the end of this operator, let's say, only a boson or only a fermion, and compute its expectation value in the planar limit, if you put, let's say, only boson, it turns out that the fermions decouple. Therefore, it has the same expectation value. And these operators that I talked about turn out to be BPS operators of the symmetry that is preserved by these locally supersymmetric operators in the n equal to 2 theory. So this gives us explicit relation between their dimension and spin, which is the BPS condition for these operators. Surprisingly, the operator, for example, with alpha equal to -1 mapped to a new supersymmetric operator that was not considered before. Thanks.
Other questions? Well, I have a question. I was puzzled by this fractional spin. I mean, the theory started, it doesn't have fractional spins at all. And you put a defect in it and you get these fractional spins.
Yes. Because these fields are in the fundamentals, so by themselves, they are not good local operators, they are not gauge invariant. In order to make a good gauge invariant, you had to make a Wilson line end on them. And Wilson line in Chern-Simons theory, what it does is giving a fractional spin to the operator it ends on, due to its dependence on the framing vector.
So I should think of them as kind of integer spins, but with contributions that are fractional from two different sources or something like that.
By themselves, they are not good local operators, and once you put them at the end of a line operator, they have a fractional spin that interpolate between bosons and fermions as you go from weak to strong coupling.
Other questions? Okay, if not, let's thank Amit again. Okay, our next speaker is Lucia Cordova, and she will tell us about conformal correlators and analytic S matrices.
Okay.
Please.
Yeah, so first of all, I was told to be on this side. I would like to thank the organizers for the opportunity to speak here. It's a pleasure to be at this conference and to get to visit Prague. So I will tell you about this work from conformal correlators to analytic S matrices that we put out in this paper with Elvang and Miguel Pablos, who are also at École Normale in Paris. So the main idea of this project is to extract non-perturbative information about S matrices from the flat space limit of conformal correlators. And this flat space limit was proposed in this paper here by this gentleman. And the idea is that these S matrices and conformal correlators are related through rigid holography. So we can put our QFT in some ADS background, and this induces some conformal theory at the boundary, so in one less space-time dimension. And then using the usual holographic dictionary, we have that the masses of the particles in the bulk are related to the dimensions of the operators in the conformal theory, and where the radius of ADS appears here on the left-hand side. So now, if we want to recover flat space physics, what we should do is to take this radius to infinity, which in the conformal theory side means that we're taking all dimensions to infinity as well. Moreover, since we're keeping the masses fixed in this QFT side, we should take these ratios to be fixed as well. So one motivation to study these flat space limits is to explore this very rich interplay between S matrix and conformal bootstraps, so that the ideas and methods that one uses on one side might lead to new insights on the other side. And another motivation is to try to understand better the analytic properties of S matrices. So in various investigations, including the S matrix bootstrap, one usually assumes some analyticity, which is not fully proven. So the idea is to take the conformal correlators that are in much better control and try to say something about analyticity of the S matrix from them. Okay. So what I will be describing here is the simplest scenario where we have a 4-point conformal function in a 1D conformal theory where we have identical operators, and then we map this to a scattering amplitude in 2 space-time dimensions of 2 particles going to 2, again with the same masses for the external legs. So the 2 functions I will be talking about are this g of z, which appears in the 4-point function here, and this z is a cross ratio made out of the difference of the positions of the operators. And on the S matrix side, we have this S matrix, this scattering amplitude S of Mandelstam invariant S, which is a 2-to-2 amplitude, and S is the center of mass energy. So now the goal of this talk would be to understand how we start from some function that looks like this. So it has some branch points, as you can see from the OPE, at 0 and 1. And then by taking these flat space limits in which the dimensions go to infinity, we recover some other function, which is more complicated. So it also has some branch points, as you can see from the 2 particle thresholds, but it can have other non-analyticities, like simple poles for bound states, or more complicated things for anomalous thresholds. And even though I introduced this flat space limit with some holography, we will not be putting a specific UFT in ADS. Rather, what we're trying to do is to try to understand what are the general properties for these amplitudes, purely from CFT, from a CFT perspective. So our starting point will be this position space map proposed by this gentleman here. And this relates the positions of the operators in the CFT to the momenta of the particles in the S matrix. So for this very simple scenario that we have, it just relates the cross ratio Z to the Mandelstam invariant S in these forms of 4 times 1 minus Z. But crucially, this limit is not well defined for any Z. So it's only well defined for some region here I'm calling D. So what we are proposing here is to perform some analytic continuation. So first, we take this limit where it is well defined, and then we analytically continue into the full complex plane. So this is what I denote by this curly F, and what I will call flat space limit from now on. Let me get some water. All right, so to see how this limit works in a very simple example, let me review how it works for generalized free fields. So these are free fields in ADS, and if we take the correlator, this will be given only by the 3 possible weak contractions. So it's given by this expression here. And just to review some notation, let me also use the OPE expansion. So we have a sum over the GFS spectra. So we have these double traces dimensions, 2 delta phi plus 2n. Then we have the OPE coefficients squared, which for this here are these ratio of gamma functions. And then we have the conformal blocks G, which in 1D are these hypergeometric functions, and they're just kinematic variables. So as you can see clearly from this first expression, this large dimension limit would give 1 or infinity. So it gives this plus minus 1, plus these other 2 things that either give 0, if we are outside these 2 unit disks, or infinity if we are inside. So in this case, the analytic continuation is trivial. We're just continuing a constant. And we get plus or minus 1 in the end, which is precisely the S matrix for free theory. And now the idea will be to understand how this would work for more general correlators. So for this, I will use 3 main tools. One is Polyakov blocks. We have also extremal functionals. And the third one is bounds on the correlator and OPE coefficients. So the first one is Polakov blocks. And as I said, using the OPE, we can expand the correlator in this way, using conformal blocks. But one can also do this expansion in terms of some other blocks called Polakov blocks, which make crossing symmetry manifest. So they satisfy this property. And you can get them, for instance, by computing the crossing symmetric sum of Witten exchange diagrams, which has this decomposition in terms of conformal blocks. But what we will use really is a relation to a certain type of extremal functionals that I will review next, called master functionals. So we can write them down in terms of these analytic functionals, omega. So this is all we need about Polakov blocks. Now, let me review these extremal functionals. So these make their appearance in the conformal Bootstrap. And there, what we're really trying to do is to solve the crossing equation. So g of z equals g of 1 minus z. And we can rewrite using the OPE this crossing equation in this way, where this f is the crossing vector given by the difference of the conformal blocks. So if we want to extract information about this crossing equation, one thing we can do is to act with some linear functionals. So these functionals omega acting on the crossing vector will give some number. It could be, for instance, the crossing vector evaluated at a point. Here we will use something a bit more sophisticated. So we will be integrating these crossing vectors with some kernels f and g. And these kernels define the functional for you. So having these functionals, what we can do is act on this crossing equation. And this gives us some sum rule, which we can use to constrain the CFT data. So to get the dimensions and OPE coefficients of the theory. And something to notice here is that for unitary theories, these A's are positive since they are OPE coefficient squared. So one way in which we can constrain this data is by playing with this positiveness. So for an example in a cartoon, let us think of a functional whose action looks like this. So for different dimensions acting on this crossing vector, it will give something positive above certain dimension or negative below. So then this sum rule will read as this. So we have some negative terms and some positive ones, and they should give 0. So if we have negative plus positive, it's fine, we can get 0. But imagine we are in a situation where the theory has operators with dimensions only on this blue side. So then we can immediately rule out this putative spectrum. And some other thing we could try to do is to put bounds on some OPE coefficient. So for instance, if we are trying to bound the OPE coefficient for the operator with this dimension delta B, and we have one other operator here in this negative region, say the identity, since all other operators would be in this blue region, you can immediately get this bound on the OPE coefficient. So, okay, this is a crash course on functionals for CFTs, but the punchline is that different functionals that here will be defined through these kernels lead naturally to different bounds. Okay, so now let me discuss the master functionals. And these functionals were constructed in this paper, and they are built so that you get bounds on the correlator itself. So they bound the correlator at a given point W. And this bound reads as follows. So this G bar is a subtracted correlator in which we remove the contributions from operators below 2 delta phi, which I will call threshold because it's like the 2-particle threshold in the S matrix. So the subtracted correlator is bounded by above by the generalized free boson, and below by the generalized free fermion. So as I said, these functionals are defined through their kernels, which need to satisfy various equations, which in general are very hard to solve. But for delta phi going to infinity, there's an explicit solution to them. and they take the form of this very simple Cauchy-like kernel. So we will use this in the following. And also, as I mentioned, there's a relation to Polyakov blocks. So we can write them in terms of this functional action, which could look like this for some operator above 2 delta phi, and where we have this integral with a conformal block and this kernel G of W. So one last thing that was proven in this paper and we will use is that with these functionals, one can derive a dispersion relation for the subtracted operator, which reads like this. Again, with this kernel, which at infinite delta phi gives you this Cauchy-like structure. Okay, and now the last element is bounds on OP coefficients. We already saw the bound on the correlator. And for operators below this threshold 2 delta phi, it was already figured out in this paper that one can use certain functionals called sign-Gordon functionals to see that the OP coefficient for some operator with dimension delta B, with this ratio with their free theory counterpart, in this limit of large dimensions, is bounded above by the sign-Gordon coupling, which, okay, is related to the sign-Gordon's matrix, but it looks like this for different delta Bs. So you see that for almost any delta B, you have some bound, except, of course, this point 2. So whenever we have this relation between the operator we're trying to bound and the external one, we lose this bound on its OP coefficient. And something else that might happen is that if we have crossing symmetric pairs of operators, basically because the functional action is antisymmetric around this point 2, then we would also lose the bounds as these contributions might screen each other. So a simple way to ensure that we always get these bounds is to say that the theories we're describing have some gap. So that is the first operator after the identity should have dimension greater than square root 2 delta phi. Okay, so this is below threshold. Now, above threshold, we can get it directly from this bound on the subtracted correlator. So in this large delta phi limit, it takes this form, which basically tells us that the OP coefficients are in some average sense the same as the ones for the GFF. So this function n here arises from the large delta phi limits of the conformal blocks, and is some Gaussian centered around square root s with some width square root delta phi. Okay, so now we have everything we need. Now let me sketch the main idea of what we get. So something we see is that this flat space limit separates nicely into two different parts. One comes from the sum of operators below this 2 delta phi threshold, and another one of operators above this 2 delta phi. So from this second one, we get an analytic function in the cut plane, as we can see from this dispersion relation. But really, the more interesting part comes from this sum, and this is how we can get all the non-analyticities like bound states and anomalous thresholds. So one term in this sum we already saw. The Polyakov block for the identity is simply the GFF correlator, and we saw that the flat space limit of that is 1. So what about other operators in this sum? So if we take a single Polyakov block below 2 delta phi and take this large delta phi limit, we see that we roughly get 2 contributions. So using the master functional for the Polyakov blocks, we have a part that looks like this. So we have an integral with these kernels and the conformal block, and then another part which are separate conformal blocks. So this will give either 0 or infinity in the complex plane, and this will give a finite piece that will actually become the bound state pole. So this integral, one can evaluate it using the saddle point for the conformal blocks, So it's basically given by the kernel evaluated at this saddle point, given by the dimension of the operator. And we have, of course, the OP coefficients. So this will give you these poles, and then this other part gives you infinity inside these blobs and 0 otherwise. And as we saw in the GFF example, the flat space limit will be basically getting rid of these blobs, of these divergent pieces, so that the analytic continuation gives you only these poles. And then you see it clearly using this map between the cross ratio and the Mandelstam S, that you recover the bound state for the S matrix. So where the position of the pole is related to the dimension of the operator, that is the mass of the bound state, and the residue is given by the OP coefficients. So this is one example of how it works, but in general, what we find is the following. So starting from this decomposition in terms of Polakov blocks, and separating the identity below threshold and above threshold contributions, we get in this flat space limit 1 from the identity Polakov block. Then this sum below threshold becomes an integral over ds prime. This rho here is given by some average of the OP coefficients, as we saw for the bound state coupling being related to OP coefficients. And these kernels here, which are some Cauchy-like kernel, come from the functional expression for these Polakov blocks. And similarly you have another contribution from the states above threshold. So this is an important result because basically we're recovering the analyticity properties of the S matrix in terms of the CFT data. We're not stating first dispersion relation and then figuring out, but really deriving this dispersion relation. And it is also crossing by construction. So we have seen how this works in various perturbative checks. But something else we find about these S matrices is that they obey unitarity. So for physical values of the energy, that is S above 4, we can use this phase shift formula. So it's the OP expansion for Z less than 0. For which the operators below 2 delta phi are suppressed. So we actually get this function here, again, where this n comes from the large delta phi limit of G. And if you remember this bound we found on the OP coefficients, we clearly see that then the S matrix at physical energies is bounded by 1. So we recover unitarity. Okay, so are we actually done? Did we solve everything? No. And this is because in order to derive this dispersion relation, we needed to put some gap so that we always get bounds on the OP coefficients. So what happens if we lose these bounds on the OP coefficients? And as I will argue, this gives rise to anomalous thresholds. So these anomalous thresholds are extra singularities in the scattering amplitude that one cannot easily interpret as some intermediate state. So one can get this using Landau diagrams, which are Feynman diagrams where you put all particles on shell. And critically, you cannot write these Landau diagrams unless there's a specific ratio between the masses for all legs. So in this case of the triangle and box diagrams with some internal mass M2, you can only draw these Landau diagrams when M2 squared is below 1/2. So our claim is that these anomalous thresholds are related to the unboundedness of the OPE. So let's recall how we get some unbounded OPE. It was either when we're touching this point 2 here in this ratio of dimensions, or where we have crossing symmetric pairs. So going back to this inequality here, we see that if M2 squared is below 1/2, the two particle states associated to this M2 will have this relation here, which when we have the equality, they precisely touch this point in which we lose a bounds. And for the inequality, we would be in this situation where we have positive and negative contributions, so we lose the bound. And yet, another way of seeing that we can actually get unbounded OPEs is through these Fourier solutions to crossing. So basically, below certain gap, one can add solutions to crossing which have 0 flat space limit and positive OPE coefficients. So an explicit example is this function here, which for some gap has positive OPE coefficients. So the idea then is that if we start with our initial correlator and sum these Fourier solutions to crossing with some coefficient, then we can get some arbitrarily large and positive OPE. So to see how this works in an example, this is the last thing I will review. Let us see how this works for the box diagram. So what we're proposing here is that we can write some dispersion relation with some density, and this density in the CFT side is related to this limit of OPE coefficients. So these OPE coefficients would come from this box Witten diagram. They're not super easy to compute, but one can do it numerically. And on the flat space limit, we should recover the discontinuity for this box Feynman diagram, which, okay, you compute with Kotkowski rules. So what happens in the safe region, where M2 is bigger than 1/2? You see, in black, we have the exact result from the flat space limit, and in blue, these OPE coefficients for some large but finite delta phi, and you see that they match exactly. So what happens instead when you're in this anomalous region where we lose these bounds? So from the flat space, we have now this curve here, and we should also get some delta function contribution because this would give rise to some extra pole in the amplitude. And what we see if we compute this for this M2 is that the densities match for some range of S, but the CFT1 has some bump which grows with delta phi. And something curious that we found is that this general form of the bump matches the one you would get from these Fourier solutions to crossing. So this gives us a hint that by thinking of these solutions to crossing, we might be able to recover the actual singularities of the anomalous thresholds. So I will end with one-line summary. So we were able to find analytic crossing and unitary S matrices in 2D from 1D CFT correlators. And I didn't have time to talk about it, but we also saw a very nice connection between these extremal functionals in CFT and the dual S matrix Bootstrap. And we also have some results about extremal S matrices. But something for future directions would be to clarify how to get precisely these singularities for the anomalous thresholds, various generalizations like doing mixed correlators, higher point functions, and of course higher dimensions. And another interesting question would be to understand which CFTs give rise to iterable theories. So thank you for your attention.
Any questions?
Sorry, I cannot hear. I didn't hear. One of the collaborators said that the anomalous threshold.
I thought that Miguel had a paper that says that the anomalous thresholds are in the kinematical region. It's called bad kinematical regions, where the map between the boundary and the bulk S matrices break down due to long propagation in ADS.
Right, so if you see it from some Witten diagram perspective, yeah, it matches with some different saddles that you would get in IDS. But here we're trying to forget about this part and really see how they arise only from CFT. But, okay, one connection to this superior solution to crossing is that this specific function I was writing down, you can interpret it as some diagram in some Witten diagram with some like triple trace structure. So yeah, it's still an open problem, but yeah.
Lance?
That was very interesting. What do you think are the biggest hurdles to pushing to higher dimension?
Well, I know some people are working on it, so Bolt and Chern. And from this functional perspective, these functional kernels are not known. Yeah, as soon as you go from 2 to higher, things are way more complicated. But yeah, some people are trying, but I think they're not using this functional, but something else.
So I want to ask an analogous thing about generalizing to higher than 4 points, because in conformal bootstrap, we think that, you know, but looking at all the 4-point correlators, you can get all the constraints you want, but from the S-matrix perspective, it has been very hard to, you know, but are there conceptual obstacles in extending this to 4-point correlators involving multi-trace operators and so forth?
Are there some obstacles to doing higher point functions in the CFT? Or, sorry,
yeah, but specifically, I'm asking about, you know, with the external legs being the multi-trace operator, so that you can hope to relate to some higher point,
yeah,
or 2 to 3 and so forth.
I have not thought too much about it, so in principle, no, but for sure we will find something in the way. But yeah, it's an interesting thing, something we should explore, because as you say, in the S-matrix, it's really hard to go to higher points.
Thank you.
Okay, I don't see any other questions, so let's thank Lucia again.
All right, welcome back for the last session of today. So while the last people are sitting down, I'm gonna abuse my privilege as the chairman to show you one advertisement about the future program that we're gonna have at Nordita. So next summer, at the best possible time of the year, right after midsummer, June 26th to July 21st, we're gonna have a program, a 4-week program at Nordita. And I show you some picture of Stockholm. There's the old Nordita building. That is the new one. It looks maybe a bit grayer, but it's brand new facilities, so it's going to be nice to explore those. And so that's a 4-week program. And then after that program, we're going to have a focus event, which is from a workshop, a conference called From Scattering Amplitudes to Gravitational Waves. So that's 1 week. So that's the last week of July. And the week after that, Amplitudes at CERN Summer School is going to start, so it's right back to back with some other events. And so there's some topics that you have there, and also you can see who are the organizers. So I hope some of you are interested in applying for this program. And I should also mention that the minimum stay, if you're approved, is 1 week. So if you have a busy summer, you could probably squeeze in a week at this program. All right, so having said that, we should then go to the next speaker. So maybe you can go to Henriette's slides. All right, so we're gonna hear from a remote talk by Henriette Elvang. She's calling in from University of Michigan, and she's gonna tell us about bootstrapping C-theory. Please go ahead.
Thank you so much, and thank you for the invitation and for putting up with having a Zoom talk all the way across the oceans. So I'm going to talk about bootstrapping C-theory. Here's an outline. I'm going to start out with reviewing ideas of the KLT double copy bootstrap and the results we had last year at 4 and 5 point. And then I'll tell you about new results that enter at 6 point, where factorization plays a major role. I'll then tell you how that helps us bootstrapping C-theory. And then we get to ask, where is string theory in this picture? Everything in this talk will be at tree level. So when I say amplitude, I mean tree level amplitude. So the KLT double copy bootstrap is the idea of investigating the fundamental structure of the KLT double copy and how it may generalize, in particular in the context of EFTs, but not limited to that. So this was work that came out last summer, and the setup is the following. So the KLT double copy relation can be looked at as a product structure, a product rule that takes field theory amplitudes and say Yang-Mills theory, and double copy them multiplicatively with amplitudes in another copy of, so it could be Yang-Mills theory of another theory. These are color ordered amplitudes, and you have to sum over the color structures of these products with a certain kernel, which is a rational function of Mandelstam variables. This is known as the field theory double copy kernel. And the output of this, in case we have Yang-Mills theory and Yang-Mills theory, is famously that you get the graviton amplitudes. Now, this came originally from the KLT string relations, where what you're double copying is really the same type of multiplicative structure, but open strings double copied to closed strings. And in that case, the kernel is a function, again, of Mandelstams, but with now an alpha prime dependence. So this is the string theory double copy kernel. And you sum over the same number of color orderings, some subset of color orderings that you choose. And the output is independent of which choices you make for the color ordering. So it's really a map on the space of field theories. The question we can ask is now, suppose that we take and think about the string theory, you can think about this as Yang-Mills plus high derivative corrections controlled by alpha prime. But we could also look more generally and say, what if I look in a low energy bottom up effective field theory point of view, and I take Yang-Mills theory plus high derivative corrections with say free Wilson coefficients, and I try to double copy that to get gravity with high derivative terms. What is then the most general kernel that I can use there to get the most general result in the output? It's clear that the string theory kernel in the alpha prime expansion has alpha prime terms that are cleanly attuned to what the open string is. So if we generalize the input on the Yang-Mills side, then we should presumably also generalize the kernel. So that is the setup. So we're basically asking, what is that most general kerning from a bottom-up EFT point of view? So let's first review what is the relation that we know, what do we know about the field theory KLT kernel? So one way to describe it is that it comes in as the inverse of any n-3 factorial by n-3 factorial submatrix of 3 amplitudes of the cubic biadjoint scalar model, which I'll denote BAS going forward. This was discovered by CHY. And basically the BAS model that we're talking about here is a model with a single scalar that comes with 2 adjoint indices. It has adjoint indices under 2 non-abelian groups. And then it just has a simple cubic interaction term that's controlled by the antisymmetric structure constants of those groups. Okay, so that's all it is. Now, if we then think about the string theory kernel, Sever found out that that can be thought of as the inverse of another set of n-3 factorial by n-3 factorial submatrices of some kind of amplitudes, but they really are amplitudes in the alpha prime expansion. And there they become cubic biadjoint scalar model plus very specific higher derivative terms that are controlled by the alpha prime expansion of the string kernel. So there's sort of they're definitely a local model with high derivative terms. It looks like BAS. And then the leading order corrections are 2 derivative terms. Then there are 6 derivative terms, but you can sort of see that it skips the orders. There's no phi to the 4. There's no d to the 4, phi to the 4. So there's very specific terms. And of course, these coefficients here also have some dependence with some pi's and so on that go in the numbers. So what is the setup? The setup to look at is to assume that the most general EFT KLT kernel you can have is likewise an inverse of some submatrix of amplitudes of the same dimension as before that starts out with cubic biadjoint scalar theory, but then instead of having the specific high derivative terms that you get for the string kernel, then you look at a general ansatz with all the general possible high derivative terms you could have in a biadjoint scalar model like this with higher derivative terms. So then you could just start adding terms. For example, you could add a phi to the 4, but you quickly encounter a problem, which is that the kernel that you produce does tend to give rise to spurious poles. And of course, that's something that it shouldn't do, because then the output of the double copy wouldn't be the matrix elements of some local theory, the amplitude of local theory. So you want to make sure that you have some suitable rules for adding higher derivative terms in the most general form here, such that you do not spoil the desired properties of the kernel so that the output remains a nice local amplitude. So what are those rules? Well, those rules we propose are encoded in the KLT algebra. And the idea here is the following. If we look at the standard field theory double copy, then it has an identity element. So first of all, we can think of this as a map from a product of field theories into a new set of field theories. And we can write this multiplicative table with some examples. So Yang-Mills times Yang-Mills gives gravity. We can add supersymmetry. We can include chiral perturbation theory. And so, for example, take chiral perturbation theory times Yang-Mills gives the Born-Infeld model, and so on. If we include in this picture the biadjoint scalar model we just discussed, then it turns out that that acts as an identity element in this multiplicative table. So that means that there is something that we call the KLT algebra, which is basically the statement that the biadjoint scalar model is the identity when the product rule is defined by the kernel, which is written down as the inverse of these biadjoint scalar models. Okay, and then precisely this identity, this whole thing here is the algebra, but precisely the basic identity that 1 has to equal 1 times 1 becomes an identity that links the kernel, namely the double copy kernel, what defines the product rule, to the inverse submatrices that I just described before, namely the inverse submatrices of the amplitudes of the biadjoint scalar model. These other relations are also important, and we'll discuss them shortly. So the proposal we have is that we take the KLT algebra as a fundamental property, and then we see where that takes us. Then this 1 equals 1 times 1 becomes a bootstrap equation. You start modifying the biadjoint scalar model, which is the identity, with high derivative terms, but in such a way that this identity holds. That turns out to become a bootstrap that requires the high derivative terms to only be of a certain form and links higher derivative terms of, links the Wilson coefficients of some of the higher order terms to some lower terms. So it gives a nice way of defining what is the most general way to modify the biadjoint scalar model with high derivative terms such that it is still an identity under a suitably given product. Then once you have solved your bootstrap, you have your identity and your product rule. Then you can apply it to say, what does that imply on the amplitudes say Yang-Mills plus higher derivatives that goes in on the left and the right so that these identities hold. In the standard approach, where we're working with the kernel of the bi-adjoint Taylor model, so field theory kernel, these relations then encode the KK and BCJ relations. If you work with the string product rule and the string identity element of Misera, then you find that these relations here encode the string monodromy relations. And so when you generalize the identity and the kernel, these relations will then become some generalized versions of KK-BCJ relations, a subset of which must be the monodromy relations. Now, it turns out that when you look at the Bootstrap equation, it becomes equivalent to the statement that if you look at the doubly ordered tree-level amplitudes of this identity model, then you can, because you have a cyclic trace from the single trace parts that could give you the trace structure, then you have n-1 factorial independent orderings for each, let's say, the left sector and the right sector. So you have this n-1 factorial by n-1 factorial matrix of tree amplitudes of the identity model. And this condition that 1 equals 1 times 1 is precisely the statement that this matrix cannot be full rank, but it must have rank n-3 factorial. We call this the minimal rank condition. Okay, so let's see how this works at 4 point. So at 4 point, we have 6 independent single trace color orderings. That means we can make a 6x6 matrix of doubly ordered tree amplitudes for the identity model. And so this I encode here. This is my 6x6 matrix. And it turns out that using cyclic symmetry of the trace and momentum relabeling, I can express all 36 matrix elements here in terms of just 3 different functions that we'll call F1, F2, and F3. F1, F2, and F6. So F1 is just the one where you have the same color ordering. In F2, you have switched the ordering of 3 and 4 in the last element. And in F6, you have reversed the trace structure in the last entry. If you look at a general matrix of this form, it will have full rank, so rank 6. But when you impose that it should only have rank 1, which is n-3 factorial for n equals 4, then it turns out that there are 3 simple relations that ensure that that happens, that ensure the rank 1 condition. One says that F1 must be fixed in terms of F2, and that F6 must equal F1. F6 equals F1 just says that there's a trace reversal property. Now F1, having the same orderings here, has to be a cyclic function of the Mandelstamms, and that is ensured in terms of the function F2, so long as F2 satisfy this relation down here. And so all that put together, you just have to solve these conditions here, then you have a rank 1 system. This is solved by the BAS model, but if you put in generic higher derivative terms, you don't necessarily get rank 1. Instead, you can put in an ansatz for F1 and then fix what coefficients you have to have in your ansatz such that this equation holds. And you also have to ensure that no spurious poles show up in F1 when you express it in terms of F2. So here's what we do. We start with some ansatz for F2. That is the most general one we can think of in a local theory. It starts with BAS. Then there's a phi to the 4 term. There are 2 possibilities for the d squared phi to the 4 terms, and so on. We write down all the possible options. Then we impose this Bootstrap equation for F2. And we impose that no spurious poles arise in F1. That condition, no spurious poles in F1, requires that A00 and A22 are vanishing. Actually, all the elements of just the pure S parts will have to vanish. Pure S polynomials have to vanish for the even powers of those. But it also imposes other constraints, such that these 2 coefficients must be the same, A20 and A21. And then you get a general solution like this. There are no constraints at the cubic order. At the quartic order, there are in principle 4 different terms, but one of them is fixed in terms of the other ones. There are more constraints as you go to higher orders. So you can write down to as high order as you desire in the derivative expansion by just solving order by order the Bootstrap equations. And that gives you the most general solution. Let's compare that to what you get for the string, the inverse string kernel. So Misera found that this can be expressed, the F2 function can be expressed in terms of -1 divided by sine pi alpha prime s. And when we expand this in small alpha prime s, then we find the leading order is the BAS model. The order s is going to be the 2 derivative term. the order S cubed is going to be the sixth derivative term, and so on with appropriate coefficients here just schematically indicated. It's clear that this only has odd powers in S, and it's clear that it doesn't depend on T at all, or U for that matter. So compare that with the general bootstrap. We see that the general solution for the 4-point bootstrap is way more general than the string kernel. All the things that are crossed out here in red have to vanish for the actual string solution. So it looks like 4-point bootstrap gives a much more general result than the strings kernel. Of course, we have to be aware that once we go to higher point in the bootstrap, we have to solve this equation again, that the rank condition now at 5-point. And at 5-point, it has to know about 4-point because there are factorization diagrams that takes the cubic biadjoint together with the new local 4-point terms. And then, of course, you have to add the local 5-point terms as well. To solve this equation now at 5-point requires that you look at the 24 by 24 matrix of all 3 amplitudes with our 4-point input as before, a general ansatz for the local counter terms, and then impose on that it has rank 2. So we can solve this to high order, and we find no constraints whatsoever on the 4-point coefficients. There's also freedom starting in the local coefficients, namely from these contact terms, starting at Mandelstam order cubed. But what happens at 6-point is more interesting. So, of course, there are a number of different factorization diagrams that enter at 6-point. And here I'll just focus on 2 kinds, but of course there are many others. So this one has a 4-point input right at the middle, and then 2 3-point vertices from the biadjoint scalar part. And this other diagram is the factorization into 2 4-point vertices. Now let's look at some power counting for this. Here S will just denote generic Mandelstams of various kinds, but we'll just use it as power counting. So the 4-point vertex here, as we learned, it starts at order S because there was no phi to the 4th term allowed by the bootstrap at 4-point. So we have something that starts at S, and then we have S squared, S cubed, and so on coming in. The 4-point vertices here, they also enter starting at order S. And so this diagram only starts to contribute at order S. This means that the other type of diagrams of this sort here, of course, there are different topologies of those too, they have to sort out by themselves, starting at order 1 over S, where you get information from 4-point here. An interesting thing that was one reason Alan, my student, started investigating this was that there's no way of absorbing any problems or any adjustments, make any adjustments in the ansatz from local 6-point counter terms because they start at order 1 over S. So it really just has to work or impose conditions on these coefficients A10 and A11 that we had before at 4-point. It turns out that it solves, it doesn't impose any conditions whatsoever on the 4-point coefficients, it just goes as it should. Now at order S to the 0th, then there are local terms, and they could absorb, they will be non-zero in general, and they can actually, in fact, totally fixed by the A2I coefficients that sit here. And again, there's no contribution over there. So that takes care of itself, these type of diagrams. And then the plot thickens, we get to the cubic order from the local input, that all gives an order S to the 1st. These have linear coefficients in A3s from this type of diagram, but this diagram now starts kicking in with coefficients that are quadratic in the 4-point input. And in fact, solving the 5-point bootstrap at this order imposes relations among the coefficients of the cubic polynomial terms in the ansatz at 4-point to those from the linear polynomials, but they are quadratic in those, okay? And in fact, all of the 4 coefficients that were free at 4-point and 5-point bootstrap get completely fixed. This is how they look. This is what they fixed to be. G is the coupling of the biadjoint scalar model, and A10 and A11 were the coefficients set from the 4-point bootstrap. And now that's related there. How does this relate to the string? That should, of course, be a subset of the solution, the string kernel. Well, if we take A10 to 0 and A11, but just matching the terms that are linear and Mandelstams, and plug that in here, we see that all 3 coefficients here end up being 0, and the last one give the string theory result right on the nose as it should. Going to the quadratic order, we'd have to set A20 to be 0, 2. Now we can continue this 6-point bootstrap to higher orders in Mandelstams. And at the quartic order in Mandelstams, it turns out that all the coefficients are fixed except 1, which is I can pick to be A40. And to match to string theory, I have to set that one to 0. At the quintic order, everything is fixed. And it matches string theory when I just pick those lower coefficients. At the 6th order in Mandelstam's, everything is 6 except A6, 0. I set that to 0, and everything else is fixed in terms of the lower terms. So now you see that from the 6-point bootstrap, we're narrowing ourselves in much more on the string theory result. We have much, much less freedom at 4-point than we had before. So does that mean that we can then bootstrap the string theory kernel? You might think perhaps if I go to even higher point in the analysis, perhaps there will be some relation, say, between the A1 coefficients and A2 and A4 and so on. That turns out not to be the case, and for a very good reason. And to see why, we need to take a little detour into a different corner of the KLT landscape. So a different corner of this double copy story, which of course is very vast, there's C theory. And it was found by Mafra and Slaughter and Stieberger that you can express the open string amplitudes in terms of a double copy relation that takes Yang-Mills amplitudes and double copy them with the standard BIS kernel. And this is Yang-Mills without any high derivative terms. You double copy it with the amplitudes of C theory, which C theory amplitudes are the result of the string disk integrals. So those integrals come naturally equipped with two different orderings, one from the insertions along the edge of the disk, and then a second one, which come from the integrand, as you can see here. So those are sigma and rho. And of course, you can see the alpha prime dependence and the Mandelstam dependence up here in the numerator. So if we translate this into the language that we just used, we see the open string amplitude with color ordering C. That C color ordering comes from one of the orderings in the C amplitudes. And then the other ordering in the C amplitude participates actively in the double copy in the sum here over the usual n-3 factorial color orderings, and you double copy with Yang-Mills. Now, it's important for this double copy to work that the result of the double copy is independent of which of the color orderings I choose to sum over here. It always has to give the same answer. And that property is ensured by, in the standard double copy, by the KK and BCJ relations. So that must mean that in order for this to really work, then the C theory amplitudes have to obey the KK and BCJ relations on the color ordering A that is participating in the double copy. Otherwise, there could be dependence on which choice I make for the sum here of the sum color orderings. So in the algebraic sense, this means that the C theory amplitude must obey this left set of identity elements, where this is the standard BCJ double product kernel, and this is the BIS theory amplitudes. But it doesn't necessarily have to obey that from the right, because C doesn't participate in the double copy here. It's just inherited by the right-hand side in the open string. Now, one way, it turns out, to encode the KK-BCJ relations is in terms of null vectors. And it says that there's a set of null vectors for the matrix C of amplitudes, such that when you sum over all the n-1 factorial color orderings, you get 0. But then it says that this big matrix of all the C tree-level amplitude, or the C amplitudes, then that says that they have to have n-1 factorial minus n-3 factorial null vectors. So this matrix has to have all those null vectors. But if it has all those null vectors, it says that it's a matrix that indeed has rank n-3 factorial. And because the bootstrap equation 1 = 1 × 1 was a rank condition, that must mean that the C theory amplitudes solve the bootstrap equation. So because it solves the bootstrap equation, C theory could define its own kernel if it wanted to. It would satisfy a relation like this. And in fact, in our paper from last year, we did notice that C theory solved the 4-point bootstrap. Okay, so C theory must be a special case of the generalized KLT bootstrap. And that means we have a situation where we know that there has to be at least two different solutions of our general KLT bootstrap equation. Namely, one has to be the inverse string kernel, and the other one has to be C theory. Now let's look at what the C theory amplitudes actually look like. So for the 4-point, at 4-point, the same color orderings for the two entries famously is given by the beta function. Now we had that the KK-BCJ relation had to hold on the second color ordering. So if I use this BCJ relation on the second color ordering here, I can find the function that I would have called F2, which is the one with the opposite ordering for the last two entries. in terms of F1, which is the beta function. So that's simply a little gamma function identities, then allows us to rearrange it into this form here. Now take that F2 and expand it, and we can compare it with our general result from the Bootstrap for F2. We see that it nicely starts out with a BAS model, and I picked a pi normalization here such that I can match the same value that we had for the string. And then I see higher derivative terms coming in. So C theories indeed is BAS plus specific higher derivative operators. I can match on to the coefficient I had in the general Bootstrap, and I see that the 1, 1 and 1, 0 coefficients have to be the same. And that was the same value that we had for 1, 1 in the string theory. But one thing is different is that A20 is given in terms of the zeta function Z3 divided by pi times alpha prime squared. And you see then the A3s are fixed to be particular values too. So if we give an overview, then we had that the 6-point Bootstrap would fix these higher coefficients except for a certain small set of parameters, small number of parameters. And by picking the lowest terms and these 3 parameters to be particular value, I can either match onto the inverse string kernel, or I can match onto C theory. And you see that these values are quite different. So could one hope, as we discussed before, to say that maybe if I went to 7.8 point or something like that, I might hope to fix, say, A20 in terms of A10 and A11. Well, that can't really happen because we see from C theory that because it involves a zeta 3, there's no way there's some algebraic relation that would fix it in terms of A11 or A10. And similarly, for the higher ones, they involve the higher higher transcendentality zeta functions. So we know that the space of solutions have to include those 2 points, and therefore there's no way we could just get the inverse string kernel right away. So let's talk about what we can actually get out of this. So we know that C theory obeys the standard BAS KK-BCJ relations from the right, so that can I write schematically in this way. But I could then also say, what if I just took my most general solution to the most general ansatz for our F2 and for all our different Bootstrap, and I just impose those relations on the right. So I'm not necessarily saying it's C theory, I'm just imposing, looking at the most general solution that satisfy KK-BCJ relation on the standard form on the right color ordering. Well, at 4 point, what we find that because we can only bootstrap things at 4 point up to a symmetric function, because anything I multiply my polynomials with a symmetric function in S, T, and U would still satisfy the bootstrap. And so there's an ambiguity on symmetric polynomials at 4 point. And it turns out that by just imposing the BAS conditions on the right side, from the right, and I fix the lowest order terms, then up to a symmetric function, I land on bootstrap. So with just 2 functions fixed, I can land completely in Z theory as desired. In fact, when I say I have to fix both, actually the KK-BCJ relations will say that these 2 have to be the same anyway. So I only have to fix 1 number, and then up to a symmetric function, I have bootstrapped C theory from the most general case. So let's ask, where's string theory in this story then? Well, it turns out that if you look at the C theory amplitudes, then they obey string monotony relations on the left. So on the right, we had the BAS field theory KK-BCJ relations. On the right, it turns out that they satisfy string monotony. Now let's take ZT as transpose to be the model whose matrix elements, whose matrix of 3 amplitudes is simply the transpose of that of Z theory amplitudes. Now this will then have the opposite property that it obeys BAS KK-BCJ relations from the left and string monotony from the right. And because it obeys BAS from the left, then we can use it as input as a right sector function in the double copy in an unambiguous way with the standard standard BAS kernel. Now that means that this double copy product with Z on one side and Z transpose on the other side is a well-defined quantity and amplitudes in the theory, and these will obey string monotony relations on the both left and right, just like the string theory kernel does, or just like this inverse string theory kernel does. So is it the string kernel? Well, almost. In fact, it is up to just a very simple symmetric function in S, T, and U. So what does this mean? So we have a hybrid decomposition conjecture with Alan, which says that the most general minimal rank model amplitudes obey that we can decompose them into hybrid models, models that satisfy standard KKBCJ on either side. Then we postulate, and we have tested extensively at 4-point and 5-point up to very high orders in Mandelstam's, that we indeed get the most general result just with some Wilson coefficient shuffled. Now, these hybrid models, GS and SG, then we have learned that they are basically the same as C and Z tilde after fixing the value of just one coefficient. So what does that mean? It means that the most general kernel, and this is just a 4-point statement, is, and the twiddle here means in the same equivalence class, it means that they differ by some ST and U symmetric function, which we can never expect to fix by the bootstrap. So it's the same equivalence class as this hybrid decomposition. We can write SG as the transpose of GS, just thinking of them as matrices. And now we know that this translates into C theory times C tilde up to some symmetric functions. And then we learned that this double copy product of C theory with itself is really the inverse string kernel up to some symmetric function S, T, and U. So this means that when we can bootstrap C theory, then we can also bootstrap the string kernel, and it will always be in the same equivalence class as the most general kernel, at least at 4-point. 5-point and higher is a little more complex in terms of what the ambiguities are, but we can discuss that at a later point. But this means that we're really closing in on bootstrapping that the most general 4-point kernel is in the same equivalence class as the string kernel, and anything you do in this symmetric function is just a matter of shifting Wilson coefficients in the output. So I will end with that, and I will highlight the contributions from my collaborators, Callum, Shruti, Juan Hang, and Aiden in the early work from last year, and the new work with Alan Chen, who has a poster on this subject that you should be able to go and look at. Aiden was instrumental in pointing us in the direction of C theory, and he has a poster on some completely different work. And then Justin is another student of mine who has a poster on some work he and I are doing with Aiden also. So I hope you will get the chance to go see that. And then otherwise, I'll just send happy greetings here from Michigan and happy to try to answer any questions.
Thank you very much, Henriette, for a very nice talk and being very punctual. So is there any questions from the audience here?
Yeah, so some of the structure you described reminds me a lot of a modular tensor category of rational conformal field theories. I was wondering if there's a precise connection.
I have not investigated that. I mean, I think it would be really nice to try to talk about. So if there's a chance, I don't know if we can connect in a coffee break or something like that on Zoom, then it would be nice to try to talk more.
Yeah, in fact, in particular, I was wondering there might be a physical construction where you just take, since you're just doing tree level, you can take a bosonic string with the internal rational CFT and consider Cardi states of D branes, and then maybe the KLT relation for that case can translate into something that relates to the, the tensor category of the rational CFT. But
that would be amazing. That would be fun. Is it Xi Yin talking?
yes.
Okay, all right, that was my guess. Great, let's try to talk at some point about that. That would be fun.
Yeah, great.
All right, Oliver has a question.
Hey, thanks a lot for the exciting talk. Maybe you already said it and I missed it. To which extent are you paying attention to the poles and the zeros of the Z integrals that we at 4-point can read out from the gamma functions?
So they're not directly playing any role in what I have to do. So because I look in the alpha prime expansion when I match, the poles and zeros are more obstructed. But one thing that is true is that in these double copies, for example, now just pointing to the kernel here, is that when we look at the kernel, the strings kernel, its poles and zeros are absolutely essential for the double copy of open strings to work and give the correct answer for the closed string. But otherwise, they don't play a role here because we look in the alpha prime expansion and match up.
Okay, thank you.
Maybe since I don't see any more questions, let me ask a question myself. So I'm wondering, since you're looking at the inverse of the Z-series matrix, do you expect that to be simpler than the Z-series itself? For example, I mean, a 4-point is of course trivial, but what about 5-point? Do you expect it to be simpler in some way? Because we know that inverse of the KLT, well, the inverse of the KLT matrix is the Barry-Jones scalar, which is actually harder to write down than the KLT matrix itself.
Yes, no. I mean, so one thing that comes out of this hybrid decomposition, let me try to highlight this again. So this hybrid decomposition makes it a lot easier to calculate. And so maybe that helps answering the question in a sort of indirect way. So when we solved the general bootstrap, we had to impose these rank conditions on very large matrices. So at 6-point, it's 120 by 120 matrix that has to have rank 6. So that means that you have to take all the 7 by 7 minors and set them to 0 in principle. It turns out a small subset of them does the job. But it's still a complex way of solving the problem and very nonlinear until you expand. And so it's a very slow process and hard to go to higher point. If the hybrid decomposition is true, then solving for GS and SG is much easier, because what you're doing is then you're simply taking the general ansatz and imposing the linear KK-BCJ relations on them. So these are linear relations among the ansatz functions instead of these nonlinear 7 by 7 vanishing minors and so on. So once you have GS, you have SG because you just transpose the big matrix. And so this gives a way of solving to higher order and higher point much more easily and straightforwardly. We can go to way higher order using this. And we can verify this with very large counting. So in a sense, as a way of generating kernels, having the hybrid decomposition is quite powerful.
All right, thank you for that answer. And I think in light of time, we should move on to the next speaker. So let's thank Henriette again. Check if it works.
Yeah,
okay.
And is there a pointer? Yeah.
All right. Yeah, so the next speaker is Mariana Carrillo Gonzalez, and she's going to tell us about double copy with topological masses. Please go ahead.
Thank you. Well, indeed, I'm going to tell you about this new type of double copy that I've been working on. And the first half is going to be just a review of basically all the progress that has been done in the past 2 years on how to construct a well-defined massive double copy. And I'm going to be focusing on work that I did with these two students, Arsha Momeni and Justinas Rombutis at Imperial, on these topologically massive theories. And the second part of the talk is going to be something new that I've been working on with Will Eman, Nathan Moynihan, Justinas Rombutis, and Chris White on how to derive this classical double copy for these topologically massive gauge theories, but now starting from a mini-twistor space point of view. So let me start with the big picture of the double copy these days. So by now it's understood that double copy is not just the classic Yang-Mills squared equals gravity, and in fact it's a much broader relationship that this Sage's review picture very well explains. And in fact it can include non-gravitational theories as in the upper corner, but for this talk what I'm going to be focusing on is this bottom corner on massive gravity. And in generally, one understands that corner from originating spontaneously breaking of some massless theories. And what I want to say today is that maybe there can be something more than just that. So let's review basics double copy that everyone probably has seen many times before, just to set notation. So in the previous talk, we saw the KLT version. Now we're going to do the BCJ version. As usual, we know we can divide our amplitude now in a color factor, a numerator, and its propagator, which already here I'm considering that this is going to be the massive case. So I can call this, instead of the numerator is going to be a vector, my denominator is going to be this matrix D minus 1. And we know already that the color factors due to Jacobi identities satisfy these relationships that I'm just schematically going to be denoted MC equals 0. And color kinematics duality for Yang-Mills, for example, tell us that the kinematic numerators satisfy exactly the same. Then we can get our standard double copy. So this is just the old story. Now, we know also that there are generalized gauge transformations, and if we are not constructing our numerators where the color kinematics duality is explicit, we can actually do these generalized gauge transformations that don't change my Yang-Mills amplitude, and basically just change my numerator by a delta n. And since they don't change Yang-Mills amplitude, this delta n should lead to this equation, which is just putting delta n over here being 0. So delta n can basically be written as this matrix D, the transpose of this M for the Jacobis, and some arbitrary vector V. So now when you apply this to what would be your Jacobi identity for the kinematic part, now you can see that this extra part could help you get color kinematics duality. Now, of course, we know that not every theory should satisfy this, and we know that this extra matrix actually is not going to be invertible in every case, and this is actually related to the fact that it has a kernel that's non-zero, which has null vectors, as Henriette just told us in the previous talk, and this corresponds to BCJ relations. So this is the standard story. Now, for the massive case, this is a bit different, and this is different because that matrix that I was talking about is actually invertible if you just consider standard massive Yang-Mills. And that tells you that you can just create any massive theory to something that's color kinematics dual, which immediately doesn't sound right. And yes, there is a problem. So if I grab these new n tilde numerators that I forcefully made to be now satisfying color kinematics duality, and I construct my double copy out of them, in terms of the previous numerators, what I will find is the following. The first part is just our old double copy. So everything's fine. We know that the residues and the poles are the correct ones. But then you get an extra term that basically is proportional to the violations of the Jacobi identities of your original numerators. But it also has the inverse of this matrix. And for the massive case, we know now because that this is going to have unphysical poles. And in fact, this kind of way of writing the double copy was observed before, and it was used to construct a double copy including in loops amplitudes for this paper, but in that case for massless theories, and when you know that color kinematics works the way we know it works and you have BCJ relations, it turns out that this extra term is just a contact term. And since it's a contact term, then everything's fine. You again have the residues and poles that you expect for your amplitude, and you don't have anything on physical. But for massive theories, that's not the case. And now the question is, when is actually this thing that appears here something that's just a contact term? And it was answered in some way in these papers by the following people. And the answer is on the left side of this screen. Well, yeah. And the idea is, yes, if you have a spontaneously symmetry breaking from a massless theory, then you know that that theory satisfied color kinematics duality, so now your massive theory is going to have the same properties as the massless case, which means that that matrix that I showed you before that I said, oh, for the massive case is invertible, now it's not going to be invertible. It actually is going to have minimal rank, which is exactly what was being talked about in the previous talk, but in the KLT version. So now if it has minimal rank, it has null vectors, you have BCJ relations, and you go back to the massless story. So you can construct a well-defined double copy that is physical. So those are the examples that you have on this side. There's also another theory with masses that also satisfies the double copy, but it's still not known if it's for all point amplitudes and for all external massive states, so I'm just going to leave it as an aside. And the thing that I'm going to focus on for the rest of the talk is on this right side for the 3D kinematics. So as I told you, the first issue with the massive theories and this inverting this matrix happens at 5 points. And it actually is also known now that at 5 points, this matrix, the determinant, has a special shape that is proportional to a gram determinant. And in 3D, this gram determinant, since it's going to be an antisymmetric tensor with 4 indices, it's going to be 0, which tells us again we reduce the rank of our matrix. And it's reduced now that it just gives you one BCJ relation. So the important thing here, and I really want to highlight, is that that's completely different from what we had on the other side. On the other side, at 5 points, we had 4, and this was the minimal rank. For 3D kinematics, we don't have 4, we only have 1. It doesn't look like the standard BCJ relations, but that's enough. That's enough to have a good, well-defined double copy with only physical poles and the correct factorization of your amplitudes. So if you just have that one simple BCJ relation, then everything will work out well. And we know now that the theories that satisfy these are these topologically massive theories, and there's large work now being done on this double copy for these theories. So let me just quickly introduce what these topologically massive theories are. And basically, it's just our standard Yang-Mills and gravity, but adding a Chern-Simons form. So let me start from the bottom. So you just have your Yang-Mills as usual, and now you're going to have a Chern-Simons tree form that you include, and the level now is going to be giving you the mass. And this only describes 1 degree of freedom, even though it's massive, so it's like the helicity depends on the sign of the mass. For gravity, topologically massive gravity similarly is described just by our Einstein-Hilbert term, but with a minus sign with respect to what you will usually have, just so you don't have ghost degrees of freedom. That's something that these topologically massive gauge theories require. And you also just have a Chern-Simons term, and it just propagates again 1 degree of freedom. And indeed, we have shown that these kind of theories do satisfy the double copy for 3, 4, and 5-point amplitudes and satisfy this special BCJ relation that I've been talking about. Sorry. So now what I want to ask is another question. So we know that the double copy, besides for amplitudes, it also holds in certain classical context. So if I want to go to a classical context, an interesting place to start looking at in its relationship with amplitudes is to go to iconal limit. So let's consider scattering of a massive scalar of mass m, the same the mass of the Yang-Mills field. And let's do its double copy, just standard BCJ. And we will find that indeed it double copies to something that is a topologically massive graviton, but it has an extra term depending on this contact interaction from these scalars. Now, if I want to build a classical double copy, we usually require that you don't have any extra terms here, but that's going to be fine for us because we're going to look at the iconal limit, and in the iconal limit, which is related to the classical limit, this will be subleading, and we're going to have our standard classical double copy. Okay, sorry, I guess it's slow. Okay, so in fact, these amplitudes that I was showing to you in the iconal limit are related to shock waves. So we can see in an old-style double copy now, the Kershil double copy, that indeed shock wave solutions of this theory will satisfy this double copy relation. And to see this, you have to choose some special boundary conditions, but nevertheless, you can pick that on one side of the shock wave, you will find a double copy relation in this Kershil-like metric, where the metric is, as usual, just given by Minkowski plus 2 null geodetic vectors and a scalar field phi. So the scalar field phi for gravity on one side double copies to the one in Yang-Mills, which will be the corresponding single copy, and on the other side it doesn't. Now the question is why that doesn't matter, and the answer is on that side of the shock wave, we actually don't have anything. We have no curvature on gravity, we have a 0 field strength, which also tells you something. You're not looking at the right variables to understand the double copy. So instead of looking at the fields, a more interesting double copy is to look actually at the curvature. So in 4D, what you will usually do is look at the Weil tensor. In 3D, this is 0, but the analog will be the Cotton tensor. So if we look at the Cotton tensor, we will see that this shockwave solution satisfies this relation of the Cotton tensor is actually the square of the dual field strength. And a simple question will be like, why do you even have that relation? And you can motivate it by looking again at plane wave solutions, which is the simplest solution you can think of. And by looking at that plane wave solutions, we can start with like our linearized cotton tensor that is described by this. And you can notice immediately it's order p cube. So if you want to build a square, some sort of square, if you want to build it out of the field strength, you actually realize that you need extra derivatives. The field strength will be only order p, this will order p, but if you add an extra derivative, you get your order p squared. Now, if you look at the linearized equations of motion for topologically massive Yang-Mills, you will realize that this is equal to the mass times this, which is basically just the dual field strength. So again, you get this relation of the cotton being equal to the mass and the field strength square. And basically, this is what led us to propose the cotton double copy, which is the analog of the now well-known version of the Weil double copy in 4D. So for those that are not familiar with the Weil double copy, the idea is basically to look at the spinorial formalism for gravity. So we just take the fact that the Lorentz group is double covered by SL to C. In 3D, we're going to assume the same, but now with the Lorentz group in 3D, double covered by SL2R. So this simply means that now, instead of bracketing our vectors, we're going to take these spinors. In 4D, there's the dotted ones. In 3D, we don't have the dotted ones. Now, for the Weil double copy, it's now known that you can write the Weil spinor as the square of the field strength spinor over S being a scalar. And this scalar satisfies the equation of motion written here, which is the conformally coupled scalar, while the linearized equations of motion for gravity and for Yang-Mills are the following if you write them now in spinorial notation. Now for the cotton double copy, basically we have the same story, but the interesting thing now is that if you write the cotton now spinor as the square of the field strength spinor, the equations of motion that just look like just simply adding a mass on the other side, these correspond to topological masses. In principle, I don't think it has been pointed out before in the literature, but these simple equations of motion are exactly the topologically massive gravity equation of motion and the linearized topologically massive Yang-Mills equation of motion. Now, the interesting thing perhaps here is that the scalar is now not conformal. While in 4D you have a conformal coupling, in 3D you actually have the exact same coupling and of course a mass. So this starts hinting to a perhaps dimensional reduction relation of why we have a cotton double copy. Could it be just a dimensional reduction of what the Weil double copy is? So I don't have an answer for that, but I'm just pointing out that there are some hints that this could be true. And now as an example, I'll just show you here that we have proven this cotton double copy relation explicitly for type N solutions. So these Petrov type N solutions are basically just wave solutions. They're defined by a cotton spinor that it's given like this in terms of a dyad, which is just a basis for the spinors. And if you have this type of spinor, it means you have just one principal null direction repeated 4 times. And it's a very simple double copy relation now in terms of these Newman-Penrose scalars. And we've checked that it works for shock waves, girotones, if you include spin, and also in ADS. But now we would like to understand if it actually works beyond just these wave solutions. Since in 4D we know that the double copy works for what's called type D, which is just like solutions for stationary objects like black holes. And it's not entirely clear if this 3D double copy works beyond just these wave solutions. And by that I mean in coordinate space, because we could have a double copy that we know that squares in momentum space, but it's not entirely clear if it's going to square in coordinate space, just like this nice squaring for the wave solutions over here. So now going to the second half, that's going to be slightly shorter but more technical. What I'm going to tell you now is how we can understand this from mini-twister space. So the very quick summary of mini-twisters in one slide is the following. So all you need to know is that mini-twister space, you can think of it as the space of null planes. Now I'm going to work in complexified Minkowski, so you can think of C3 and all the null planes that you can construct in C3. And they're defined by this equation of motion, where u is just a complex number equal to n mu, which is going to be the vector perpendicular to your complex plane, times x mu, your coordinate. So since we're in 3D, now this null vector can be expressed in terms of spinor of one simple spinor, which tells you that to define these null planes, you only need these two quantities, your u, so one complex number, so our mini twister is going to be u, and lambda alpha, so one spinor. So this is going to be your mini twister, and it satisfies this so-called incidence relation, which is just the equation of the null planes. Now, if you realize this equation for null planes is actually invariant under scalings, and this rescaling is taking this u to r squared and the lambda alpha to r. And if you plug that in here, that equation is going to be invariant. And that will be your standard description of mini twisters. But if you actually dig a bit more into the literature for mini twisters, you find that that's not the only scaling that mini twisters are invariant under. And there are two ways of understanding this, one more physical than the other. One is to just realize that mini twister space is actually a quotient space of ESL to C over Q, which is just a closed subgroup of ESL to C that gives you the isometries of the null planes. Now, this group Q actually is going to have two parameters, and these two parameters are going to correspond to rescalings and some extra translations. Now, another point of view that I think is also more interesting on understanding these extra symmetries, well, extra equivalences for mini twisters is looking at dimensional reduction. So if you look at the dimensional reduction of your coordinate spinor in 4D, you can contract it with this matrix, if you want, in SL2C that just corresponds to the direction of which you're doing the dimensional reduction over. And what you're going to get is the symmetric part corresponds to your 3D coordinate, and the antisymmetric part is just the direction that you're doing the dimensional reduction over. Now, if you plug this in what was your incidence relation, you realize that besides the scalings that you had with this R, you also have this shift that you can do over here, and your relationship would still be invariant because lambda b is basically 0. Now, why am I telling you about these extra scalings? And the reason is that that's what's going to allow us to construct a relationship with actually massive theories and not just massless theories. So the relationship between coordinate space fields and mini twisters is given by Penrose transform, and what I'm going to talk about here is just the massive version, which I'm going to be calling the massive Penrose transform, which gives you an isomorphism between solutions of the massive field equation in 3D and what will be, I'm going to call them twister functions, or mini twister functions, although they're actually representatives of the cohomology class. So basically, what our massive Penrose transform tells us, which is similar to the 4D case, is that if you have a field with two n indices, so it's a spin n, and you can write it equal to a contour integral, where here you have all the lambdas being your spinor from the mini twister, and this that is just a function, and this just indicates that it's under the incidence relation, meaning that it has to satisfy the equation for the null planes that I showed you before. Now, the special thing about these functions is that if you want to consider the relationship with massive field theories and massive solutions, these scalings become important. So before I told you, okay, we know that mini twister has to be related under these scalings in certain way. Now these functions of mini twisters also have to satisfy certain properties so that this integral is well defined. One that is already known from 4D twisters is that it has to be homogeneous of certain degree. So by that I mean that when you rescale your twister space by this scaling of R, your function has to scale like R minus 2n minus 2. And this is just accounting for the measure that you have here and the factors of lambda. But again, the important part of telling you why there's this extra parameter that's related to the translations where you do the dimensional reduction over is that you also need to take into account how this function scales when you do these translations of your spinner. And it is required that it scales with an exponential form. And again, you can just think of this as being a function that is, so I told you this is just a quotient group. So if you know that mini twister is a quotient group, then it has to translate on the, sorry, this function has to be actually transforming on this complex representation of this subgroup Q. And the complex representation of this subgroup of ESL2C is actually just this homogeneous R minus 2n and this translational parameter e to the I CM. So now we want representatives that translate in this form. And the representatives are actually something very simple. You just have an exponential with minus m and these products of an arbitrary twistor A, your coordinate x, and your spin or lambda, and a function g that depends just on your mini twister coordinates u and lambda. Now, this part is, again, just like the 4D massless case, but this is the extra part that you need for the massive case. And this is what allows you to check that, indeed, this satisfies the massive equations of motion. So now we have a way of relating a field that satisfies our topologically massive equations of motion and just a function, again, quote, quote, function, because it's a cohomology representative in mini twister space. Now the question is, can we use this to understand why do we have the double copy relationship, the Cotton double copy that I showed you before? And the answer is yes. For type n, for the waves, it's very simple. And it is known that there are some specific representatives that you can write that will give you certain Petrov type just because of knowing how many null directions your Cotton tensor will have. For type n, it is known that you require that it has only one simple pole like this. So if you write a twister representative that looks like the following and parameterize your spinners in terms of 1, z, just a z in the complex, you can very easily just do this counter integral for any of these representatives, since it's going to be just a simple pole, and we're going to assume that this exponential here has no poles. And by doing it, you will find a very simple relation that indeed corresponds to a lot of wave solutions in topologically massive theories. Now, why this gives you a proof of the double copy is because we're going to assume that there's a double copy relation first in mini twister space. So then you have this relation that the cohomology representative square over a scalar one is equal to the gravitational one. Of course, this is squaring, since it's cohomology representatives, is not well defined. So we have to pick a specific representative. And this actually has been understood for wave solutions in 4D by picking what's the characteristic data at infinity. So for waves, there's no problem on how to pick which representative we want. But for type D, now we would like to understand if we can do the same. So we also know how to pick these representatives that will give you a type D solution. Again, type D just means fields around an isolated object, so something like a black hole. And they're of the following form, where there's like a quadratic function here, because you're going to have poles of 1 plus 2n order, where you have an n spin field. Now, if one tries to do the same kind of proof of why you should get a double copy relation, if one can easily construct a double copy relation for the twister functions, one will see that this is not possible for type D. It might not be obvious from here, but the reason is that in 4D, the proof is very similar, but again, you don't have this exponential. So in 4D, you basically do the same kind of residue, and you find that you have this relationship giving your double copy relation if you don't have an exponential. When you have the exponential, that nice double copy relation in coordinate space breaks down and you don't find it. So this kind of tells us that nice double copy in coordinate space that we're searching for might only work for the wave solutions and not for anything else. So just to conclude, let me tell you that what I try to show you today is that we have a lot of evidence from both amplitudes and the classical side that there is a double copy relation for these topologically massive theories. There are several open questions, such as how to do the double copy for non-equalized matter, and there are several answers by looking at double copy for anyons, which looks like everything works fine in momentum space, but not in coordinate space again. Now, type D, as I've been mentioning, actually it's known that it's just a squashed ADS in topologically massive gravity. So perhaps all these anion solutions are also not type D and not what we should be looking at. And lastly, and probably one of the biggest and most interesting questions for me is if this has any origin in dimensional reduction. Thank you.
Great, thanks Mariana for a very nice talk. Is there any questions here from the audience? Sylvia?
Yeah, so for this type D, you're saying it fails to...
Do you want a microphone?
There's a microphone behind you.
Sorry, can you hear me?
Yeah.
For the type D, you're saying it fails to factorize as a single product?
I think it's not on. No. All right, sorry.
Okay, yeah, that's... So for type D, you're saying it fails to be just a nice product like it does in the massless case. But so in the massless case, we were finding when we were trying to go beyond type D, like doing type 2, type 1, that we get like sums of products. Have you thought about if that might be a possibility for these guys?
We haven't checked carefully. My immediate intuition is that it's not going to work as nicely, but it might be. Yeah, it's just literally that extra exponential factor that messes up. Yeah, you just get different principal null directions that just don't match.
Oh, and not even as a sum, you don't see how it could be.
I think we can try to look more carefully, but so far it doesn't look like it. Also, I would say it's not entirely clear that for the mini twister case, this is the only cohomology representative that you should be looking at. Although that's what you will get actually relating it to amplitudes, but it's not entirely clear that that's the right one.
Great, I guess I have a question myself. Have you thought about supersymmetrizing what you're doing?
Yeah, not enough, but it is likely that it could explain a lot of things, especially the like of the question I put there, like the first one. Yeah.
Maybe I ask one more question. So you find unique numerators because you can invert this propagator matrix. And so do this numerator have some interesting properties? Do you see a pattern? Could you write them down to all orders? Or how difficult is it to compute them?
Well, I mean, so it's only 5 points, but even with these 5 points, the only nice property is that BCJ relation that we can write between them. Aside of that, I don't think there's anything nice we can see immediately, unfortunately.
Right, I see no more questions, so let's thank Mariana again. Yeah, so the last speaker of today before the reception is Sylvia Nagy, and she's going to tell us about generalized asymptotics in the self-dual sector. Go ahead.
Okay, so thanks so much to the organizers for having me here and for organizing this very nice conference. And today I'll tell you a little bit about some work in progress. Oh, I don't think the pointer is... Is it just this middle one?
Sure.
I can't really...
Does not work? The
Oh yeah, if I press harder, sorry. Yeah, so this is some work in progress that we hope will appear in a few weeks with Javier Peraza, who is an excellent PhD student who will be finishing next year. Okay, so I'll jump straight into it. And okay, so we all know, everyone working on amplitudes knows that asymptotic symmetries are very useful in that they tell us about infrared properties of radiative fields, and most famously the amplitude factorizations and soft theorems and so on. So just to give you a picture, if I'm working in the Bondi coordinates, I will be focusing on the free data AZ, and it has this kind of fall off, which I think everyone is kind of familiar with. And then the leading soft behavior, so I didn't even write it down for the amplitudes because I assume people will be familiar, just the Weinberg factorization theorems are a consequence of asymptotic symmetries, with parameters that are of order r to the 0. So then we can see how this free data transforms under these large symmetries in the following way. Okay, so up to here, everything is nice. However, since Weinberg's times, there has been progress in going beyond these leading orders. So here I just gave one example of going in gauge theories to the next order. So here omega is the energy, and we have some nice, in the limit omega equals to 0, we have these nice relations at second order, and S is just some differential operator, so the details are not important. The important thing is that we have these nice relations in amplitudes, and we assume that they will be consequences of some symmetries. And it has been proposed that they are consequences of these order R gauge symmetries. And now this leads to an issue, which is that our free data AZ was order 0 in the radius. However, this lambda now, this parameter is order R. So we have a violation of the fall off of our free data at null infinity. A similar story that you might be familiar with arises in gravity, where I have this order R fall off for the GZZ, and then the super rotations, unless I take this YZ vector here to be holomorphic, will violate this fall off. But people have noticed that we can allow this to violate the fall off, and we get interesting relations in amplitudes. So ultimately, the issue is how to resolve this violation of the fall-off. And the first naive guess would be to relax our fall-off for the gauge field, right? So our gauge field started at order r to the 0, so why not have it start at order r to the 1? However, it turns out this doesn't work. This leads to divergences when we compute the charges. So instead, I'll show you on the next slide, this issue was resolved at order r. And the main question of this talk will be how to extend it to all orders in the field and to all orders in R. So capturing all sub-leading effects in the amplitudes. However, we don't yet know how to do it in the full theory, so we started with the simplified setup of the self-dual sector, where we have a very nice control of our symmetries. Okay, so in self-dual Yang-Mills, it helps to work in these light cone coordinates. You will see soon why, because they make everything look quite nice. And then we separate our space-time into these two subspaces. Our Minkowski metric has this cross form here, and we will be introducing this anti-symmetric pi, which will help us write our gauge field in light cone gauge in the following simple form. So this is just a bit of notation for now. And the self-dual sector, for those who are not familiar, is just the restriction of our gauge theory to the self-dual condition. So if I define the dual of my field strength and I set it to be equal to the field strength itself. Okay, so in this setup, okay, now it's, okay, in this setup, we now look at residual symmetries, and this will be the symmetries that we will consider. So I want to preserve this particular light cone formulation of my self-dual Yang-Mills, and then the residual symmetry is no longer the full gauge symmetry, but a restricted symmetry such that I preserve this AI equal to 0 condition, and this just means that my lambda is now just a function of y. Good. It turns out this condition also automatically preserves the Lorentz gauge, and from now on, instead of working in the Bondi coordinates, we will be working in these light cone coordinates, and the fall-off is very similar. So instead of thinking of working in R, just think of as working in this V. Okay, so this, okay. Okay, so I can start with defining my radiative phase space now. Instead of a Z before, I have this new AZ, and I have this fall-off in V. And now the allowed fall-off for the standard large gauge transformations, you see, only goes up to order 0 here in V. But we would like to go beyond this. And first, I will just show you the linearized extension. So how can we go to the next order? So just order V to the n. You see, immediately we have a violation because AZ stops at V to the 0. However, it turns out that we can define an extended phase space. And we do it in the following way. So we define this A tilde to look as if we have done a gauge transformation. However, this psi here now is a new field that we are introducing in our phase space. And this field has the following fall-off. So it goes as linear in V. And we also take it to have the same coordinate dependence as the parameter, but now this psi is an actual field. Good, so for these phase space, we then have the following consistency condition that we would like this extended AZ to transform the standard way under a Yang-Mills gauge transformation. And the reason why we do this is if we think about where this guy came from, so where did this extension came from, so it helps to think of it as in the bulk, we are allowed to have any kind of order in V, right? We can have any kind of dependence on the coordinates. But when we go to null infinity, we don't want to have this, as I was saying, the charges start to blow up if we do this. And instead, we select only the pure gauge part of the order V part. So this dz psi, you can think of it in that way, but you can think of it as having come from a full gauge field in the bulk. Okay, so from this consistency condition, then, we have the standard variation for AZ, so now we don't have any violation, and we can read off the transformation rule for the new field psi that we have introduced. So this is our extended phase space. Good, now going back for a second to Bondi coordinates, we can then construct charges here. So there's a charge related to this first order lambda, and then the 0th order lambda, and then they satisfy a nice commutation relation. So now, this is just to show that now everything works nicely. At null infinity, you can define your charges, and then you can see the subleading soft theorems coming from here. Good. Now, how do you extend this to all orders in V? So to do this, it kind of, as I've already mentioned, when I look at this extension that we've defined here, this looks a little bit like a gauge transformation already. So for those of you who are maybe, I don't know, familiar with cosmology or something, this looks exactly like the Stuckelberg procedure when we reintroduce a broken local symmetry. So the procedure there is that we perform a transformation. So of this form, this is just a standard gauge transformation, and then we promote the parameter to a field. So this is the field psi that we've introduced here. Good. And then, if we want to go to all orders in V, it turns out that we actually have to go to all orders in psi here. So this is just the full, this is just the full gauge transformation for Yang-Mills now. Good. The consistency condition then is as before. So when we do the actual transformation in terms of lambda, we only consider it to linear order, and then it gives a nice expression for this operator, and then from here we can read off the transformation of psi. And now we have this psi working to all orders in V, i.e. all orders in R in the phase space, and all orders in the field. So this is now our psi, which allows for all sub-leading effects at null infinity when we will change to the appropriate coordinates. So this is the extension for Yang-Mills. It turns out you can do the same for gravity. So the self-dual sector is quite simple even for gravity. So the definition here of self-duality is very similar. So again, we define the dual tensor starting with the Riemann, and we set it equal to itself. It turns out the metric can be split in this very nice way. And this, I want to emphasize, this is an exact splitting, so we're not doing perturbation theory. It just so happens that in this context, you can do this nice splitting. And then in the light cone gauge, this is, you see, very similar to the gauge case. You can write the metric in this form, and it turns out to automatically satisfy the transless, traceless gauge condition. And the diffuse that we're interested in now are of the following form. So we are doing a diffuse transformation, but we have had to restrict our parameters in the following way. And the transverse tracelessness is automatically preserved. Now the self-dual gravity, it has been shown, has some very nice double copy relations with the self-dual Young-Mills, which I will not show in detail. Sorry, we will focus on the symmetry part. And here it helps to introduce a little bit of notation. So starting with just a standard diffuse transformation with these parameters, it helps to define this Hamiltonian in terms of which I can write my diffuse transformation basically as a Poisson bracket, as a linear term plus a Poisson bracket. And then remembering that this was my Young-Mills transformation, I see some very nice double copy rules between the Young-Mills part and the gravity part. So basically, under these replacement rules, so the commutator going to the Poisson, phi going to phi, and lambda of the gauge field going to this Hamiltonian, you see that I recover from the Young-Mills up to this extra operator here, I recover the gravity diffuse transformation. And the way to think of it, if you're more familiar with the amplitudes, is that this commutator corresponds to kind of the color factors, and this is kind of the kinematic part. Good. So up to here, we are just looking at things with a standard fall-off. So they will stop at order r to the 0. So also our h will stop at order r to the 0 now that we're working in this v, which you should think of as instead of r. But we would now like to go again just like one order higher than that, and it turns out now everything is analogous to what we've done for Young-Mills, right? So now I define this extended phase space, this h tilde, which looks just like a diffuse transformation of my h, but where instead of the parameter, I now have this field psi, which is kind of I've replaced this Hamiltonian lambda with a field psi now. So it has a very similar form, but this is now a field itself. And under the consistency condition, then I can read off the transformation rule for this psi itself. And because this looks just like the symmetry transformation, but with the parameter replaced by the field, the double copy will just work trivially now. So I just extend this by saying psi of the Young-Mills goes to the psi of gravity. Good. But then we also wanted to go to all orders in the gravity case. So the way we do this is we take the Lie derivative and we simply exponentiated its action on the metric. So this is just a standard Lie derivative. And it turns out, after a little bit of calculation and massaging these expressions, it turns out that you can put it in this form. So this lambda is just the same lambda Hamiltonian that I've shown you before. And it turns out, so for a restricted transformation, of course, this is not the full diffuse transformation, you can have this nice exponentiation. Then, once I've written my transformation rule in this way, so I've introduced this new notation for the action of the Poisson bracket, this mat-frac add here. So now we are ready to extend our gravity parameter to all orders in V, which is all orders in R, basically, by defining this full extended phase space for gravity in terms of this psi, and now this psi, as I was saying, goes to all orders here. Good. Okay, so remember we had this nice splitting in gravity between eta and h, which was exact, even though it looks like it is perturbative. It was just a consequence of working in the light cone gauge. It turns out that even under this full extended thing, it is still preserved very nicely. So this guy is still 0, and this h still splits very nicely like this. Okay, so now, because the double copy was working so nicely for the standard transformations for these subsets in the self-dual sectors, we were wondering if we could also see it for these all-order transformations, which it doesn't look obvious at all if you look at the form of these transformations, but it turns out that it will work quite nicely. So first, let's start with this. This was the full extended phase space for Yang-Mills. So you can also think of it as just like the full transformation for Yang-Mills, where I'm taking the parameters to all orders, but except this is the field here because it's my extended phase space. Here, after a lot of massaging again and using just general properties of these exponential operators, and using the fact that my psi is just a function of 2 of the coordinates now, it's not a full gauge transformation, it turns out I can write it in this very nice form. And I hope here it's not too confusing. This phi is the phi that was used to define the gauge field in the light cone formulation, so it's not related to this psi here. But it's just helpful to put it in this form because it's how we formulated the double copy relations. And then we also have this operator which I've defined down here, and we have in terms of an exponential of the action of the adjoint operator. So this is just a commutator, the adjoint operator, and this has a little bit of a funny form. You see that you have this kind of, you're dividing by this operator, which is like a commutator, but it turns out that it has a nice order by order expansion. So this is the closed form for it, but it has a nice order by order expansion where it's just a set of nested commutators. And this is just a way to write them out. So you can imagine expanding this E. Okay, so now the double copy that we had before, it's exactly the same. So here, I've just changed the notation. So this was like the commutator, like the color factor. It goes to the Poisson bracket, which is like the kinematic factor. I'm sending this, this bold phi, which defined the gauge field in the self-dual sector, to the little phi, which defined the graviton in the self-dual, and then these extra psi's that I've introduced for my extended phase space. Then I simply take this object A here in the form written here, apply the double copy rules. Remember, I need an extra operator of this pi, and then after some rearrangement, I get to the following form in terms of H and in terms of the psi of H. And this omega is defined as just a double copy of this kind of scary looking exponential operator. But this form, it turns out, again, after a little bit of massaging and after a little bit of rearranging these exponential guys, is exactly the H that I was showing you earlier. So it's exactly this H that I had before. So kind of to kind of summarize what I was doing, because I was kind of using, this notation that maybe, I think now it's died. I was using this notation that's very specific to the, to the self-dual formulation in the light cone gauge. So if you don't care about these particular details, you know that of the notation that we have been using, and kind of the take-home message is that if I start with, now let me think of it as an actual symmetry transformation. So if I start with this full symmetry transformation for Yang-Mills to all orders in the symmetry parameter, but with the parameter slightly restricted, it then, under these very simple double copy rules that I've written here, it double copies to the Diffie transformations to all orders in the Diffie parameter, but again with the restricted coordinate dependence. And to our knowledge, this order thing had not been observed in the literature before. The main issue here that we have, that we would like to understand better, is, of course, how to go beyond these restrictions. So these restrictions were important for us because, of course, there is something special about the self-dual sector, and the double copy works very nicely there, and this is why we think also the symmetries double copy worked up very nicely. But there are some ideas for looking at least at asymptotic symmetries for the full theory as residual symmetries in the light cone gauge. So maybe I will finish a bit early, maybe. So, sorry. Something that we are looking at doing next is extending to full Yang-Mills. So the reason why we worked in the self-dual case and with these restricted transformations, and the reason why the previous phase space extension was done only to order R, is because basically we wanted to say Yang-Mills first. If you're doing just Maxwell, everything is easy and you can go to all orders in R. But for Yang-Mills, things get very ugly very quickly, because the way we traditionally try to derive these asymptotic gauge symmetries, so one way is we set a gauge fixing, and then we set a certain fall-off, and then we calculate what sort of solutions we can have with this fall-off starting off at null infinity and satisfying, you know, being a residual symmetry of this gauge fixing. And what happens in Yang-Mills, maybe I should have given some explicit equations for that, but what happens in Yang-Mills that makes it very complicated is that we get a lot of log terms, and then we get our symmetry parameters themselves end up depending on the field. So things get very, very complicated when we try to start off with these more unusual fall-offs. And this is why the previous work had stopped at linear level in R. However, in the light conformulation, in the self-dual case, everything was much simpler. So these residual symmetries, we could have a simple fall-off, we could ignore the log term, so that was eliminated, and also we didn't have a field dependence in our gauge parameter. So that solved the issue. But something that we have noticed very recently is that perhaps one doesn't actually need to restrict to self-dual case, but for the full Yang-Mills in the light cone formulation, it should be able to get a nicer description of these unusual fall-off symmetries, and then perhaps also for gravity. Whether the double copy still works as nicely in that case, it's a little bit unknown. There are some hints there has been some work done at cubic order for those cases, but we don't know whether something as nice as this, as nice as this all-order thing would still work. So that's still an open question. And then some other open questions are possible relations to infinite towers of symmetries in the self-dual sector. So we know that the self-dual sector is integrable, so we actually have an infinite tower of symmetries that we get recursively in the self-dual sector, and there's a nice pyramid one can construct, but now we can also go to all orders in R. So there's a very nice interplay between those two there that I didn't have time to go into, and linked to that story is a possible relation to these W infinity algebras. So maybe I will finish a bit early.
All right, thanks very much for a nice talk and finishing before the time limit. Yeah, so please go ahead, ask a question.
Thank you for the lovely talk. Partially because I don't have my glasses on, so I just want to make sure I can repeat it back, and then you can tell. So you're basically just exponentiating what would be the generator of like the subleading soft photon or like the sub-subleading soft graviton, and then getting a very restricted, I guess, like overleading dependence of the full like gauge field. And so somehow, sorry, am I summarizing that correctly? And then you're getting the W infinity because some of the first few generators of that algebra generate the rest of them? Okay.
Yeah, that's kind of an open question, the link to the W infinity. So that is something we still have to go into. That's more speculation based on the relation to some previous work where we were getting this infinite tower that looked very related. But we haven't actually looked at it explicitly yet.
But like, so would you guys say that like you wouldn't have independent like overleading like beyond this like first leading and overleading in R? Sorry. So like a gauge field that goes like R squared, you would not say there's an independent symmetry generator for you? Because it's a very particular form coming from that exponentiating of like the linear in V guy, right?
Yes, you can think of it as coming from the exponentiation, because in this case, it doesn't mess things up. And the reason why it wasn't messing things up is because you didn't have a field dependence in the parameter.
Yeah, so you would say you can't, or sorry, I guess like it's only that particular form of all orders in V for you, or would you try to find like additional like independent infinitesimal transformations that are starting at order like v squared for you, I guess.
Yeah, so do you mean at v squared would the transformation be just like the truncation of that exponentiation too?
No, I mean, sorry, maybe from my point of view, basically, like completely in ladder or whatever, they're able to make sense of the order, like v term, which is what you have, and then, sure, if you want to say that that's the infinitesimal, like, gauged parameter, and then you're exponentiating it, you somehow get this special tower, like, that's distinct from trying to talk about, like, a set of independent charges at each order in v, I think, right?
Sorry, can you say the last thing?
No, I guess what I'm saying is whatever gauge parameter would have, like, generated the linear in v term, you're just exponentiating that, right?
Sorry.
Or no, my glasses are off.
Sorry, I see your question now. Yes, no, sorry, maybe I went too quickly there. So, yeah, I think I went too quickly when I was showing that. So it's actually more, sorry, I see your question now. It's more general than this.
Great.
Sorry, this is, okay, yeah, let's do the full. Okay, this is the linear extended phase space. So here, let's say I have this psi, that's like the psi1, and this is the coefficient of just v to the 1, right? However, okay, good. When I do the full extended phase space, this guy, my psi here, which, did I even write the full psi? Okay, so you can imagine just lambda here being the psi, right? Because I can just replace
But it has
lambda.
all powers, or?
Yeah,
Okay,
these
sorry.
lambda ends are all arbitrary,
Great.
unrelated to each other,
Great, thanks. Sorry.
Yeah,
My
sorry.
glasses are off,
So it's not the exponential,
Perfect.
it's much more general than that, yeah.
Thanks, sorry about that.
I guess I'll ask a question. What's the applications, for example, to classical double copies? Do you have anything in mind, or?
You mean to solutions?
Yeah.
To classical solutions. Yeah, that's a good question. So for now, we haven't thought about solutions because this is more like in the sense of symmetries. However, because these are large gauge symmetries, they really can change your space of solutions. So in that sense, you could think of, I guess, generating solutions from them.
I mean, I guess, well, I don't know much about it, but there are interesting self-dual solutions to Yang-Mills and to gravity, I guess. Yeah.
Oh, yeah, like instantons and stuff, yeah. So there you should be able to see some nice, yeah.
Okay, Ricardo has a question.
Thank you. Thanks for the talk. Related to this, have you thought of solution generating techniques for these theories and how they may relate to this?
Solution generating?
So these theories are classically integral.
Yes.
And there are procedures to construct solutions. And I was asking if you thought about the interplay of that with this. So what you're doing here, you're considering like finite large gauge transformations and seeing that they double copy. Is that the correct interpretation?
Yeah,
of what you're doing?
The first goal was to kind of extend the phase spaces to all orders. And then the double copy is just something that kind of seems to happen in the self-dual sector almost naturally. So we thought might as well write that as well. But our main goal here was how to extend these phase spaces beyond just linear order in R, which turned out to be necessary to extend them beyond linear order in this new psi field that we're introducing. So the double copy was more of a secondary thing for us here, so we haven't really thought much about, but you're right, like in the self-dual case, it should lead to some solution generating things, but we haven't looked at it in detail yet.
Thank you.
All right, I think we should probably thank Sylvia, but let me just ask, do you want to say something later on? Yeah, okay, so let's thank Sylvia.
So probably you have noticed before concluding the first day, there is still one item in agenda, welcome reception. So of course you are all welcome to attend. There are 2 floors, but yeah.
There is a better food on the 2nd floor, so.
But don't forget, it is also a poster session, so there are more posters on the 2nd floor as well, so please.
So when you leave this room, there will be aperitif on both sides. So if you wish, you take that first. And also reminder that people with allergies should go to the right side on the 1st floor. Yeah. Okay, thanks a lot all the speakers of today and welcome.